Space is filled with mysteries that challenge our understanding of the universe. Despite centuries of scientific progress, the cosmos continues to surprise and bewilder us. What is the true nature of dark matter and dark energy? How do supermassive black holes influence entire galaxies? These are questions that push the boundaries of science and fuel our curiosity about the vast unknown. One of the most captivating mysteries is the WOW signal shoal, an enigmatic radio signal that remains one of the most intriguing phenomena ever detected by astronomers. Discovered on August 15, 1977 by Dr. Jerry Amen using the Big Ear radio telescope at Ohio State University, this powerful narrow-band radio signal was unlike anything previously observed. The signal's intensity and its origin, which seemed to emanate from the constellation Sagittarius, immediately captured attention. What makes this signal so remarkable is its duration. A mere 72 seconds, the exact time the Big Ear telescope could observe a fixed point in the sky due to the Earth's rotation. During those brief moments, the signal exhibited an intensity and pattern so distinct that Dr. Amen famously circled the data on the printout and wrote "Wow" beside it, giving the phenomenon its lasting name. Despite extensive follow-up searches, no repeat of the signal has ever been detected, leaving scientists to speculate about its origin. Could it have been a naturally occurring astrophysical event, a reflection off space debris, or possibly a highly focused transmission from an intelligent extraterrestrial source? The absence of any subsequent signals has kept the mystery alive, and the WOW signal remains a unique and elusive piece of the cosmic puzzle. As humanity continues to search the cosmos for signs of extraterrestrial intelligence, its origin continues to fuel both scientific inquiry and public fascination. Meanwhile, another profound mystery of the universe involves the discovery of ultramassive black holes in the early universe. These behemoths, some possessing the mass of billions of suns, existed when the universe was still in its infancy, less than 1 billion years old. The mere existence of such colossal objects in such a young universe raises significant questions about how they could have formed so rapidly after the Big Bang. One leading hypothesis suggests the direct collapse of massive gas clouds, bypassing the traditional stellar formation phase and collapsing directly into black holes. These direct collapse black holes could accumulate mass at an astonishing rate, potentially forming the ultramassive black holes we observe today. Another possibility involves the merging of primordial black holes, which could have formed moments after the Big Bang in the highly dense regions of space. As the universe evolved, these primordial black holes might have collided and merged into even larger, more massive black holes. Additionally, the extremely high accretion rates of gas and dust in the early universe might have contributed to their rapid growth, allowing these black holes to reach ultramassive sizes in an incredibly short cosmic time frame. While no single theory has been proven, it's likely that a combination of these mechanisms, driven by the dynamic and complex nature of the early universe, explains the presence of these enormous cosmic giants. Adding to the list of cosmic enigmas is the mysterious dimming of Tabby's star, also known as IC 846285-2. Located about 1,400 light-years away in the constellation Cygnus, this star exhibits irregular and significant fluctuations in its brightness. The phenomenon was first noted by astronomer Tabitha Boyajian, after whom the star is named, and has since confounded astronomers worldwide. Various theories have been proposed to explain these dimming events. One of the most plausible is the presence of a large cloud of dust or unevenly distributed objects orbiting the star. These objects could cast irregular shadows as they pass between the star and Earth, causing the observed dips in brightness. The star's infrared emissions support this theory, suggesting that some material is absorbing and re-radiating light in a non-uniform manner. However, another more speculative, though intriguing, possibility is the existence of an advanced extraterrestrial civilization. Some scientists and enthusiasts have proposed that a so-called megastructure, such as a Dyson sphere, could be partially enveloping the star, causing the irregular dimming. While this remains a highly speculative idea, it speaks to our fascination with the possibility of intelligent life beyond our world. Each of these phenomena, whether it's the WOW signal, the ultramassive black holes, or the dimming of Tabby's star, highlights the vast unknowns still present in our understanding of the universe. As we continue to explore the cosmos, these cosmic puzzles offer a tantalizing glimpse into the mysteries of the universe, urging us to look deeper, ask more questions, and, perhaps one day, uncover the answers that have eluded humanity for so long. However, despite ongoing searches for accompanying radio signals and further observations, no concrete evidence of alien technology has emerged. In the quest for answers, a more recent and plausible explanation has surfaced, one that points to a family of comets or debris from a disintegrated planet. These fragments, along with their associated dust clouds, may be on highly elliptical orbits, periodically blocking the light from a distant star. While numerous theories have been proposed, no single explanation has been able to fully account for all the observed characteristics of this peculiar celestial body, making it one of the most intriguing and actively studied objects in modern astronomy. As technology and observational techniques continue to improve, future discoveries may finally unlock the secrets behind this enigmatic star. One of the most profound puzzles in physics remains the apparent scarcity of antimatter in the universe. According to our understanding of the Big Bang, matter and antimatter should have been produced in nearly equal amounts. Yet our universe is overwhelmingly composed of matter, with incredibly little antimatter to be found. This mystery has sparked intense investigation, leading scientists to propose a potential explanation rooted in a phenomenon known as baryon asymmetry. This hypothesis suggests that, in the earliest moments of the universe, slight differences in the behavior and decay of matter and antimatter particles could have caused an imbalance. This led to a tiny surplus of matter over antimatter. When matter and antimatter later annihilated each other, the small surplus of matter remained, ultimately forming the stars, planets, and galaxies we observe today. Further investigation into subatomic particles, particularly neutrinos, may offer more insight into this puzzle. Some theories propose that neutrinos could be their own antiparticles, a property known as Majorana particles. If this is true, it might help explain the matter-antimatter imbalance in our universe. To test these theories, researchers are conducting a range of experiments, including studying neutrino interactions in sophisticated underground detectors. Additionally, scientists are investigating the role of symmetry violations in fundamental physics processes, such as charge parity violation. These subtle violations could be the key to understanding why matter triumphed over antimatter. Despite the depth of this mystery, the ongoing quest to unravel the universe's asymmetry continues to push forward both theoretical and experimental physics, promising profound insights into the very fabric of our cosmos. Ultra-high-energy cosmic rays, some of the most energetic particles ever detected, pose a significant challenge to modern astrophysics. These particles possess energies that are millions of times greater than those generated by the most powerful particle accelerators on Earth. Yet, the sources of these particles remain a mystery, defying our understanding of both cosmic mechanisms and fundamental physics. One leading theory suggests that active galactic nuclei, AGN, supermassive black holes at the center of certain galaxies, could be the source. These black holes are surrounded by intensely energetic accretion disks, where matter spirals inward, heats up, and emits powerful jets of particles. These jets may have the capability to accelerate cosmic rays to the extraordinary energies we observe, propelling them across vast distances in space. Another potential origin of these cosmic rays is gamma-ray bursts, GRBs, brief but immensely powerful explosions that occur when massive stars collapse or neutron stars merge. The energy released during these bursts is so intense that it could accelerate particles to ultra-high energies, launching them into the cosmos at nearly the speed of light. The brief, yet intense nature of GRBs makes them an intriguing candidate for the source of these mysterious cosmic rays. However, there is also the possibility that some of these ultra-high energy cosmic rays originate from yet undiscovered astrophysical phenomena. These could include exotic processes such as the decay of massive particles from the early universe or interactions involving dark matter. Such speculative sources would not only explain the extraordinary energy of these cosmic rays, but they could also reveal new insights into the fundamental workings of our universe. Ultra-high energy cosmic rays, UHECRs, are among the most fascinating and mysterious phenomena in the universe. Their exact origins remain elusive despite decades of research. To pinpoint where these particles come from and what mechanisms drive them, scientists employ cutting-edge detection techniques such as ground-based observatories and space-based detectors. These methods allow researchers to gather vast amounts of data, but the ultimate goal remains to uncover the processes behind these awe-inspiring cosmic messengers. With each new discovery, there's hope that the data will eventually reveal deeper truths about the high-energy processes that shape our universe. One particularly intriguing puzzle in cosmology is the so-called axis of evil, an anomaly found within the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates the entire universe. This anomaly refers to an unexpected alignment of temperature fluctuations in the CMB that appears unusually consistent over vast angular scales. This defies the expected isotropy and homogeneity of the universe on such large scales. The implications of this finding are profound, suggesting that our understanding of the universe might need re-evaluation. One possible explanation is that this anomaly arises from residual foreground contamination. Some scientists believe that galactic radiation or cosmic dust within our Milky Way could be interfering with CMB measurements, despite extensive efforts to cleanse the data from such potential sources. These remnants of foreground distortions might still be subtly affecting the results. Another hypothesis is that the alignment could be a mere statistical fluke. Given the massive volume of data involved, it's conceivable that some patterns could emerge purely by chance without representing any underlying cosmic truth. While proponents of this idea acknowledge the strangeness of the alignment, they argue that it doesn't necessarily point to a flaw in our fundamental understanding of the universe. Yet, there are more radical possibilities. Some theorists suggest that the anomaly could indicate the presence of new physics, ideas that challenge the current cosmological models. Among these concepts are the effects of primordial magnetic fields or even alternative theories of gravity, both of which could be influencing the CMB in ways that haven't been previously considered. These theories push the boundaries of established physics but remain speculative until further evidence is gathered. To explore the axis of evil more deeply, researchers continue to refine their measurements of the CMB, with missions like the Planck satellite playing a crucial role. The data from these advanced observational tools may eventually confirm or dispel the anomaly's significance, offering insights into the very fabric of our universe. In another corner of the cosmos, recurring nova explosions provide a striking example of stellar dynamics at play. Unlike supernova, catastrophic explosions marking the end of a star's life, recurring novae are periodic outbursts that occur in binary star systems. These systems often involve a white dwarf and a companion star, typically a main sequence star or a red giant. The key to understanding these dramatic explosions lies in the intricate process of matter transfer between the two stars. In a typical recurring nova system, the white dwarf, a remnant of a star that has exhausted its nuclear fuel, gravitationally attracts material from its companion. This material, primarily hydrogen, accumulates on the white dwarf's surface, forming an ever-growing layer. Over time, the increasing pressure and temperature from the accumulated material trigger a runaway fusion reaction. This explosive fusion process causes the hydrogen to ignite, resulting in a sudden and dramatic increase in brightness, visible as a nova. The explosion ejects a portion of the accreted material into space, causing a temporary spike in the system's luminosity. These recurring nova explosions offer critical insights into the dynamics of binary star systems and the complex interactions between stars at different stages of their lives. By studying these phenomena, astronomers can learn more about the behavior of white dwarfs, the processes that govern star evolution, and the broader mechanics of the universe. Each nova event is not just an explosion of light, but a window into the complex interactions that shape the cosmos. As our understanding of these stellar outbursts continues to grow, so too does our knowledge of the vast and intricate workings of the universe. However, unlike supernovae, this event does not lead to the destruction of the white dwarf. Instead, the process is able to repeat itself after the eruption subsides. Once the outburst has faded, the system returns to its pre-nova state and the cycle of matter transfer begins anew. The length of this cycle can vary depending on how quickly the companion star donates material and the specific conditions of the white dwarf's accretion. These cycles can repeat over time scales ranging from just a few years to several decades. While each nova event shares similarities with the previous one, no two events are ever identical. The amount and rate at which material is accreted on the white dwarf, as well as the specifics of the eruption, ensure that every nova event is a unique phenomenon. Studying these recurring nova events provides astronomers with invaluable insights into binary star evolution, as well as the intricate physics that govern accretion processes and nuclear fusion under extreme conditions. By better understanding these processes, we can deepen our knowledge of stellar life cycles and the dynamic forces that shape the universe. Nova events are not just spectacular bursts of light, but windows into the fundamental processes that drive the evolution of stars and galaxies. Through them, scientists continue to unravel the mysteries of how stars live, die, and regenerate, contributing to the broader cosmic tapestry. One of the most intriguing puzzles in modern astronomy lies in galaxies like NGC 1052 DF2, which appear to lack significant amounts of dark matter. Dark matter, a mysterious substance that does not emit or absorb light, is thought to comprise around 85% of the universe's total mass. It plays an essential role in the formation and behavior of galaxies, providing the invisible gravitational glue that holds them together. Yet, NGC 1052 DF2 defies this conventional understanding by seemingly having little to no dark matter. This anomaly presents a compelling enigma, forcing astronomers to reconsider what we know about the universe's structure. One possible explanation for the scarcity of dark matter in NGC 1052 DF2 is the galaxy's unusual formation history. It could have been stripped of its dark matter during a tidal interaction or a merger with another massive galaxy. Such a close encounter might have displaced much of the galaxy's dark matter, leaving it predominantly composed of ordinary or baryonic matter. Alternatively, NGC 1052 DF2 might not be an isolated case, but rather a representative example of a larger class of ultra-diffuse galaxies. These galaxies are distinguished by their low luminosity and extended structures, making them difficult to detect. Their diffuse nature could be a result of the initial conditions in their formation, which may have hindered significant dark matter accumulation. Another hypothesis revolves around modifying our understanding of dark matter itself, or even reconsidering the laws of gravity. For instance, alternative gravity theories such as modified Newtonian dynamics, (end), suggest that the gravitational effects observed in galaxies lacking dark matter might be explained by tweaks to Newton's laws of gravity, particularly at low accelerations. However, these theories remain speculative and require more evidence to gain widespread acceptance. Regardless, the study of NGC 1052 DF2 and similar galaxies is still in its early stages. As astronomers collect more data and refine their models, they hope to shed light on the underlying reasons for these anomalies. The findings could challenge our current understanding of dark matter and galaxy formation, potentially leading to groundbreaking discoveries in cosmology. Another fascinating concept that has captured the imagination of physicists is mirror matter, which arises from the symmetry laws in physics, particularly parity symmetry. Our universe, as we know it, exhibits certain asymmetries in the laws of physics. Mirror matter suggests the existence of a parallel form of matter, one that behaves as a mirror image of ordinary matter, exhibiting opposite parity. In this theory, a right-handed particle in our universe would have a left-handed counterpart in the mirror universe. One of the most intriguing aspects of mirror matter is its potential invisibility to standard detection methods. It would interact with regular matter primarily through gravity, but not via the electromagnetic force, making it nearly undetectable by conventional electromagnetic instruments. Despite this, mirror matter could still influence the dynamics of galaxies and large-scale cosmic structures through its gravitational effects. If mirror matter exists, it might form objects similar to those of ordinary matter, such as mirror stars, planets, and even entire mirror galaxies. These mirror objects would emit mirror photons instead of regular photons, making them invisible to our eyes and existing detection technologies. The gravitational effects of these mirror structures, however, could be detected and might influence the movements and behaviors of ordinary galaxies. While experimental detection of mirror matter remains challenging due to its weak interaction with normal matter, its gravitational influence could provide the first hint of its existence. As researchers continue to probe the universe's deepest mysteries, mirror matter presents one of the most exciting and enigmatic possibilities for explaining some of the unexplained phenomena we observe in the cosmos. Through these investigations, we may one day uncover new forms of matter and forces that push the boundaries of what we thought was possible. However, scientists have proposed several potential methods for detecting mirror matter, each of which could revolutionize our understanding of the universe. One of the most intriguing approaches involves searching for anomalies in gravitational experiments. These anomalies, which cannot be explained by ordinary matter alone, could provide the first hints of mirror matter's existence. Another promising avenue is the quest to detect rare interactions between mirror matter and ordinary matter. Sensitive detectors designed to detect ultra-low background noise, such as those used in dark matter searches, may be the perfect tool for this task. The discovery of mirror matter would not only explain some of the universe's greatest mysteries, but also open new doors in theoretical physics and cosmology. It could potentially shed light on the elusive nature of dark matter and unravel certain unexplained gravitational phenomena. As experimental techniques advance, the pursuit of evidence for mirror matter remains one of the most exciting and contentious frontiers in modern science. One of the most fascinating enigmas in cosmology is the mysterious gravitational force exerted by the Great Attractor. This immense gravitational anomaly, discovered in the 1980s, affects the motion of galaxies, including our own Milky Way and many galaxies in our local supercluster. The Great Attractor's pull is so powerful that it influences galaxy motion over a region stretching hundreds of millions of light years, but it has proven elusive to direct observation. Its location, hidden behind the dense, dusty plain of the Milky Way, makes it difficult to study directly, leading astronomers to refer to this region as the zone of avoidance. However, advancements in X-ray and infrared astronomy, which can penetrate this cosmic veil, have provided critical clues. One leading theory suggests that the Great Attractor is part of a massive, dense supercluster of galaxies known as the Norma Cluster, also designated as AEL 3627. This supercluster, located about 200 million light-years away, is teeming with large galaxy clusters and vast amounts of dark matter, which together create a gravitational well powerful enough to influence the motion of galaxies on a massive scale. Another intriguing hypothesis involves an even larger structure known as the Lanaka supercluster. The name Lanaka, meaning immense heaven in Hawaiian, refers to a vast supercluster complex that stretches across more than 500 million light-years. This colossal web of galaxies and dark matter may be responsible for the peculiar velocities observed in galaxies over vast distances. Despite the progress made in understanding the Great Attractor, much remains unknown. Ongoing research, bolstered by technological advancements capable of penetrating the Milky Way's plane, promises to provide more insights into the forces shaping the motion and evolution of galaxies. At the opposite end of the cosmic scale, neutron stars present another extraordinary puzzle. These celestial objects are the remnants of massive stars that have exploded in supernovae. The core that remains is incredibly dense, so much so that it challenges our understanding of physics. These remnants pack more mass than our sun into a sphere just about 10 miles across, creating conditions of unimaginable extremes. Inside a neutron star, the matter is compressed to densities that exceed several times that of an atomic nucleus. The intense pressure forces protons and electrons to merge, forming neutrons, which make up the star's composition. This process results in a star predominantly composed of tightly packed neutrons, and the density near the core of the star can reach up to hundreds of millions of tons per cubic centimeter. These conditions create an environment unlike anything found elsewhere in the universe, offering valuable insights into the fundamental forces of nature. As research continues into both the enigma of the Great Attractor and the extreme conditions inside neutron stars, the universe reveals its vast, mysterious complexities. The more scientists discover, the more we realize how much there is still to learn and how these discoveries will forever change our understanding of the cosmos. However, the extreme conditions within neutron stars push the boundaries of our understanding even further. The state of matter in these celestial giants could move beyond the mere formation of neutrons. Several theoretical models suggest that the central regions of neutron stars might host exotic forms of matter, including hyperons, particles that contain strange quarks, or even deconfined quark matter. In this extraordinary state, neutrons themselves break down into their constituent quarks, potentially creating a quark-gluon plasma, a phase where the fundamental building blocks of matter are no longer confined. One of the most intriguing possibilities involves the presence of nuclear pasta, a strange and fascinating phase of matter where neutrons and protons arrange themselves into shapes resembling spaghetti, lasagna, or even gnocchi in the inner crust of a neutron star. This phase is thought to arise from a delicate balance between the nuclear attraction of the particles and the repulsive forces of the Coulomb interaction, occurring at incredibly high densities. In this high-energy environment, the very fabric of matter takes on forms unimaginable in ordinary conditions, with these intricate shapes potentially having significant effects on the star's behavior. Yet, despite the exciting prospects these theories present, our current understanding of the physics governing neutron stars remains incomplete. The extreme conditions present within them simply cannot be replicated on Earth in laboratory settings. However, advancements in technology and observational techniques are providing valuable insights into this enigmatic state of matter. Observations of neutron star mergers, the detection of gravitational waves, and advancements in particle physics continue to yield groundbreaking discoveries, bringing us closer to understanding the fundamental forces at play. These findings not only promise to unlock new aspects of quantum mechanics, but could also revolutionize our understanding of general relativity. If they exist, quark stars could represent an even more exotic and extreme state of matter than neutron stars themselves. Both types of stars are born from the catastrophic collapse of a massive star during a supernova, but quark stars would push the limits of this process to an entirely new level. While neutron stars are predominantly composed of densely packed neutrons, quark stars would consist of quark matter, a phase in which neutrons themselves break down into quarks, the fundamental building blocks of matter. In a typical neutron star, gravity compresses matter to such an extreme density that electrons combine with protons to form neutrons. If the gravitational pressure continues unabated, it could overcome the strong nuclear force that usually confines quarks within neutrons and protons. This would trigger a phase transition, breaking down neutrons into a sea of up and down quarks, and possibly strange quarks, creating what is known as quark-gluon plasma. The conditions inside a quark star would be even more extreme than those of a neutron star. The density and pressure would be so immense that quark matter would no longer be confined to individual neutrons or protons. Instead, quarks would move freely within a sea of quark-gluon plasma, a state in which they are no longer bound by the strong nuclear force. If strange quarks are present, these stars are sometimes referred to as strange stars. The presence of strange quarks might make the star more stable, potentially resulting in even more unusual characteristics. Quark stars, unlike neutron stars, would not only differ in their internal composition, but also in their observable properties. Due to the distinctive nature of quark matter, quark stars might exhibit different thermal and radiation profiles, making them stand out in ways that we are only beginning to understand. While neutron stars are already one of the most extreme objects in the universe, quark stars would push these boundaries even further, offering a deeper glimpse into the fundamental nature of matter under the most extreme conditions imaginable. The transition from a neutron star to a quark star is a captivating phenomenon that could have profound implications for our understanding of the universe. While neutron stars are already known for their intense density and extreme gravitational fields, quark stars, if they exist, could take this to an entirely new level. One of the most exciting aspects of quark stars is the possibility that they could produce unique gravitational wave signatures or bursts of radiation, potentially offering a new way to detect and study them. However, despite their theoretical appeal, direct observational evidence of quark stars remains frustratingly elusive. The search for quark stars has led scientists on a multidisciplinary journey that spans theoretical modeling, astrophysical observations, and even experiments in particle physics. Advances in detectors, such as those used to measure gravitational waves, and observatories focused on high-energy cosmic phenomena are opening new doors in this search. These sophisticated instruments might one day provide the clues that confirm the existence of these extraordinary objects. Until then, quark stars remain a tantalizing possibility, an enigma that challenges our understanding of matter in the most extreme environments known to science. They push the boundaries of what we know about the universe, shedding light on the deepest mysteries of matter itself, under conditions that are truly beyond comprehension. Equally mysterious is the solar corona, the outermost layer of the sun's atmosphere, which presents a paradox for solar physicists. Despite the sun's surface, or photosphere, reaching a relatively moderate temperature of about 6,000 degrees Celsius, the corona can soar to temperatures ranging from 1 to 2 million degrees Celsius. This dramatic temperature difference is puzzling and raises important questions. How can the corona get so hot, and what processes keep it at such extreme temperatures? One of the key mechanisms believed to contribute to the heating of the solar corona is magnetic reconnection. The sun's magnetic field lines, generated by the dynamo effect deep within its interior, become twisted and tangled as they are affected by the sun's differential rotation and convective motions. When these twisted field lines reconfigure themselves, they release vast amounts of stored magnetic energy, which is converted into both heat and kinetic energy, heating the surrounding plasma. This process can manifest as solar flares, sudden, intense bursts of radiation that significantly contribute to the heating of the corona. But that's not the whole story. Another critical factor in the heating process is believed to involve waves and oscillations that are generated in the sun's interior. These waves, particularly Alfvén waves, travel along the sun's magnetic field lines, moving from the surface all the way into the corona. As they propagate, these waves carry energy that gets dissipated as they reach the corona, converting their energy into thermal energy. This continuous dissipation process is crucial for sustaining the high temperatures observed in the corona. Then there are nanoflares, smaller, more frequent versions of solar flares that add yet another layer of complexity to the puzzle. Proposed by renowned solar physicist Eugene Parker, nanoflares are tiny magnetic reconnection events that happen throughout the corona. While each nanoflare may release only a small amount of energy, their cumulative effect could play a significant role in the overall heating of the corona. The combined effects of these mechanisms, magnetic reconnection, Alfvén waves, and nanoflares, are believed to work together to maintain the solar corona's puzzling heat, and by studying them, scientists hope to unravel one of the sun's most perplexing mysteries. Magnetars, an even more enigmatic type of neutron star, offer yet another fascinating area of study. Magnetars are characterized by their incredibly powerful magnetic fields, which are the most intense known in the universe. To understand how magnetars generate such immense magnetic fields, we need to delve into the dynamics of stellar life cycles, focusing particularly on what happens during and after a supernova explosion. When a massive star runs out of nuclear fuel, it can no longer resist the immense gravitational pressure, and the star collapses, triggering a supernova. What remains behind is the core, which condenses into a neutron star. For magnetars, this collapse is coupled with rapid rotation and a powerful dynamo process that further intensifies the magnetic field. During the formation phase, if the neutron star spins rapidly on the order of milliseconds, its magnetic field is enhanced by a mechanism known as the alpha-omega dynamo. This process involves differential rotation and convection within the neutron star, which amplifies any pre-existing magnetic fields exponentially, producing magnetic fields that can reach up to 1,000 trillion Gauss or even more. This dynamo mechanism is short-lived, ceasing within a few seconds due to strong magnetic braking, But by that time, the magnetic field has already become deeply entrenched in the star. Another factor that contributes to the magnetic strength of magnetars is the flux freezing principle. As the core collapses, the magnetic flux is conserved, and as the star's radius shrinks, the magnetic field lines are compressed, further intensifying the magnetic field strength. This combination of processes, the rapid spin, the dynamo effect, and flux freezing, results in the ultra-strong magnetic fields observed in magnetars. These magnetic fields are not just theoretical. They are a tangible reality, one of the most extreme phenomena found anywhere in the universe, pushing the limits of what we know about the forces at work in the cosmos. The intense magnetic fields of magnetars are among the most powerful and mysterious forces in the universe. These fields can generate surface phenomena such as starquakes, where the magnetic stresses fracture the crust of a neutron star, releasing bursts of X-rays or gamma rays. These violent events, known as soft gamma repeaters, SGRs, or anomalous X-ray pulses, AXPs, are hallmark features of magnetars, highlighting the extreme and dynamic nature of their magnetic environments. The study of magnetars is an evolving and ever-expanding field. Observations made by X-ray and gamma-ray telescopes, combined with theoretical models and advanced simulations, continue to enhance our understanding of how these celestial giants generate and maintain their extraordinary magnetic fields. These insights provide more than just an understanding of magnetars. They enrich our broader comprehension of magnetic phenomena across the cosmos, shedding light on forces that govern the universe at its most extreme. One such example is the Crab Nebula, one of the most studied objects in the sky, which has confounded astronomers for years. The nebula's central pulsar, a rapidly spinning neutron star formed from a supernova explosion, is the source of sudden bursts of gamma-ray flares. Despite being only about 12 miles in diameter, this pulsar contains a mass greater than that of our Sun. Spinning 30 times per second, it generates intense magnetic fields that accelerate particles to nearly the speed of light. The origin of the gamma-ray flares lies in the dynamic environment created by the pulsar's rapid rotation. As the pulsar spins, it generates a powerful wind composed of charged particles that spiral along the pulsar's magnetic field lines. When these particles interact with the surrounding nebula material, they create shock waves in a region known as the pulsar wind nebula. Within this chaotic environment, magnetic field lines can reconnect, a process known as magnetic reconnection, releasing vast amounts of energy. This energy propels the particles to extreme velocities, causing them to emit gamma rays, the highest energy form of electromagnetic radiation. These gamma ray flares from the Crab Nebula are short-lived, lasting only a few days. Yet, in that brief period, they can be 1,000 times more intense than the total energy output of our Sun. Understanding these flares not only helps astronomers better understand the behavior of pulsars and their wind nebula, but also offers invaluable insights into fundamental processes that occur throughout the universe, making the Crab Nebula a cosmic laboratory for high-energy astrophysics. At the centers of most large galaxies, supermassive black holes, ranging in size from millions to billions of times the mass of our Sun, dominate the surrounding environment. Their gravitational influence profoundly affects the motion of stars and interstellar gas within their galaxies, but the impact of these cosmic giants extends far beyond mere gravity. Supermassive black holes shape their host galaxies in significant ways, primarily through the release of enormous amounts of energy as matter falls into them. This process occurs in the accretion disk, where gas and dust spiral inward, heated to extreme temperatures due to friction and gravitational forces. The material in the accretion disk emits intense radiation, which can either trigger or suppress star formation within the surrounding galaxy. When the black hole is actively feeding, it produces powerful jets of charged particles that shoot outward at nearly the speed of light, extending thousands of light years into space. These jets and outflows inject vast amounts of energy into the interstellar medium, creating shock waves and turbulence. This energy can compress gas, promoting the formation of new stars, or prevent the gas from cooling, thus inhibiting the formation of new stars. The regulation of star formation by supermassive black holes has profound implications for the growth and evolution of galaxies, contributing to phenomena such as the quenching of star formation in massive galaxies. Supermassive black holes not only shape their galaxies, they drive their very evolution. Understanding these complex and interconnected processes deepens our knowledge of the universe, revealing the hidden mechanisms behind the creation, destruction, and transformation of galaxies. These cosmic giants, through their extreme environments and powerful energy outputs, help us understand the dynamics of the universe at its most energetic and mysterious. The interactions between supermassive black holes and their host galaxies are far more significant than we once realized. In fact, they're believed to play a crucial role in regulating the size and growth of both the galaxies and the black holes themselves. Observations have shown a striking correlation between the mass of a black hole and the characteristics of the galaxy's central bulge, such as its velocity dispersion. This relationship hints at a profound coevolutionary process. As the black hole grows, so too does the galaxy, suggesting a dynamic interplay that could shape the very structure of the cosmos. Among the most fascinating theoretical concepts in astrophysics is strange matter. This exotic form of matter is thought to exist as quark-gluon plasma, a state where quarks, the fundamental building blocks of protons and neutrons, and gluons, the particles responsible for binding quarks together, are no longer confined within particles. Instead, these quarks exist in a fluid-like state, free to move independently. However, strange matter is even more unusual. Unlike ordinary matter, which contains only up and down quarks, strange matter includes strange quarks, giving it extraordinary properties. Strange stars, sometimes called quark stars, are hypothesized to be astrophysical objects made primarily of strange matter. They could form from the remnants of supernova explosions when a neutron star, the dense leftover core of such an event, collapses under its own immense gravity. In extreme conditions, this gravitational pressure might force neutrons to disintegrate into their constituent quarks, leading to the formation of a star made entirely of quark matter, particularly strange quarks. What makes strange stars so unique compared to neutron stars is their hypothesized stability. Strange matter is believed to be the most stable form of matter in the universe. This could mean that strange stars are not only denser, but also far more compact than neutron stars, with smooth, nearly frictionless surfaces rather than the hardened crusts characteristic of neutron stars. Such differences in structure might explain certain cosmic phenomena that cannot be attributed to known neutron stars or black holes, adding further intrigue to their potential existence. The detection of strange stars, or the confirmation of strange matter, remains one of the greatest challenges in modern astrophysics. Astronomical observatories that monitor gravitational waves and high-energy cosmic events will be pivotal in this search. If strange matter or strange stars are ever discovered, they could revolutionize our understanding of particle physics and provide groundbreaking insights into the extreme conditions that exist in the universe's densest objects. Another truly captivating celestial phenomenon is the existence of super puff planets, also known as cotton candy planets. These bizarre worlds are striking for their remarkably low densities. Despite being roughly the size of gas giants like Jupiter, they have masses so small that their densities resemble that of cotton candy. The formation and characteristics of these super puff planets challenge traditional theories of planet formation and spark intense scientific curiosity. One leading hypothesis suggests that these planets may possess extraordinarily thick atmospheres, primarily made up of hydrogen and helium, surrounding a relatively small core. During the early stages of their formation, these planets could have accreted large amounts of gas from the protoplanetary disk, causing their atmospheres to inflate. This could lead to a planet that is large in radius, but surprisingly low in mass. Another possibility is that superpuff planets have high-altitude layers of hazes or clouds made up of complex molecules or fine dust particles. These hazes or clouds could scatter and absorb sunlight, making the planet's atmosphere appear more expansive and less dense than it actually is. This visual distortion might explain their inflated appearances and the low densities that make them so unusual. Orbital dynamics could also be a contributing factor to the formation of these super puff planets. If they formed farther from their star and later migrated inward, they might retain their low-density characteristics, even after substantial migration. This process could explain why some super puff planets remain so puffed up despite being closer to their star. The mysteries surrounding strange matter and super puff planets are far from solved, but their study opens the door to a deeper understanding of the universe. From the extreme conditions within supermassive black holes and neutron stars to the bizarre properties of distant exoplanets, the cosmos constantly challenges our understanding, pushing the limits of what we know about matter, energy, and the fundamental forces that govern the universe. In the vastness of the universe, where mysteries unfold on a cosmic scale, super puff planets and colossal jets have emerged as two of the most extraordinary phenomena, each holding secrets that challenge our understanding of planetary and galactic formation. These super puff planets, a class of exoplanets unlike any other, captivate scientists with their almost ethereal characteristics. Their lower density and puffed up appearance defy conventional expectations of planetary structure. One intriguing aspect is the relatively mild radiation environments that exist in certain orbits, which may be key to preserving these planets' fluffy nature. In regions where radiation exposure is minimal, the atmosphere of these planets is less likely to be stripped away, allowing them to maintain their outer gas layers over extended periods. By studying these enigmatic worlds through advanced space telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, astronomers are on the brink of unlocking the formation and evolution of super puffs. What makes these planets even more compelling is their ability to force scientists to rethink traditional models of planetary development. Their discovery challenges what we once knew about planetary formation, urging the scientific community to explore new, innovative theories within exoplanetary science. In this way, super puffs serve as a reminder that the universe is not just full of unexplained wonders, but also an invitation to continually expand our boundaries of knowledge. Shifting focus to a different realm of cosmic phenomena, colossal jets emitted by active galactic nuclei, AGN, have captivated astronomers for decades. These magnificent jets can stretch across millions of light years, radiating with an energy so powerful that it outshines entire galaxies. But what causes such immense outflows of energy? The answer lies in the heart of these active galaxies, supermassive black holes. These colossal black holes reside at the center of AGNs, drawing in vast amounts of gas and dust from their surroundings. As this matter spirals inward, it forms an accretion disk, a swirling whirlpool of gas heated by friction and intense gravitational forces. This process creates the perfect environment for some of the most extreme phenomena in the universe. At the core of these jets is an intricate interplay of forces. As matter in the accretion disk moves toward the black hole, it generates powerful magnetic fields. These fields intertwine, twist, and coil due to the rotation of both the accretion disk and the spinning black hole itself. These intense magnetic forces funnel particles, including electrons and protons, to the poles of the black hole. Here, these particles are accelerated to near light speeds, forming the tight, focused columns of energy that we observe as jets. These high-speed particles emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The phenomenon of synchrotron radiation occurs when these fast-moving particles spiral along magnetic field lines, producing high-energy photons in the process. Additionally, inverse Compton scattering takes place when the accelerated particles transfer energy to low-energy photons, boosting them to higher energies. These interactions make the jets not only visible across different wavelengths, but also reveal the extreme physics at play near supermassive black holes. The impact of these jets extends beyond their immediate surroundings. As the particles and radiation emanate from the black hole, they inject energy and momentum into the intergalactic medium, influencing the dynamics of the surrounding gas. This process can either trigger or quench star formation in the host galaxy, while simultaneously shaping the galaxy's large-scale structure. Through the study of these colossal jets, astronomers gain a deeper understanding of the coevolution of supermassive black holes and their host galaxies, shedding light on the intricate relationship between the two. Both superpuff planets and colossal jets represent the frontiers of astronomical discovery. From the delicate balance that allows superpuffs to thrive to the awe-inspiring power of AGN jets, these phenomena force us to confront the mysteries of the universe. As we continue to explore, we open doors to new revelations that not only expand our scientific understanding, but also deepen our wonder at the vast and dynamic cosmos we inhabit. In the vast and mysterious realms of the cosmos, stars like R136A1 stand as true giants, pushing the boundaries of our understanding of stellar formation and evolution. Currently, the most massive star known, R136A1, weighs in at over 300 times the mass of our Sun. It resides in the dense and dazzling star cluster R136, located in the heart of the Tarantula Nebula, within the Large Magellanic Cloud. The very existence of such colossal stars prompts deep questions. How do they form, and what drives their immense mass? To uncover the secrets of R136A1's birth, we must explore the unique and dynamic environments where these stellar titans come into being. Stars like R136A1 are born in the most extreme and chaotic conditions in space, where clouds of gas and dust collapse under the force of gravity. This process, known as stellar accretion, is responsible for the formation of stars, and in the case of the most massive ones, it is a complex and explosive dance. In regions like the Tarantula Nebula, hydrogen and other elements gather together in dense pockets, creating the raw material needed for star formation. However, for a star to grow to the immense size of R136A1, it must be born in a particularly dense clump of gas and dust. The gravitational forces within this clump, coupled with an abundant supply of material, allow the protostar to accumulate mass at a rapid rate. During its formation, R136A1 likely experienced a phase of hyperacceleration, where the protostar rapidly drew in material from its surroundings. The intense gravitational pull of such a massive protostar would have attracted vast quantities of gas and dust, feeding its growth. In the dense environment of the R136 star cluster, interactions between nearby stars could further funnel material toward the growing star, propelling its mass to even greater heights. Under normal circumstances, radiation pressure, which opposes accretion in massive stars, would act as a barrier. However, in the case of R136A1, the sheer gravitational pull of the star would have temporarily overcome this resistance, allowing the star to continue growing at an extraordinary rate. Once formed, stars like R136A1 burn through their nuclear fuel at an astonishing pace. The pressures and temperatures at their cores are so intense that their internal fusion reactions occur at speeds far beyond those of smaller stars. The energy produced by these reactions powers the star's brilliance, producing vast amounts of radiation and stellar winds. These powerful forces can dramatically affect the surrounding environment, blowing away any remaining gas and dust and possibly limiting further growth. The interplay between accretion and feedback mechanisms, the forces that push matter away, is a delicate balance that ultimately determines the final mass and lifespan of these stellar giants. Stars like R136A1 offer astronomers a window into the most extreme corners of stellar physics. They are natural laboratories, allowing scientists to explore the fundamental processes that govern star formation, evolution, and eventual death. Understanding how these massive stars live and die not only enhances our knowledge of their role in the universe, but also provides insights into the greater cosmic system, shedding light on the vast forces that shape the universe we observe. Moving beyond individual stars, we encounter the cosmic web, an intricate and colossal network that forms the backbone of the universe itself. This web is composed of interconnected filaments of dark matter, gas, and galaxies spanning vast stretches of space. The structure of the cosmic web dictates the large-scale distribution of matter, influencing how galaxies are organized and how they evolve. To understand the cosmic web is to gain profound insights into the origins of the universe, as it emerged from the slight density variations present in the early universe, shortly after the Big Bang. Dark matter, an invisible yet dominant component of the universe, played a crucial role in shaping the cosmic web. Its gravitational pull served as a scaffolding, drawing in ordinary matter and forming the observable structures we see today. Galaxies and galaxy clusters reside at the intersections of these filaments, regions known as nodes, where the convergence of matter is greatest. These nodes are often home to vast galaxy clusters, forming some of the largest structures in the universe. Meanwhile, the filaments themselves, though less dense, serve as pathways along which galaxies travel, interact, and sometimes collide. The study of the cosmic web has provided valuable insights into the dynamics of galaxy formation and the evolution of galaxy clusters. Telescopic observations and advanced simulations reveal fascinating details about how matter flows through the filaments, tracing the movements of galaxies and shedding light on the processes that drive the formation of stars within galaxies. These filaments not only serve as highways for galaxies, but also act as reservoirs of material that fuel the birth of new stars. Understanding the cosmic web helps astronomers decipher the complex interactions between dark matter, gravity, and visible matter, allowing them to explore the fundamental forces that shape the universe itself. Within the cosmic web, galaxies are not distributed randomly. Instead, they follow a periodic pattern that can be traced back to the early universe. This phenomenon, known as baryon acoustic oscillations, BAOs, provides a crucial tool for measuring the large-scale structure of the universe. The sound waves created by the interplay between gravity and pressure in the early universe imprinted a subtle yet measurable pattern in the distribution of galaxies. These sound waves, which propagated outward from regions of higher density, left behind a signature scale, roughly 500 million light-years, that can be observed in the arrangement of galaxies today. Astronomers use large-scale galaxy surveys to detect these periodic patterns, mapping the positions of millions of galaxies. By studying these patterns, scientists can gain valuable insights into the history of the universe's expansion and the mysterious nature of dark energy. Baryon acoustic oscillations act as a cosmic yardstick, allowing astronomers to measure distances within the universe with unparalleled accuracy. This enables them to investigate the rate of expansion and gain a deeper understanding of the forces driving it. The periodicity of galaxy distributions, imprinted by the primordial sound waves of the early universe, offers a powerful link between theoretical models and observational data. Baryon acoustic oscillations confirm many fundamental aspects of cosmological models, providing crucial evidence for the accuracy of our understanding of the universe's birth and evolution. These patterns, etched into the very fabric of space itself, offer a window into the profound regularities that govern the cosmos. And by analyzing them, we move ever closer to comprehending the grand design of everything that exists. One particularly intriguing phenomenon related to galaxy surveys is the fingers of God effect. This occurs when galaxies within clusters experience peculiar velocities that distort the way we perceive their positions in space. When observing large-scale maps of the universe, this effect creates elongated finger-like extensions of galaxy distributions that point toward the observer, distorting the true spatial positions of the galaxies. This phenomenon arises from the peculiar motion of galaxies as they move within clusters, which affects how we measure their distances. Understanding this effect requires a grasp of how astronomers measure the distances to galaxies. Using redshift, the stretching of light due to the expansion of the universe, scientists can estimate the distances to galaxies by analyzing the wavelength of light emitted from them. The redshift reveals how much the light has been stretched, allowing astronomers to calculate the galaxy's positions and create an accurate three-dimensional map of the universe. By studying these intricate cosmic structures, we continue to uncover the vast and mysterious forces that shape our universe, from the birth of stars to the largest galactic clusters. However, galaxies are not passive objects simply drifting through the universe. They exhibit individual motions relative to their local environments, known as peculiar velocities. These velocities are not part of the uniform expansion of the universe. Instead, they arise from interactions between galaxies and the gravitational influence of nearby objects, especially within galaxy clusters. As galaxies move, their velocities gain components above and beyond the cosmic expansion, complicating the measurement of redshifts. This additional motion distorts the apparent shift in light as seen from Earth. When astronomers plot galaxies along the line of sight, peculiar velocities cause a distortion in their redshift measurements. In regions with dense galaxy clusters, these peculiar motions are especially noticeable. Galaxies in clusters can move toward or away from us due to mutual gravitational interactions, which stretches the redshift data. This distortion is often referred to as the fingers of God effect, where the galaxies appear artificially elongated along the line of sight, despite being much closer to each other in space. The three-dimensional shape of the cluster, which is otherwise compact, gets smeared into these long, finger-like structures. This phenomenon underscores the complexity of interpreting redshift data. It highlights the need to account for both the cosmic expansion and the individual motions of galaxies. Correcting for these peculiar velocities requires sophisticated models and simulations that incorporate the dynamics of galaxy clusters. By doing so, astronomers can refine their maps of the universe, providing a more accurate understanding of the forces that shape cosmic structures and the universe's evolution. In contrast to the dense clusters of galaxies, there exist vast regions of space called cosmic voids and supervoids, enormous, empty spaces in the universe where very few galaxies exist. These voids can range from tens to hundreds of millions of light years across, forming a stark contrast to the packed clusters of galaxies and the intricate cosmic web that spans the universe. Understanding the formation and significance of these voids is essential for gaining insight into the large-scale structure of the universe and the forces that govern it. Cosmic voids are a product of the universe's early stages. Right after the Big Bang, the universe was nearly uniform, with only slight fluctuations in density. Over time, gravity amplified these fluctuations, causing matter to clump together in some areas while leaving others increasingly empty. These underdense regions, unable to attract enough material to collapse into the dense structures that form galaxies, became the voids we see today. As matter aggregated into sheets, filaments, and nodes, forming the cosmic web, the voids grew, expanding as the denser regions continued to collapse. The process was self-reinforcing. The more a void expanded, the more galaxies and gas were pushed out, increasing its emptiness. Although voids are not completely devoid of matter, containing dark matter, for example, and sometimes even sparse populations of galaxies, they are significantly less dense than the surrounding cosmic web. Their emptiness offers valuable scientific insight. The rapid expansion of voids provides a natural laboratory for studying dark energy, the mysterious force responsible for the accelerated expansion of the universe. Since voids expand more quickly than denser regions, they offer astronomers a unique opportunity to observe how dark energy influences the universe on a grand scale, providing critical tests for cosmological models. Furthermore, cosmic voids play an important role in understanding galaxy formation and evolution. By comparing galaxies within voids to those in more crowded regions, astronomers can explore how different environments influence the properties of galaxies. For example, galaxies in voids tend to have different star formation rates, morphologies, and chemical compositions than their counterparts in denser areas. This comparative analysis enriches our understanding of the universal processes that drive galaxy growth and transformation, shedding light on the intricate forces that shape the cosmos. In sum, while galaxy clusters with their peculiar velocities present challenges for interpreting redshift data, cosmic voids offer a unique perspective on the universe's structure and the forces shaping it. These vast emptinesses are not just blank spaces. They are laboratories for studying the universe's expansion, dark energy, and the evolution of galaxies, providing critical insights into the workings of the cosmos on the largest scales. In the vast expanse of the cosmos, voids, these seemingly empty regions play an essential role in shaping the structure of the universe. Far from being just empty spaces, they serve as critical elements in the cosmic web, influencing the distribution and movement of matter across vast distances. These cosmic voids are interconnected with filaments and clusters, forming an intricate network that defines the large-scale architecture of the universe. By studying the spatial and dynamic relationships between these structures, scientists can build a more comprehensive understanding of how forces like gravity and dark matter interact, sculpting the universe as we observe it. In this context, voids are not mere empty spaces, but active participants in the cosmic drama, contributing to the flow of matter and energy. They offer clues about the origins and evolution of galaxies, dark matter, and the very structure of the universe itself. It is through the analysis of these voids, alongside the vast cosmic filaments and dense galaxy clusters, that we can start to unravel the secrets of the universe's formation. These connections between voids, filaments, and clusters allow scientists to test various cosmological theories and offer deeper insights into the cosmic forces that have shaped everything from the smallest particles to the largest structures in the universe. Among the most intriguing hypotheses in modern cosmology are the cosmic strings, hypothetical one-dimensional topological defects that may have formed during the early universe. These strings, if they exist, are thought to have emerged during a period of symmetry-breaking phase transitions, which took place mere moments after the Big Bang. The conditions of the early universe were incredibly hot and dense, where the fundamental forces of nature, gravitational, electromagnetic, and the nuclear forces, were unified. As the universe cooled and expanded, these forces began to separate through a series of phase transitions, much like water freezing into ice. In these transitions, imperfections could have arisen in the fabric of space-time, with cosmic strings being one of the potential outcomes. Cosmic strings would be incredibly thin, far thinner than a proton, yet they could possess an immense mass stretching across vast distances. These strings would have an extraordinary gravitational pull, capable of distorting space-time around them. If these cosmic strings exist, their implications for our understanding of the universe are profound. They could serve as the gravitational seeds for the formation of large-scale structures like galaxies and galaxy clusters. Their immense mass per unit length would cause them to act as gravitational attractors, drawing matter toward them and potentially influencing the formation of galaxies across the universe. As cosmic strings move and interact, they might even generate gravitational waves, ripples in the fabric of space-time, which could be detected by observatories such as the Laser Interferometer Gravitational Wave Observatory, LIGO, or the Laser Interferometer Space Antenna, LISA. While cosmic strings have not yet been directly detected, astronomers continue their search. One method involves looking for gravitational lensing effects, where the enormous mass of a cosmic string bends light from background objects, producing unique distortions in the light's path. Additionally, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, could hold traces of cosmic strings, leaving specific patterns that researchers are closely scrutinizing. If these strings are confirmed, they would offer an extraordinary window into the early universe, shedding light on the unification of the fundamental forces and providing crucial insights into the conditions that existed just after the Big Bang. Another monumental feature of the universe's structure is the galactic filament, colossal threads of dark matter, gas, and galaxies stretching across hundreds of millions of light years. These massive filaments are not merely random structures, but essential components of the cosmic web, connecting galaxy clusters and shaping the growth of the universe over cosmic timescales. They form the vast scaffolding of the universe, providing the channels through which matter flows and organizes itself into the galaxies, stars, and clusters that we observe today. The formation of galactic filaments can be traced back to the early universe. In the moments following the Big Bang, the universe was nearly uniform, with only slight variations in density. However, tiny quantum fluctuations, minuscule differences in density, gradually amplified over time through the effects of gravity. These fluctuations acted as seeds, causing matter to clump together in some areas while other regions remained relatively empty. As the universe expanded and cooled, the clumps of matter began to grow, eventually forming the enormous galactic filaments that we see today. These filaments act as highways for the flow of matter, guiding galaxies and clusters of galaxies along their vast lengths. The study of these galactic filaments offers important clues about the forces driving the universe's evolution. They help astronomers understand how dark matter influences the formation of large-scale structures and the complex interactions between gravity, matter, and dark energy. By examining the intricate network of filaments, voids, and clusters, scientists can piece together a detailed picture of how the universe grew from a nearly uniform state to the rich, complex structure we observe today. As we delve deeper into the mysteries of cosmic voids, cosmic strings, and galactic filaments, it becomes clear that the universe is far more than a simple collection of stars and galaxies. It is a dynamic, interconnected system, shaped by forces and phenomena that we are only beginning to comprehend. Each discovery, each new piece of the cosmic puzzle, brings us closer to understanding the very fabric of reality itself. The quest to unravel these cosmic mysteries continues, promising new insights and revelations about the nature of our universe. In this vast and awe-inspiring universe, an intricate cosmic structure is unfolding, one that began with subtle fluctuations after the Big Bang. These fluctuations in density, as the universe expanded and cooled, set the stage for the formation of the cosmic web, a massive filamentary structure. Central to this phenomenon was dark matter, an invisible force that does not interact with light but exerts an undeniable gravitational pull. This force was instrumental in shaping the filaments of the cosmic web. Dark matter clumped together, forming a scaffold of immense scale. Around this framework, ordinary matter composed of atoms gathered in the form of gas and dust, drawn to the gravitational influence of dark matter. As this cosmic scaffolding took shape, gas and dust streamed along these paths, creating the vast filaments that would later serve as highways for the movement of matter. These filaments act like the veins of the universe, channeling material towards denser regions where galaxy clusters form. Within these cosmic threads, galaxies and clusters interact, merge, and evolve under the immense gravitational forces at play. The flow of gas through these filaments not only fuels the growth of galaxies, but also provides the essential ingredients for the formation of stars, leading to a dynamic and constantly changing cosmic landscape. Galactic filaments are not just passive structures. They are the very conduits for the universe's evolution. By observing these filaments, astronomers can trace the large-scale structure of the universe. Advanced techniques and powerful telescopes, such as those capable of mapping the distribution of galaxies and detecting slight distortions in the cosmic microwave background, allow scientists to peer deep into the heart of the cosmos. This observational data, combined with sophisticated computer simulations, helps us understand the universe's evolution from the Big Bang to the present, offering a virtual laboratory to study how these filaments form, grow, and evolve. Understanding these cosmic filaments is crucial for unlocking the mysteries of the universe. They reveal not only the interconnected nature of cosmic matter, but also the underlying forces, dark matter, gravity, and cosmic energy, that shape the large-scale structure of everything we see. The study of these filaments also provides valuable insights into galaxy formation and growth, offering clues about how the building blocks of galaxies and stars come together over billions of years. By studying these vast cosmic threads, we gain a deeper understanding of the universe's grand design and the complex forces that govern its development. One of the most extraordinary large-scale structures discovered within this cosmic web is the Sloan Great Wall, also known as the Great Wall of SLO. Spanning an immense 1.37 billion light-years, this structure is composed of countless galaxy clusters and superclusters arranged in a ring-like formation. To comprehend how such a colossal structure came into being, we must look to the early universe. After the Big Bang, minute variations in the density of matter and energy existed throughout space. These fluctuations were amplified by gravity over billions of years, leading to the formation of massive filaments, walls, and voids, fundamentally shaping the cosmic web. Gravity, acting relentlessly over time, caused matter to clump together along these filaments, creating dense regions that would become superclusters of galaxies. The Sloan Great Wall is essentially a massive collection of these superclusters, all interconnected by filaments of galaxies and dark matter. While its appearance might suggest a perfect ring, this is a projection effect due to our vantage point in the universe. When mapped in 3 dimensions, the structure reveals a more complex and interconnected pattern, resembling an elaborate network of cosmic highways. The discovery of the Sloan Great Wall was made possible through the groundbreaking Sloan Digital Sky Survey, SDSS, a massive project that mapped millions of galaxies across vast stretches of space. This survey provided unprecedented insight into the universe's structure, revealing enormous cosmic formations like the Sloan Great Wall. The data gathered by SDSS allowed astronomers to identify and measure the vast size of such structures, confirming predictions made by cosmological models about how galaxies are distributed in the universe. The significance of the Sloan Great Wall lies not only in its enormous size, but also in what it reveals about the universe's composition. Studying these colossal structures allows scientists to refine their understanding of cosmic evolution, including the role of dark matter and dark energy in shaping the universe. The Sloan Great Wall, along with other large-scale structures, acts as a natural laboratory, helping us understand the formation and evolution of galaxies within the broader cosmic web. In addition to the cosmic web and the Sloan Great Wall, astronomers have been captivated by a mysterious phenomenon involving quasars, intensely luminous and energetic active galactic nuclei powered by supermassive black holes. Observations of distant quasars suggest that their spin axes are surprisingly aligned across vast cosmic distances, which has puzzled scientists and sparked numerous theories. To explain this alignment, one hypothesis involves the influence of large-scale cosmic structures. Quasars are typically located at the intersections of the cosmic filaments, where matter has collapsed to form galaxies and clusters. The alignment of quasar spin axes might, therefore, be a consequence of the orientation of these filaments. If the spin axes of galaxies and their central quasars are aligned with the cosmic filaments, the alignment could extend over billions of light years. Another theory suggests that primordial magnetic fields or cosmic torsion from the early universe might have imparted a specific orientation to the matter that formed galaxies and quasars. This initial condition could have influenced how galaxies and their central black holes formed, creating a coherent alignment that persists today. These hypotheses suggest that the alignment of quasars might be a vestige of the universe's early conditions, preserved as the cosmos expanded. In conclusion, the study of cosmic filaments, structures like the Sloan Great Wall, and the alignment of distant quasars provides an incredible window into the universe's past, present, and future. These phenomena not only reveal the underlying forces that shape the cosmos, but also offer critical clues about the fundamental processes driving galaxy formation, the influence of dark matter, and the complex interconnections that make up the grand tapestry of the universe. The quest to understand these cosmic structures is not just an exploration of space. It is a journey into the very heart of the universe's origins and evolution. In the vast expanse of the cosmos, there are anomalies that continue to challenge our understanding of the universe. One such mystery is the potential role of observational biases or selection effects in the observed alignments of distant cosmic objects. These alignments might be shaped not by inherent cosmic phenomena, but by the limitations of our current survey techniques and instruments. As astronomical technology advances and our surveys grow in scope and precision, these alignments will be better understood and their statistical significance will be refined. The ongoing and future observations, especially from cutting-edge telescopes like the James Webb Space Telescope, are expected to provide deeper insights into quasar alignments. With more comprehensive data from these advanced instruments, we may be able to determine whether these cosmic alignments are rooted in fundamental cosmic processes or if they are merely an artifact of observational limitations. Regardless of the outcome, this exploration will underscore the complexity and interconnectedness of cosmic evolution, propelling humanity's relentless pursuit to unlock the secrets of the universe. One fascinating feature that has captured the attention of cosmologists is the cold spot in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Discovered by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite, this cold spot represents a region of space where the temperature of the CMB is significantly lower than the average temperature across the universe. Its existence has sparked intense debate, as its unusual characteristics could challenge our current understanding of cosmology, potentially hinting at new and exotic physics. Several hypotheses have been put forward to explain the cold spot. One possibility is that it is simply a statistical fluke, a rare yet plausible deviation in the random fluctuations of the CMB. While quantum fluctuations in the early universe are expected to produce minor variations in temperature, the size and scope of the cold spot make it unlikely to be a mere accident of chance. Another theory involves the integrated Sachs-Wolf effect, which suggests that as CMB photons travel through large cosmic structures, such as supervoids, vast underdense regions of space, they lose energy and are redshifted, thus cooling the observed temperature. Some researchers speculate that the cold spot could align with an exceptionally large supervoid, offering a potential explanation for this strange anomaly. Beyond these more conventional theories, there are even more speculative ideas, such as the possibility that the cold spot could be a sign of cosmic bubble collisions or evidence of interactions with parallel universes, a concept rooted in multiverse theories. While these ideas are currently far-reaching and lack the empirical evidence to support them, they remain subjects of active investigation and could lead to groundbreaking discoveries. There's also the possibility that the cold spot could be an artifact of unknown systematic errors in our observational techniques or instrumentation. As astronomers refine their methods and technologies, they continue to scrutinize the data, ensuring that the cold spot reflects a genuine physical phenomenon. The significance of the cold spot extends far beyond the study of the CMB. It challenges established cosmological models and encourages researchers to explore new data and refine their observational techniques. Understanding the true cause of the cold spot could provide profound insights into the early universe, the large-scale structure of the cosmos, and even the fundamental laws of physics. As ongoing research delves deeper into the cold spot's origin, it remains a focal point in the quest to unravel the deepest mysteries of the universe. Equally fascinating is the Boots Void, a vast and enigmatic feature of the universe discovered in 1981. This nearly spherical region, located in the constellation Boötis, spans a staggering 330 million light-years in diameter. To put this into perspective, if the Milky Way were positioned at the center of this void, only a handful of galaxies would populate its immense expanse. Such voids are not uncommon in the cosmos, as they are thought to be a natural consequence of the gravitational interactions that shaped the universe's large-scale structure. In the early universe, regions with slightly more mass than others attracted even more matter, eventually forming dense clusters of galaxies. Meanwhile, areas with less matter became underdense, leaving vast empty spaces that we now recognize as cosmic voids. What sets the Boots Void apart is its sheer size and the striking scarcity of galaxies within it. Initially, astronomers were puzzled by the existence of such a large empty region, but subsequent observations have confirmed that the universe does indeed contain these vast cosmic deserts. The Boots Void stands as a reminder of the universe's complexity and its capacity for surprising structures. The void's existence has challenged our understanding of cosmic evolution, prompting new questions about the forces that govern the formation and distribution of matter. What other hidden features might remain to be discovered in the far reaches of space? Each new finding brings us one step closer to understanding the intricate web of the universe. Perhaps the most profound mystery in modern cosmology is the elusive nature of dark matter. While it does not emit, absorb, or reflect light, its presence is inferred from its gravitational effects on galaxies and galaxy clusters. The search for the particles that constitute dark matter has led scientists to explore a variety of candidates, each offering a unique set of possibilities. One leading candidate is WIMPs, weakly interacting massive particles. These theoretical particles interact with regular matter only through gravity and the weak nuclear force, making them difficult to detect directly. However, their potential mass could account for a significant portion of the total mass in galaxies, helping to explain their observed gravitational behavior. Another intriguing possibility is axions, ultralight particles that were originally proposed to resolve a problem in particle physics known as the strong charge parity problem. If axions exist, they would have an incredibly low mass and would interact only weakly with light. Some researchers are working on methods to detect axions by looking for their conversion into photons when subjected to strong magnetic fields. Additionally, sterile neutrinos, a type of neutrino that interacts only through gravity, have also been proposed as a dark matter candidate, though their detection remains elusive. Each of these candidates offers tantalizing clues, and the search for dark matter particles continues to be one of the most important quests in modern science. As our observational tools and techniques improve, and as we gain new insights from groundbreaking discoveries, our understanding of these cosmic phenomena will continue to evolve. With each new piece of the cosmic puzzle, we are getting closer to unraveling the mysteries of the universe and the fundamental forces that shape its existence. The Boots void, the cold spot in the CMB, dark matter, and quasar alignments all serve as reminders of the complexity of the universe and our unyielding pursuit to understand it at the deepest levels. The story of the cosmos is still being written, and the best chapters are yet to come. Sterile neutrinos present an exciting and enigmatic possibility in the search for dark matter. Unlike their more familiar counterparts, the regular neutrinos, sterile neutrinos do not interact through the weak nuclear force. Their theoretical existence arises from extensions to the standard model of particle physics, suggesting that they might be part of a broader, undiscovered framework. If these sterile neutrinos exist, they could decay into ordinary neutrinos and photons, potentially producing signals detectable through X-ray observations. However, detecting sterile neutrinos presents its own set of challenges, demanding advanced experiments and observatories, both on Earth and in space. Across the globe, scientists are engaged in the complex task of capturing these elusive particles, whether they be WIMPs, axions, or sterile neutrinos. The resolution of the dark matter mystery would not only provide a breakthrough in understanding one of the universe's most perplexing phenomena, but would also dramatically transform our view of the cosmos. This quest, tied to particles that could be all around visible to current instruments, might reshape everything from astrophysics to quantum mechanics. However, while dark matter presents a deep, captivating puzzle, dark energy is even more profound. Its influence is quietly driving the accelerated expansion of the universe, a phenomenon first identified in the late 20th century. Dark energy works against the gravitational pull of matter, causing galaxies to move apart at an increasing rate. The discovery of this accelerating expansion came from the study of distant supernovae, which showed that galaxies were not only moving away from each other, but doing so at a faster pace over time. To understand how dark energy fuels this expansion, we must explore the concept of the cosmological constant. Initially introduced by Albert Einstein, the cosmological constant was originally intended to keep the universe static, balancing gravity's pull. Yet after the universe's expansion was discovered, Einstein discarded it, calling it his biggest blunder. Ironically, the cosmological constant resurfaced as a key feature of dark energy, where it was reinterpreted as a repulsive force that exists uniformly throughout space. This force contributes to the universe's accelerating expansion. Dark energy is thought to account for about 70% of the universe's total energy content. Unlike matter and radiation, which become more diluted as the universe expands, the density of dark energy remains constant. This property ensures that as the universe grows, the influence of dark energy becomes more dominant relative to other components, thereby accelerating cosmic expansion over time. Yet, despite this understanding, dark energy's nature remains largely mysterious. As scientists delve further into the properties of dark energy, alternative theories continue to emerge. Some suggest that dark energy might simply be a characteristic of space itself, an inherent feature of the fabric of the universe. Others propose that it could be a dynamic field, evolving and changing as the universe unfolds. Regardless of the model, one thing is clear. Unlocking the nature of dark energy is essential to understanding not only the fate of the universe, but also the very forces that govern its structure and expansion. One particularly intriguing possibility is that dark energy could be linked to the vacuum energy of space, an idea rooted in quantum mechanics. In this view, even the empty vacuum of space is not truly devoid of activity. At the smallest scales, the fabric of spacetime is filled with quantum fluctuations, where virtual particles briefly appear and disappear. These fluctuations result in a form of energy that permeates all of space. This vacuum energy could exert a uniform, repulsive pressure, explaining the acceleration and the expansion of the universe. In fact, the cosmological constant can be viewed as a mathematical representation of vacuum energy. It contributes to the ever-accelerating expansion we observe today. However, calculating vacuum energy is far from straightforward. Theoretical estimates for the energy density of these quantum fluctuations have yielded results that are vastly higher than the observed value of dark energy. This discrepancy, known as the cosmological constant problem, remains one of the most significant unresolved issues in theoretical physics. Despite the challenges, the idea that vacuum energy and dark energy are related remains compelling. Both concepts suggest that the fabric of space itself holds the key to some of the universe's most fundamental mysteries. As our understanding of dark energy deepens, we may be closer to solving the riddle of how the universe came to be and where it is headed. Through ongoing research and innovation, these once theoretical ideas are beginning to reveal their true importance in the grand cosmic story. In the realm of modern physics, the enigma of dark energy has captivated the minds of scientists for decades. While its existence is evident through its profound influence on the universe's accelerated expansion, what exactly dark energy is remains a mystery. Some theorists suggest that dark energy might not be a separate entity, but rather an observable effect of deeper quantum mechanical processes yet to be fully understood. Others speculate that modifications to the laws of gravity or the introduction of new fields could provide a more profound explanation. Vacuum energy, for instance, has emerged as a promising clue, hinting that what we perceive as dark energy could be an intrinsic property of space itself. Ultimately, solving this riddle will require a synthesis of experimental observations and groundbreaking advances in theoretical physics, potentially rewriting our most fundamental concepts of the universe. At the same time, the search for dark matter, a different but equally elusive component of the cosmos, continues to challenge scientists. While we cannot see dark matter directly, its gravitational pull on visible matter suggests its presence, shaping the formation and behavior of galaxies. To detect this invisible substance, scientists employ a range of cutting-edge techniques. One prominent method relies on ultra-sensitive detectors, which are often placed deep underground. These locations, such as abandoned mines or mountain caves, serve as a shield, blocking out cosmic rays and other background radiation that could obscure the faint signals dark matter might produce. Among the most intriguing candidates for dark matter are WIMPs, weakly interacting massive particles. Detecting WIMPs involves placing noble gases like xenon or argon inside specially designed detectors. When these particles pass through, they may collide with atomic nuclei, causing a flash of light or a tiny ionization signal. These interactions are exceedingly rare, meaning that the detectors must be incredibly sensitive to distinguish real signals from the noise created by background radiation. With precision and patience, researchers continue to monitor for these fleeting events. In addition to WIMP detection, some experiments use cryogenic detectors, which operate at temperatures close to absolute zero. These detectors utilize materials that are highly sensitive to the slightest vibrations caused by dark matter interactions. When a dark matter particle strikes an atomic lattice, it can cause minute temperature changes or phonons, quantized sound waves that scientists can detect. Again, this technique requires shielding from environmental noise and precise calibration to ensure that the readings are accurate. The challenge is immense, but the potential reward, a breakthrough in understanding dark matter, drives scientists to persist. In recent years, researchers have turned to quantum sensors and advanced materials that could provide entirely new methods of detecting dark matter. One such innovative approach explores the use of materials with low-energy excitations, known as magnons. These materials might interact with dark matter in ways that traditional techniques cannot. Whether through direct particle collisions or by leveraging the power of quantum mechanics, scientists are constantly refining their methods, hoping to catch even the slightest whisper of dark matter. Dark matter's influence on the universe is far-reaching, shaping the very structure of galaxies. While invisible to the naked eye, dark matter's gravitational force is responsible for the cosmic scaffolding that holds galaxies together. In the early universe, long before stars and galaxies formed, dark matter clumped together under the force of gravity, creating the initial seeds for galaxy formation. This process occurred long before ordinary matter had cooled enough to coalesce into stars and galaxies. In the aftermath of the Big Bang, the universe was a hot, dense plasma with regular matter existing in an ionized state. This intense heat prevented the clumping of ordinary matter, but dark matter, unaffected by radiation pressure, could begin to form clumps, eventually giving rise to the cosmic structures we observe today. As we continue to study dark matter and dark energy, we edge ever closer to unlocking the secrets of the universe's most fundamental forces. With every experiment and new theoretical insight, we learn more about the nature of these hidden components. And though the journey is fraught with challenges, the pursuit of knowledge in this realm could one day lead to a profound transformation in our understanding of reality itself. However, dark matter, largely unaffected by electromagnetic forces, began to clump together under its own gravity. These clumps formed what we now refer to as dark matter halos, vast, invisible structures that exerted gravitational influence over the surrounding space. As the universe expanded and cooled, ordinary matter began to fall into these dark matter halos, creating dense regions that cooled over time, eventually forming stars. These stars then gathered into galaxies. Without the scaffolding of dark matter, this process would have been far slower and less efficient, potentially leading to a universe with entirely different structures, or even no structures at all. In the present day, dark matter remains an essential component of galaxies, continuing to shape their structure and behavior. It forms a vast invisible halo that envelops galaxies, stabilizing them and influencing their rotation. Observations have revealed a fascinating phenomenon. Stars in the outer regions of galaxies rotate faster than expected, a speed that cannot be explained by the gravitational influence of visible matter alone. This discrepancy is resolved by the gravitational pull of dark matter, which outweighs visible matter by a significant margin. Thus, dark matter is not just a relic of the past. It continues to be a fundamental force within galaxies, ensuring their stability and influencing the behavior of the stars within them. The role of dark matter is not limited to the past or the present. Its enduring influence helps us understand some of the most profound mysteries of the universe, particularly the nature of dark energy. Dark energy, a force that drives the accelerated expansion of the universe, holds profound implications for its ultimate fate. If we can understand how dark energy behaves over time, we may be able to predict what will happen to the cosmos in the far future. The potential outcomes depend heavily on whether dark energy remains constant, increases, or diminishes. Each scenario would lead to a vastly different future for the universe. If dark energy remains constant, as current observations suggest, it would imply that the universe will continue to expand at an ever-accelerating rate. This scenario is often referred to as the Big Freeze or heat death, where galaxies drift farther and farther apart, stars eventually burn out, and the universe becomes an empty, cold, and desolate expanse. In such a universe, the vast distances between objects would make it harder for new stars and galaxies to form, leading to a final state of cosmic isolation. However, there is also the possibility that dark energy's properties could change over time. If dark energy increases, the expansion of the universe could accelerate dramatically, eventually overcoming the gravitational and atomic forces that hold everything together. This event, known as the Big Rip, would result in the disintegration of galaxies, stars, planets, and even atoms themselves. The fabric of the universe would stretch to the point where everything would be torn apart at the most fundamental level. Alternatively, if dark energy were to weaken or dissipate, the universe's expansion might eventually come to a halt. The gravitational pull of galaxies and other cosmic objects could reverse the expansion, pulling everything back together in a dramatic collapse known as the Big Crunch. In this scenario, the universe would shrink back to a singularity, potentially leading to the creation of a new universe. Some theories even suggest a cyclical model, where the universe experiences repeated cycles of expansion and contraction, leading to successive Big Bangs and crunches. The true nature of dark energy remains one of the most pressing questions in cosmology. Scientists are working tirelessly to uncover its secrets, using powerful telescopes, studying cosmic microwave background radiation, and observing phenomena like supernovae and the large-scale structure of the universe. These efforts aim to shed light on the behavior of dark energy and, ultimately, on the future of the cosmos itself. One of the key pieces of evidence that led to the discovery of dark matter came from the study of galaxy rotation curves. These curves plot the orbital velocity of stars and gas in a galaxy, showing how the speed of these objects changes with their distance from the galaxy's center. When astronomers first mapped these curves, they expected the speeds to decrease as they moved farther from the center, much like how planets in our solar system slow down the further they are from the sun. To their surprise, they found that the outer regions of galaxies rotate at nearly the same speed as the inner regions, defying expectations based on visible matter alone. This unexpected result was one of the earliest and most compelling pieces of evidence for the existence of dark matter. According to Newtonian mechanics, the visible mass of a galaxy, concentrated in stars and gas, should dominate its gravitational behavior. Therefore, objects located farther from the galactic center should rotate more slowly. But this was not the case. Instead, the faster rotation in the outer regions of galaxies suggested that there was an additional unseen mass exerting gravitational influence, a mass we now attribute to dark matter. The discovery of dark matter reshaped our understanding of the universe, revealing that most of the mass in galaxies is invisible, yet it plays a crucial role in the formation and stability of galaxies throughout the cosmos. However, these flat rotation curves suggest something far more mysterious. The gravitational pull in these regions, even where visible matter is sparse, remains unexpectedly strong. This phenomenon points to the presence of an unseen mass, what we call dark matter. It is not just a theoretical idea, it's an essential factor that may help us understand the fundamental structure of our universe. Dark matter, invisible yet impactful, forms a halo around galaxies. This halo extends far beyond the visible edge of galaxies, subtly interacting with the visible matter through gravitational forces. By accounting for this invisible mass, scientists have been able to explain these peculiar rotation curves without resorting to alternative hypotheses. Without dark matter, there is simply no way to reconcile the high velocities we observe at the outer edges of galaxies with the amount of luminous mass that we can detect. As studies continue across countless galaxies, these rotation curves remain remarkably consistent. From dwarf galaxies to giant spirals, flat rotation curves are seen everywhere, suggesting that dark matter is not an anomaly of one galaxy, but a universal presence in the cosmos. This realization has prompted deeper exploration into dark matter's elusive nature, leading to a surge in experiments and observational studies. One of the most powerful tools in the study of dark matter is gravitational lensing. This phenomenon occurs when a massive object like a galaxy cluster bends the light from more distant objects behind it, such as galaxies or quasars. This bending of light acts as a cosmic magnifying glass, distorting and amplifying the images of distant objects. By observing these distortions, scientists can map out the mass distribution of the object, causing the lensing, revealing the presence of dark matter. Gravitational lensing manifests in two main forms: strong lensing and weak lensing. In strong lensing, the effects are dramatic, producing multiple images, arcs, or even entire rings known as Einstein rings. These exaggerated distortions make it easier to model the mass distribution of the lensing object. By using these models, scientists can infer the location and extent of dark matter, even though it doesn't emit light. Weak lensing, on the other hand, involves subtler and more widespread distortions. Individual distortions are minute, but when researchers statistically analyze the shapes and orientations of many background galaxies, they can detect a coherent pattern caused by dark matter. This allows scientists to create detailed maps of dark matter's distribution across large areas of the sky. These maps are crucial for understanding the large-scale structure of the universe and how dark matter influences the formation of galaxies and clusters. The beauty of gravitational lensing lies in its ability to provide direct insights into the distribution of dark matter, independent of visible matter. This has produced some of the most compelling evidence for dark matter. For example, the bullet cluster, a collision between two galaxy clusters, offers a dramatic example of how dark matter behaves. Observations show a separation between the visible matter and the dark matter, as inferred from gravitational lensing. This observation supports our understanding of dark matter's role in the universe and strengthens our belief in its existence on a cosmic scale. Another significant puzzle in dark matter research is the core cusp problem. Simulations of cold dark matter suggest that it should form dense, cuspy centers at the cores of galaxies. These peaks in density should be particularly evident in dwarf and low-mass galaxies. However, observations do not match these predictions. Instead, galaxies tend to have flatter density profiles in their centers, creating a discrepancy between the theory and what we observe in the cosmos. This ongoing issue pushes scientists to refine their models of dark matter and its interaction with ordinary matter, urging new theories to explain the gaps in our current understanding. As these various pieces of evidence continue to unfold, dark matter remains one of the greatest mysteries of modern astrophysics. Whether through galaxy rotation curves, gravitational lensing, or challenges in theoretical models, dark matter shapes our understanding of the universe in ways we are only beginning to fully grasp. However, observations suggest that many galaxies, particularly small satellite galaxies orbiting larger ones, exhibit intriguing characteristics when it comes to their dark matter distribution. These galaxies often present flatter core distributions, where the dark matter density remains remarkably constant within their central regions. This finding has sparked intense scientific debate, drawing attention to what is known as the core cusp problem. The core cusp problem first emerged from measurements of the rotation curves in dwarf and low surface brightness galaxies. These rotation curves, which chart the velocity of stars at different distances from the galactic center, indicated that the gravitational pull at the centers of these galaxies was significantly weaker than expected. According to predictions made by traditional dark matter models, these regions should experience a much stronger gravitational force due to a cuspy dark matter profile. In simpler terms, the dark matter should be sharply concentrated at the galaxy's core. Instead, what astronomers observed was a much more spread out, or cored, mass distribution. Addressing this discrepancy has prompted several theoretical and computational approaches. One widely discussed possibility centers on the influence of ordinary visible matter, also known as baryonic matter, on the dark matter structure. Events like supernova explosions, for instance, are capable of releasing massive amounts of energy, which can drive gas out of a galaxy's central region. This redistribution of matter and energy could flatten the dark matter cusp, transforming it into a more uniform core. These so-called feedback processes provide a compelling explanation for why dark matter profiles appear less steep than originally predicted. Another intriguing hypothesis revolves around the very nature of dark matter itself. While traditional models posit that dark matter is cold, moving slowly and accumulating in dense clumps, a competing theory introduces the concept of warm dark matter. In this scenario, dark matter particles move faster and have higher velocities than their cold counterparts. This increased movement could prevent dark matter from clumping tightly at the centers of galaxies, resulting in flatter, more uniform density profiles. The possibility that dark matter might be warm rather than cold adds a new layer of complexity to this ongoing puzzle. The core cusp problem, however, is far from resolved. It remains a focal point of research and continues to spark intense debate. Solving this issue could fundamentally reshape our understanding of dark matter, offering deeper insights into the mechanisms that govern galaxy formation and evolution. This investigation also holds the potential to reveal more about the intricate relationship between dark matter and baryonic matter, the ordinary matter that makes up stars, planets, and galaxies themselves. Yet, as we probe the mysteries of dark matter, we are also confronted with another profound enigma: dark energy. While dark matter and dark energy both exert powerful influences on the universe, their roles are fundamentally different. Dark matter, accounting for about 27% of the universe's energy content, primarily affects galaxies through its gravitational pull. Dark energy, on the other hand, constitutes roughly 70% of the universe's energy and is responsible for the accelerated expansion of space. For the most part, scientists treat dark matter and dark energy as separate phenomena, each operating through distinct mechanisms. Dark matter attracts, pulling galaxies and clusters of galaxies together, while dark energy pushes, accelerating the expansion of the universe. However, recent theoretical models have suggested the possibility that these two cosmic forces may not be entirely independent. Some hypotheses propose that dark matter and dark energy might be linked through a deeper unified field or interaction. In such models, dark energy might gradually evolve over time, influencing the distribution or properties of dark matter in ways we have yet to fully understand. These coupled dark energy models suggest that the equation of state, which describes the relationship between dark energy's pressure and its energy density, could shift over time. If such changes occur, they could offer a new perspective on how dark matter behaves and interacts with the larger universe. The idea that dark matter and dark energy could be interconnected raises exciting new possibilities, yet it also underscores the complexity of the questions we face. As we continue to explore the nature of these mysterious cosmic ingredients, our efforts are inching us closer to understanding how galaxies form, how they evolve, and what role dark matter and dark energy truly play in the grand unfolding story of the universe. The investigation into these forces, alongside the continued study of their interplay, remains one of the most important endeavors in modern cosmology. Solving these mysteries could one day unlock some of the deepest secrets of the cosmos, offering us a glimpse into the forces that shape not only galaxies, but the very fabric of space itself. In the vast expanse of the universe, dark matter and dark energy remain two of the most mysterious and elusive components of the cosmos. For cosmologists, exploring their interactions presents a challenging yet fascinating frontier in modern science. These scientists examine deviations from the standard cosmological model, one that assumes no direct interaction between dark matter and dark energy. This model posits that both entities coexist in the universe, yet their behaviors are independent of one another. To understand if this assumption holds true, researchers search for subtle signs of interaction in a variety of cosmic phenomena, including the cosmic microwave background radiation, the large-scale structure of galaxies, and the precise measurement of the Hubble constant, which dictates the rate at which the universe is expanding. Unexpected anomalies in these measurements could be the first clues hinting at an interaction between dark matter and dark energy. Such discoveries might suggest new, unexplored realms of physics that could profoundly alter our understanding of the universe. The role of dark matter is already known to be vital in explaining the movement of galaxies, while dark energy is believed to drive the accelerated expansion of the universe. If these two forces are indeed intertwined, it would represent a groundbreaking shift in cosmological theories, potentially unlocking new insights into how the universe functions on the largest scales. However, despite the tantalizing theories that abound, the empirical evidence required to confirm such interactions remains elusive. As telescopes and experimental techniques continue to advance, more data is gathered, giving researchers the tools to refine their models. The ultimate goal is to unravel how dark matter and dark energy, these enigmatic forces of the universe, might or might not interact. In this ongoing quest, evidence will be the key to determining whether these mysterious components are independent players or if they are locked in a deeper, previously unknown connection that could rewrite the very laws of physics. One aspect of physics that contributes significantly to this understanding is quantum vacuum fluctuations, a fundamental element of quantum field theory. These fluctuations reveal the dynamic nature of the so-called vacuum, which, contrary to classical assumptions, is not an empty void. Instead, the quantum vacuum is a seething, turbulent field where virtual particles appear and disappear in a constant dance. This phenomenon occurs due to the Heisenberg uncertainty principle, which tells us that we cannot precisely know certain pairs of properties, like position and momentum or energy and time, at the same time. This inherent uncertainty prevents the vacuum from being static, turning it into a chaotic, fluctuating energy field, even in the emptiest stretches of intergalactic space. Though invisible to the naked eye, These quantum vacuum fluctuations leave a tangible mark on the universe. A clear example of this can be seen in the Casimir effect. When two large, uncharged parallel plates are placed very close together in a vacuum, they experience an attractive force. This force arises because the vacuum fluctuations are suppressed between the plates, demonstrating that even empty space has observable effects on physical matter. This phenomenon suggests that the vacuum is not truly empty, but rather filled with energy that can influence the world around it. Such quantum phenomena have significant implications for our understanding of the universe. One intriguing possibility is the connection between quantum vacuum fluctuations and dark energy, the mysterious force accelerating the universe's expansion. Some theories suggest that the energy contributed by these quantum fluctuations could help explain the observed acceleration. Although this idea remains speculative, it represents an exciting link between the microscopic world of quantum mechanics and the vast scale of cosmology. As our observational tools become more advanced, we edge closer to understanding whether these quantum fluctuations are indeed responsible for dark energy's role in the universe. Equally crucial in the study of the cosmos is the process of quantum tunneling, which plays a fundamental role in the heart of stars. Quantum tunneling allows particles to pass through energy barriers that, according to classical physics, would be impenetrable. This seemingly magical phenomenon is vital for the process of nuclear fusion, the source of a star's energy. Inside stellar cores, temperatures and pressures are incredibly high, yet not sufficient to overcome the electrostatic repulsion between positively charged atomic nuclei. Classical physics suggests that under these conditions, protons, such as those in hydrogen nuclei, should repel each other, preventing fusion. However, quantum tunneling allows these particles to bypass this barrier, enabling the fusion process that powers stars. In stars, this quantum process is not merely a theoretical curiosity, but the very mechanism that fuels their existence. Without quantum tunneling, stars would not burn as they do, and life as we know it would not be possible. The interplay of quantum mechanics and stellar physics illustrates just how deeply quantum phenomena shape the universe at every scale, from the smallest particles to the grandest structures. As our understanding of quantum vacuum fluctuations and quantum tunneling deepens, it becomes clear that these fundamental processes are not isolated phenomena. They are deeply connected to the fabric of the universe, influencing everything from the formation of galaxies to the birth of stars. As our experimental techniques become more sophisticated, it is likely that we will uncover even more profound mysteries hidden within these quantum processes. The future of cosmology promises a deeper connection between the subatomic world and the vast universe we observe, a connection that could forever change how we perceive the cosmos. However, quantum physics introduces a remarkable and perplexing feature: the probabilistic nature of particles, which allows them to bypass seemingly insurmountable barriers. This phenomenon, known as quantum tunneling, enables particles like protons to pass through energy barriers that would be impossible to overcome under classical physics. Through tunneling, protons can get close enough to one another to overcome their electrostatic repulsion and initiate the process of nuclear fusion. Once these protons collide and come within a short range of one another, the strong nuclear force takes over, binding them together and forming a new element. This process, which begins in the heart of stars like our Sun, releases vast amounts of energy. This energy radiates outward, powering the star and providing the heat and light that sustain life on planets like Earth. Quantum tunneling's influence extends far beyond proton fusion. It is a crucial principle in the nuclear reactions occurring inside stars, driving not only the fusion of protons, but also the fusion of heavier elements within more massive stars. As stars evolve and their core temperatures rise, quantum tunneling facilitates the fusion of helium and other elements, leading to the formation of a diverse range of nuclei scattered throughout the universe. In this way, quantum tunneling ensures that stars not only shine, but also create the essential elements that drive the cosmic evolution of matter and energy. It plays an essential role in the birth of new elements and the energy production that fuels the dynamics of the universe. One of the most fascinating and perplexing phenomena in quantum mechanics is quantum entanglement. This mind-bending occurrence happens when two or more particles become intertwined, such that the state of one particle directly influences the state of another, no matter how vast the distance between them. This instantaneous interaction defies our classical understanding of space and time, suggesting that there might be deeper, hidden principles governing the very fabric of the universe. In the early universe, quantum entanglement could have played a crucial role in shaping the distribution of mass, matter, and energy during the inflationary period, the rapid expansion that followed the Big Bang. During this time, quantum fluctuations stretched to immense cosmic scales became the seeds for galaxy formation and the large-scale structures that define the universe. Entanglement among these particles may have helped maintain the coherence of these fluctuations, influencing the pattern of cosmic microwave background radiation and the eventual distribution of matter in the universe. Beyond the early universe, quantum entanglement also plays a critical role in some of the most puzzling phenomena in astrophysics, such as the black hole information paradox. When particles become entangled near the event horizon of a black hole, their behavior could offer vital clues to understanding whether information that falls into a black hole is truly lost forever or somehow preserved. Some theories suggest that entanglement could preserve information at the event horizon, ensuring that the principles of quantum mechanics remain intact even in the extreme environment of a black hole. On a more speculative level, quantum entanglement might provide insights into the nature of space-time itself. The interconnectedness of entangled particles could hint at a deeper, information-based structure underlying the classical fabric of the universe. Some hypotheses propose that space-time could emerge from a profoundly entangled state, offering fresh perspectives on gravity and potentially unifying it with quantum mechanics. While these ideas remain on the frontier of theoretical physics, they open up thrilling possibilities that may revolutionize our understanding of the cosmos as experimental techniques continue to advance. Quantum effects are also central to the remarkable properties of neutron stars, the dense remnants of massive stars that have exploded as supernovae. Neutron stars possess a mass comparable to that of our Sun, yet they are compressed into a sphere only about 10 kilometers in diameter. At such extraordinary densities, quantum mechanics governs the behavior of matter in ways that defy everyday experiences. One of the most significant quantum effects in neutron stars is the Pauli exclusion principle. This principle states that no two fermions, particles like neutrons, protons, and electrons, can occupy the same quantum state at the same time. In the extreme environment of a neutron star, where densities are so high, the Pauli exclusion principle leads to a phenomenon known as degeneracy pressure. This pressure provides a counteracting force that resists the gravitational collapse of the star, preventing it from imploding under its immense mass. Without this quantum mechanical effect, neutron stars would not be able to sustain their structure, making degeneracy pressure one of the most crucial forces at play in the evolution of these extreme celestial bodies. In summary, quantum mechanics is not just an abstract theory. It is the very foundation of the universe's ongoing processes. From the fusion of protons in stars to the complex interactions of particles in black holes, quantum tunneling and entanglement drive the cosmic evolution of matter and energy. As we continue to explore the frontiers of quantum mechanics, we uncover deeper insights into the nature of the universe, revealing how the strange and counterintuitive rules of quantum physics shape the cosmos in ways that we are only beginning to understand. The influence of quantum effects will continue to unfold, guiding the future of astrophysics and our understanding of the universe's origins, its structure, and its eventual fate. Neutron stars, some of the most extreme objects in the universe, exhibit remarkable properties that challenge our understanding of the laws of physics. Within their dense cores, these stars demonstrate a phenomenon known as superfluidity, where neutrons pair up in a way that allows them to flow without any resistance. This state of matter, known as Cooper pairing, is reminiscent of how electrons behave in superconductors. The result is a form of matter that can only exist under the most extreme conditions. This superfluid interior profoundly influences the thermal properties of neutron stars and affects their rotation, leading to fascinating phenomena like glitches, sudden and unexpected changes in a star's spin rate caused by shifts in the superfluid interior. Moreover, neutron stars possess magnetic fields that can reach staggering intensities far beyond anything we experience on Earth. These magnetic fields, created by the compression of the magnetic flux left over from the original star, can be trillions of times stronger than Earth's magnetic field. This immense magnetic force leads to stunning emissions of energy, including powerful bursts of X-rays and gamma rays. In some cases, these fields are so intense that they give rise to a special class of neutron stars known as magnetars, which are capable of emitting extraordinary amounts of radiation. These extreme fields and the quantum processes responsible for them offer scientists a unique glimpse into the bizarre behavior of matter and energy at the quantum level. However, the influence of quantum mechanics does not end there. Neutron stars are also a natural laboratory for studying quantum electrodynamics and the quantum effects that prevent these stars from collapsing under their own immense gravity. The dense cores of these stars create conditions where the laws of quantum mechanics play an essential role, not only in preventing collapse, but also in the creation of exotic states of matter. By studying these stars, we gain insights into the deepest mysteries of the universe, providing clues about the fundamental forces that govern both the microscopic and macroscopic realms. Quantum decoherence, a phenomenon that occurs when quantum systems interact with their environment, plays a crucial role in our understanding of the universe. At the quantum level, particles exist in a state of superposition, meaning they can be in multiple states or locations simultaneously. However, the classical world we observe, stars, galaxies, and cosmic events, operates according to the laws of classical physics, where objects have definite positions and states. Decoherence is the process by which these superpositions collapse into a single distinct outcome due to interaction with the surrounding environment. It is through this mechanism that the quantum world becomes classical, and the universe operates in the way we observe on a large scale. This interaction between the quantum and classical worlds is key to understanding the large-scale structure of the universe. Early quantum fluctuations, occurring in the moments after the Big Bang, were magnified during a period known as cosmic inflation. Once these fluctuations reached a sufficient scale, decoherence took over, allowing them to manifest as the galaxies, stars, and clusters of galaxies we see today. The cosmic microwave background radiation, a faint glow that permeates the universe, is another key piece of evidence of these processes. It carries imprints of the early universe, and its study helps cosmologists understand how quantum fluctuations evolved into the structures that dominate the cosmos. Understanding quantum decoherence also helps predict and interpret current cosmological phenomena, giving us a clearer, more detailed picture of the universe's past, present, and future. One of the most profound questions in modern physics concerns the search for quantum gravity, the theoretical framework that seeks to merge quantum mechanics with general relativity. This quest aims to resolve the mysteries surrounding singularities, the points within black holes where densities become infinite, and the laws of physics cease to function. Current theories, such as general relativity, predict the existence of these singularities but fall short in describing the extreme conditions inside black holes. Quantum gravity attempts to fill this gap, offering new insights into the structure of space-time at the smallest scales, where quantum effects cannot be ignored. Two leading theories in the search for quantum gravity are string theory and loop quantum gravity. String theory suggests that instead of point particles, the fundamental building blocks of the universe are one-dimensional strings that vibrate in multiple dimensions. This theory posits that extra dimensions of space might help diffuse the gravitational collapse of black holes, preventing the formation of a singularity. On the other hand, loop quantum gravity proposes that space-time itself is quantized, much like matter is made up of atoms. According to this theory, the core of a black hole does not collapse into a singularity. Instead, it may undergo a quantum bounce, reaching a minimum volume before rebounding, suggesting that singularities may be portals to other regions of space or even other universes. Although these quantum gravity theories remain under development and have not yet been experimentally verified, They represent some of the most exciting and ambitious areas of theoretical physics. They offer tantalizing possibilities for resolving some of the most profound questions about the nature of the universe, from the behavior of black holes to the very fabric of space-time itself. The study of neutron stars, quantum mechanics, and quantum gravity is reshaping our understanding of the universe, offering a unique window into the fundamental forces that govern both the smallest and largest scales of existence. As we continue to explore these extraordinary phenomena, we unlock new insights that could forever change our understanding of the cosmos. However, they present a fascinating possibility that the singularities at the core of black holes might not be as singular as once thought. Instead, these singularities could be smoothed out by the quantum structure of space-time itself. If this idea is confirmed, it would revolutionize our understanding of black holes, unlocking new insights into the deepest mysteries of the universe. At the heart of this exploration lies a profound concept: virtual particles. These are fleeting fluctuations that emerge and vanish spontaneously in the vacuum of space, as predicted by quantum field theory. Though they appear momentarily, these particle-antiparticle pairs exist only to annihilate each other in a brief flash of energy. Yet, the behavior of virtual particles near black holes becomes especially intriguing, offering a unique glimpse into the workings of extreme environments where quantum mechanics and gravity intertwine. According to the groundbreaking work of Stephen Hawking, virtual particles near a black hole's event horizon may behave differently due to the black hole's immense gravitational field. Under these extreme conditions, one particle in a virtual pair can be trapped by the black hole's gravity, while the other escapes, becoming a real particle rather than remaining a fleeting quantum fluctuation. This process is what we now call Hawking radiation, named after the physicist who predicted it. The escaping particle can be detected as radiation, while its counterpart is pulled into the black hole, effectively reducing its mass. Over time, this radiation suggests that black holes could slowly lose mass and eventually evaporate, a startling concept that challenges the classical idea that nothing can escape a black hole. The concept of black holes radiating energy is a profound breakthrough, as it opens the door to understanding the complex relationship between quantum mechanics and gravity. Moreover, the existence of virtual particles near the event horizon also raises important philosophical and physical questions about the nature of information in the universe. What happens to the information that falls into a black hole, particularly when it interacts with virtual particles near the event horizon? This inquiry leads us directly to the black hole information paradox, one of the most pressing unresolved issues in theoretical physics. Thus, the study of virtual particles near black holes is not merely an exploration of how black holes emit Hawking radiation. It also brings us closer to resolving some of the deepest and most fundamental questions in physics, questions that might only be answered through a unified theory that bridges quantum mechanics and general relativity. Theoretical physicists are increasingly focused on uncovering the nature of this connection, as understanding this relationship could provide answers to questions that have perplexed scientists for decades. But the role of quantum effects extends far beyond black holes. Quantum fluctuations were essential in the early stages of galaxy formation, setting the stage for the large-scale structures we observe in the universe today. The story begins just moments after the Big Bang, during a period known as cosmic inflation. This incredibly brief epoch, occurring just fractions of a second after the birth of the universe, saw a rapid and exponential expansion. During this time, tiny quantum fluctuations, minute variations in the density of the primordial quantum field, were stretched to vast scales, creating regions that were slightly over-dense and others slightly under-dense. As cosmic inflation ended, the universe continued to expand, but at a much slower rate. Despite this slower expansion, the quantum fluctuations that had been stretched to these macroscopic scales remained imprinted on the fabric of space. These variations, initially imperceptible, began to play a critical role as gravity took over. As the universe cooled and matter started to coalesce into atoms, gravity amplified the overdense regions, pulling in more and more matter. This process laid the foundation for the formation of the first structures in the universe, the seeds of galaxies. In essence, quantum effects provided the raw material, and gravity acted as the gardener, cultivating these seeds into the galaxies and other cosmic structures that stretch across billions of light years. These early quantum fluctuations and their amplification through gravity are the key to understanding how the universe evolved from a nearly uniform state to the richly complex structures we see today. As we peer into the nature of black holes and the quantum effects that shape the very beginning of the cosmos, we are reminded of the profound interplay between the tiniest particles and the largest cosmic structures, an interplay that continues to shape our understanding of the universe in ways we are only beginning to fully grasp. Moreover, evidence of these early quantum fluctuations is embedded in the very fabric of the universe, visible today in the cosmic microwave background radiation. This ancient light, a relic from about 380,000 years after the Big Bang, carries the imprints of density variations caused by quantum effects. When we study these imprints through telescopes like the Wilkinson Microwave Anisotropy Probe and the Planck Satellite, scientists are able to peer back into the universe's infancy, reconstructing its early conditions and gaining a deeper understanding of how galaxies, clusters, and the complex structure of the cosmos formed. Quantum effects weren't just a precursor to the universe's structure. They were the fundamental forces that shaped its very foundation. By setting the initial conditions, quantum mechanics helped script the grand cosmic narrative. It sculpted the universe from a uniform beginning into the richly detailed tapestry we observe today. This process was more than just theoretical. It was practical. Quantum fluctuations likely played a significant role in generating the cosmic magnetic fields that are some of the most enigmatic features of the universe. These magnetic fields, observed not only in galaxies and clusters but also in the vast emptiness between stars and galaxies, have long puzzled scientists. How did they form, and what force gave rise to them? One intriguing hypothesis ties the origin of these magnetic fields to quantum fluctuations that occurred during the early universe, particularly during the inflationary period. During inflation, the universe expanded at an astonishing rate, stretching the quantum fluctuations, tiny variations in the density of primordial plasma, into vast cosmic scales. This expansion did not merely stretch space itself, but also altered the dynamics of the fundamental forces. The fluctuations, influenced by these forces, could have produced regions of the universe with tiny electric fields. According to Faraday's law of induction, changing electric fields can generate magnetic fields. Therefore, the same quantum processes that seeded the density variations we observe today may also have initiated the magnetic fields that now stretch across the cosmos. As the universe continued to expand and cool, these initial, weak, quantum-generated magnetic fields would have served as seeds. Later astrophysical processes, such as the movement of ionized gases and dynamos within stars and galaxies, would have amplified these seed fields to the intensities we detect today. However, this amplification was no simple feat. The original magnetic fields produced by quantum fluctuations were incredibly weak, barely detectable in their primordial form. Yet they laid the groundwork for much larger, more complex magnetic fields. Further evidence supporting this theory comes from the relic electromagnetic waves detected in the cosmic microwave background radiation. These ancient relics carry valuable information about electromagnetic processes in the early universe and offer important clues about how cosmic magnetic fields could have formed. While the exact mechanisms are still a subject of intense research, the connection between quantum fluctuations and the birth of cosmic magnetic fields presents a promising avenue for explaining their origin. Quantum fluctuations not only give us insight into the large-scale structure of the universe, but they also provide a plausible explanation for the emergence of these pervasive, powerful magnetic fields that weave through the fabric of the cosmos. By studying the relics of these processes and examining theoretical models, scientists are piecing together yet another layer of the complex, fascinating story of our universe's evolution. Quantum uncertainty also profoundly impacts our understanding of the universe's initial conditions. At the heart of this concept lies Heisenberg's uncertainty principle, which tells us that it is impossible to know both the exact position and momentum of a particle simultaneously. This fundamental principle introduces an intrinsic unpredictability into the early cosmos. During the brief but crucial period known as cosmic inflation, quantum uncertainty played a pivotal role in shaping the universe's foundational landscape. The rapid expansion of the universe stretched out quantum fluctuations, magnifying the tiny uncertainties inherent at the quantum scale to cosmic proportions. These fluctuations manifested in a variety of ways: variations in density, temperature, and other physical properties across the cosmos. Regions with slightly higher density due to these quantum fluctuations eventually gravitationally coalesced, forming the stars, galaxies, and clusters we see today. The cosmic microwave background radiation, the ancient light from roughly 380,000 years after the Big Bang, still carries traces of these early quantum fluctuations. The minute temperature differences we detect in this radiation are direct imprints of these fluctuations, and by studying them, scientists can trace the universe's earliest conditions. But the uncertainty doesn't end with quantum fluctuations. Quantum uncertainty introduces a philosophical conundrum. While we can predict the broad evolution and structure of the cosmos, the exact blueprint of its beginnings will always remain just beyond our precise grasp. This uncertainty doesn't diminish our understanding, it challenges it. The universe at its core operates on probabilistic laws, not deterministic ones. This shift from certainty to probability redefines how we view the cosmos, introducing a new way of understanding its origins. In this way, quantum uncertainty is not merely a scientific observation, it is a fundamental aspect of the universe's creation. It shapes not only how we understand the formation of cosmic structures, but also our broader view of reality. Quantum mechanics has helped us unlock a narrative that is far from linear or deterministic, one in which uncertainty and probability played, and continue to play, a profound role in shaping the universe as we know it. At the core of modern physics, quantum uncertainty continues to be an enigmatic and captivating puzzle that drives the boundaries of both theoretical research and observational science. It challenges our understanding of the very fabric of the universe, specifically the early moments of existence where the nature of time itself may be altered in the most extreme environments, like those found near black holes. Black holes, mysterious cosmic giants, are regions of space where gravity is so intense that it warps the very structure of space-time. In general relativity, gravity is not simply a force but a curvature caused by the mass of objects within space. The presence of a massive object distorts the surrounding space-time, and this warping becomes infinitely more pronounced in the vicinity of a black hole. As one approaches the black hole, this gravitational distortion causes time itself to behave in a way that is beyond our intuitive understanding. The closer you get to a black hole, the stronger the gravitational pull becomes, warping the space around it more severely. This results in a phenomenon known as time dilation, a slowing down of time relative to areas of weaker gravity. Imagine standing at a safe distance from a black hole, observing someone daring to approach it. From your vantage point, it would appear that this individual's movement slows down as they draw closer to the black hole's event horizon, to the point where their actions seem to freeze in time. It's as if they are slowly suspended, trapped in a still moment, the universe seemingly holding its breath. Yet, for the person falling into the black hole, time proceeds normally according to their own clock. They would be oblivious to the slowing effect that an external observer perceives. Their experience would be devoid of any noticeable anomaly, despite the fact that they are hurtling toward a place where space-time itself breaks down. This effect reaches its peak at the event horizon, the boundary of no return, where the very nature of time and space ceases to behave predictably. From the perspective of an observer far away, any object falling toward a black hole would appear to freeze in time, slowly fading into nothingness due to a phenomenon known as gravitational redshift. This occurs as light, the very messenger of information, loses energy and shifts to longer wavelengths as it climbs out of the black hole's gravitational well. But from the perspective of the object falling in, the experience would continue uninterrupted. They would cross the event horizon without realizing anything unusual had occurred, though they would face incredible tidal forces in the process. Once past the event horizon, the notion of time undergoes an even more radical transformation. At the very core of the black hole, where space-time curvature becomes infinite, lies the singularity, a place where all known physical laws break down. At this point, the distinction between time and space may cease to exist as we understand them. Time, which has always been thought of as a one-way stream, could become something entirely different. Instead of moving through time as we experience it, perhaps one would be moving through space, guided by the force of time itself. Such extreme distortions of time push the limits of our current understanding of general relativity. They bring into sharper focus the need for a unified theory of quantum gravity, one that could reconcile the odd behavior of time near black holes with the well-established principles of quantum mechanics. By merging these two realms, one that governs the grand scale of cosmic phenomena and the other that rules the microscopic world, scientists may uncover deeper insights into the true nature of time, even in the most extreme and unfathomable corners of the universe. Moreover, the black hole information paradox introduces yet another layer of complexity to this already perplexing puzzle. This paradox presents a challenge to some of the most fundamental principles of physics, especially the idea that information cannot be lost. According to quantum mechanics, every bit of information should be preserved, even if the object it pertains to is destroyed. But black holes seem to defy this idea, as anything falling into one appears to be lost forever, seemingly wiped from the universe once the black hole evaporates through Hawking radiation. Hawking radiation, proposed by the legendary physicist Stephen Hawking, suggests that black holes can gradually lose mass and energy over time. The radiation emitted by black holes could cause them to eventually evaporate, with their energy dispersing back into the universe. Yet this raises a profound question. If information is never truly lost, then how does the universe preserve the details of what falls into a black hole? Is there a way for the information to escape, or does it become irretrievably lost to the cosmos? This paradox remains one of the most perplexing and hotly debated issues in theoretical physics, beckoning for a deeper understanding of how the universe functions at its most fundamental levels. However, if a black hole were to completely evaporate, what happens to all the information about the physical state of everything it once absorbed? This question is at the very heart of one of the most perplexing puzzles in theoretical physics, challenging our understanding of quantum mechanics and general relativity. Quantum theory asserts that information can never truly be destroyed, a principle known as the no-cloning theorem. This means that even if a black hole were to collapse and eventually vanish through the process of Hawking radiation, the information it once contained should, in theory, be preserved somewhere. But this seems to collide directly with the widely held belief that black holes obliterate all information about the objects that fall into them. So, where does that leave us? One intriguing resolution suggests that the information might be encoded in the very radiation that the black hole emits as it slowly evaporates. Initially, the radiation was thought to be completely random and devoid of any meaningful pattern, but some theorists now propose that subtle correlations within the Hawking radiation could actually carry the scrambled remnants of the black hole's contents. With a complete theory of quantum gravity, these patterns might be deciphered, unlocking the mystery of the lost information. A particularly fascinating proposal comes from the holographic principle, a concept developed independently by Gerard 't Hooft and Leonard Susskind. According to this principle, all the information within a three-dimensional space, such as the interior of a black hole, could actually be encoded on a two-dimensional surface, specifically the event horizon of the black hole itself. In this view, the event horizon would act as a kind of hologram, containing all the information about what has fallen into the black hole. This idea offers a way to think about black holes that avoids the need for a singularity at their core and opens up new possibilities for understanding information storage. Furthermore, advances in string theory propose that black holes might not even contain singularities at all. Instead, they may have complex extended structures known as fuzzballs, where the information about the contents of the black hole is preserved in a highly intricate and interconnected form. These fuzzballs would allow the information to remain encoded without the traditional singularity, offering a new and exciting framework for understanding black hole interiors. Though still in its infancy, this idea suggests that the information isn't lost, but rather exists in a form that we are still working to fully comprehend. Despite these fascinating theories, none have yet been universally accepted or empirically validated. The black hole information paradox remains one of the most profound and unresolved challenges in theoretical physics. Solving it would not only bridge the gap between quantum mechanics and general relativity, but could also lead to groundbreaking revelations about the true nature of space, time, and information itself. Now, consider closed time-like curves, CTCs, paths through space-time that loop back on themselves, potentially allowing for time travel to the past. This idea, rooted in the equations of general relativity, opens a Pandora's box of paradoxes and implications that challenge our very understanding of time. If CTCs exist, they would allow an object or person to revisit earlier points in their own history, theoretically enabling time travel. But this opens the door to a host of paradoxes. The most famous of these is the grandfather paradox. In this scenario, a time traveler could go back in time and alter events in such a way that their own existence is prevented, perhaps by preventing their grandparents from meeting, for example. This creates a logical contradiction that directly challenges our understanding of causality, the principle that causes precede effects. If such paradoxes exist, how can we reconcile them with the laws of physics? To address these challenges, physicists have proposed several possible solutions. One such approach is the self-consistency principle, which suggests that the actions of a time traveler must always be part of history. In other words, whatever the time traveler does in the past has always been part of the timeline, meaning no paradox can arise. This view leads to a deterministic perspective, where every action taken by the time traveler contributes to the events they already know, ensuring that the timeline remains consistent. Another possible resolution is the concept of alternate histories, or parallel universes. In this framework, traveling back in time creates a new, separate timeline, one that doesn't affect the original universe. Any changes made in the past would occur in this new timeline, thus sidestepping paradoxes and preserving causality in the traveler's original timeline. This idea introduces the possibility of multiple branching realities, each influenced by the actions of time travelers. Moreover, the existence of closed time-like curves could have profound implications for our understanding of the very structure of the universe and the nature of time. These curves might hint at extraordinary regions of space-time with properties that we have yet to fully understand, such as the interiors of certain spinning black holes, also known as Kerr black holes. Alternatively, they could point to the existence of exotic objects like wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe, potentially allowing for faster-than-light travel or even time travel. In conclusion, whether considering the nature of black hole evaporation or the paradoxes of time travel, the exploration of these concepts pushes the boundaries of our understanding of the cosmos. These ideas may not only reshape our understanding of space and time, but could also provide profound insights into the very fabric of reality itself. However, the creation of closed time-like curves, CTCs, often requires extraordinary conditions or materials with negative energy density, such as those described by exotic matter, a concept that remains speculative and unverified by experimental evidence. The very existence of closed time-like curves is still a matter of intense theoretical inquiry and debate among physicists. Should they ever be proven to exist, they would challenge our very understanding of the laws of physics, causality, and the profoundly intricate nature of spacetime. Unraveling the mystery of CTCs might demand not just new theoretical breakthroughs, but also groundbreaking advancements in experimental physics. One of the most intriguing phenomena that challenges our understanding of causality in space is quantum entanglement. This strange and puzzling property of quantum particles has been referred to by Albert Einstein as spooky action at a distance. When two particles become entangled, their states become inherently linked no matter the distance between them. Any change in the state of one particle instantaneously affects the state of the other, seemingly violating the principle that information cannot travel faster than the speed of light. In this entangled state, the particles share a collective state. The measurement of one particle's state automatically determines the state of the other, creating an instantaneous correlation. This challenge to our classical understanding of causality defies the concept of local causality, which posits that objects can only be influenced directly by their immediate surroundings. Quantum entanglement has been experimentally confirmed through various studies, including the renowned Bell test experiments. These experiments closed potential loopholes and provided strong evidence for the non-local nature of entangled particles, demonstrating correlations that cannot be explained by any theory of hidden variables. This provides empirical support for the quantum mechanical prediction that entanglement alters our classical understanding of how objects interact. The implications of quantum entanglement reach far beyond just theoretical physics. This phenomenon has led to transformative breakthroughs in fields like quantum computing and information theory. Entanglement plays a pivotal role in quantum teleportation, a process where information about the state of a particle is transmitted between entangled pairs across arbitrary distances without physically moving the particles themselves. While this does not violate the speed of light limitation, it does rely on the classical transmission of supplementary data to preserve causality, making it a fascinating yet complex example of quantum mechanics in action. Moreover, some advanced theories aim to reconcile quantum entanglement with space-time geometry. For example, the ER equals EPR conjecture proposes a stunning connection between quantum theory and general relativity. This theory suggests that entangled particles could be linked through microscopic wormholes, known as Einstein-Rosen bridges, offering a potential space-time explanation for the non-local nature of entanglement. Such theories push us to reconsider fundamental notions of causality and locality, compelling physicists to explore new frameworks that might unify quantum mechanics with the very fabric of space-time. The pursuit of this goal could unlock profound insights into the true nature of reality. The concept of the arrow of time, which suggests that time flows in one direction from the past to the future, is deeply rooted in various fields of physics, philosophy, and human experience. One of the primary explanations for this phenomenon is based on the second law of thermodynamics, which states that entropy, or disorder, in a closed system tends to increase over time. This fundamental law underpins the thermodynamic arrow of time. In the early universe, just after the Big Bang, conditions were highly ordered with low entropy. As the universe expanded and evolved, entropy gradually increased, giving time its perceived direction. This increase from order to disorder makes events seem to flow from lower entropy states to higher entropy states. A simple example of this is seen when a broken egg becomes part of an omelet. It doesn't spontaneously reassemble itself into an egg, illustrating the irreversible nature of entropy. In addition to the thermodynamic perspective, there is the psychological arrow of time, which is concerned with how we perceive the passage of time. Human memory and cognition are structured in such a way that we remember the past but cannot anticipate the future. This asymmetry shapes our understanding of causality and reinforces the notion that time flows in a single direction. The way our brains process and store information, recording memories in one direction, adds an additional layer to our subjective experience of time, further solidifying the perception that time moves forward. Thus, time itself is not just a physical concept, but a deeply intertwined experience influenced by both the fundamental laws of physics and the workings of human consciousness. As we continue to probe the nature of space-time, quantum mechanics, and causality, we may begin to understand not only the direction of time, but the very structure of reality itself, potentially unlocking new dimensions of knowledge that could radically alter our view of the universe. Time, as we know it, has always been a fundamental concept woven into the very fabric of our universe. It seems to flow relentlessly forward, an invisible current pulling us from one moment to the next. But beneath this seemingly simple progression lies a complex web of forces and phenomena that shape the nature of time, revealing profound mysteries about the cosmos and our place within it. In this exploration, we delve into the intricacies of time's arrow, the expansion of the universe, quantum mechanics, and the potential implications of particles that could break the boundaries of time itself. The expansion of the universe, which began with the Big Bang, provides a cosmic backdrop for our understanding of time. As space itself has been stretching, it creates a temporal framework where the past was a much denser and hotter universe compared to the present. This expansion forms a large-scale context where time seems to tick in one direction, from the highly ordered, low-entropy state of the early universe to the complex, entropic system we inhabit today. It's as if the universe is being pulled toward greater disorder, with time functioning as a measure of that change. Yet, time's nature doesn't just adhere to this macroscopic view. At quantum scales, time takes on an entirely different character. Quantum mechanics introduces a fascinating complexity to the arrow of time. At the quantum level, many processes appear to be time-symmetric, meaning they can unfold in either direction, forward or backward. This idea directly contrasts with our everyday experiences of time, where we only observe events unfolding from past to future. However, when we observe quantum systems, something extraordinary happens. The act of measurement collapses the quantum wave function, which had existed as a superposition of multiple possibilities, into a single outcome. This collapse seems to mirror the classical notion of time's irreversibility, suggesting a bridge between the timeless behavior of quantum mechanics and the familiar flow of time we experience in the macroscopic world. But this still leaves us with profound questions about the true nature of time and its direction. Scientists continue to probe the intersection of entropy, cosmological expansion, and quantum measurement, searching for a unified framework that could explain the unidirectional flow of time. How do these phenomena work together to produce the apparent arrow of time that governs our universe? This is an active area of research, one that may eventually reveal a deeper understanding of the temporal forces that shape our reality. In quantum mechanics, one of the most striking departures from classical causality comes from the probabilistic nature of quantum events. Unlike the classical world, where events unfold in a predictable, linear fashion, quantum mechanics operates on wave functions that represent probabilities rather than certainties. This gives rise to situations that seem to defy traditional notions of cause and effect. One of the most puzzling manifestations of this quantum causality is quantum entanglement. When two particles become entangled, their properties become intrinsically linked, such that the state of one particle influences the state of the other, instantly, no matter how far apart they are. This instantaneous correlation challenges our classical understanding of causality, which insists that information can only travel at or below the speed of light. However, while entanglement creates these distant correlations, it does not violate causality because it cannot be used for faster-than-light communication. Another quantum phenomenon that defies classical causality is the famous double-slit experiment. When particles like electrons are fired at a barrier with two slits, they produce an interference pattern on a screen behind the barrier, a behavior typical of waves. Yet, when the path of the particles is measured, the interference pattern disappears, and the particles behave like discrete particles. This suggests that the act of observation retroactively affects the path of the particles, making it appear as though the outcome was not determined until it was measured. This is known as wave function collapse, a process in which a quantum system, initially in a superposition of states, chooses a single state upon observation. The randomness of when and how this collapse occurs further challenges the deterministic view of causality that classical physics adheres to. One way to reconcile these strange features of quantum mechanics with classical causality is the many worlds interpretation. According to this theory, all possible outcomes of a quantum event actually occur, but each in a separate, non-interacting branch of the universe. This interpretation removes the need for wave function collapse, maintaining a form of deterministic causality across a multiverse. However, it doesn't align with our experience of a single, consistent timeline, raising further questions about the nature of reality. Efforts to unify quantum mechanics with general relativity through the development of a quantum theory of gravity may provide even deeper insights into the nature of time and causality. Some theories suggest that space-time itself could be fundamentally probabilistic and interconnected in ways we are yet to understand, beyond the capabilities of both our classical and quantum frameworks. The paradoxical behavior of quantum mechanics forces us to rethink our basic assumptions about reality, especially when it comes to the nature of causality, locality, and the very fabric of the universe. While these phenomena challenge the classical view of time and cause and effect, they also open up exciting new avenues for exploring the deepest aspects of the cosmos. If particles that travel faster than light were discovered, the implications for our understanding of the universe would be nothing short of revolutionary. Such a discovery would challenge the cornerstone of Einstein's theory of relativity, which holds that no object can exceed the speed of light. The implications would ripple across the foundations of modern physics, particularly concerning our understanding of causality. In the context of relativity, faster-than-light travel could lead to backward time travel in certain reference frames, creating paradoxes similar to the infamous grandfather paradox. This concept, where changes made in the past can affect the present in illogical ways, threatens to destabilize our traditional understanding of temporal sequences and causality itself. In this intriguing landscape, the arrow of time, at once so familiar and so enigmatic, remains one of the most profound and elusive phenomena in the universe. The search for a unified theory of time, whether in the realms of quantum mechanics, cosmology, or beyond, continues to captivate the imagination of physicists and laypeople alike. With every new discovery, we come closer to unraveling the mysteries of time itself, while opening doors to a future where our understanding of reality may be transformed in ways we cannot yet fully imagine. Moreover, tachyons, hypothetical particles that travel faster than light, could unlock new ways for communication and data transfer across vast distances. If we could harness these elusive particles, they might make instantaneous communication possible over cosmic scales, revolutionizing not just how we interact with the universe, but how we understand it. Such a breakthrough would reshape the fields of science and technology, but its implications would extend far beyond practical applications. It would challenge the very foundations of information theory and signal transmission, altering our comprehension of the universe itself. Speculatively, the discovery of tachyons might also offer profound insights into the fundamental workings of the universe. These particles could be integrated into theoretical frameworks attempting to unify quantum mechanics with general relativity, such as string theory. By revealing connections between these domains, tachyons could bridge gaps in our understanding of some of the universe's most enduring mysteries, such as dark matter and dark energy. These elusive phenomena, which remain largely undetected by current instruments, might interact with the universe in ways we have yet to comprehend, potentially unveiling new dimensions of existence we have only begun to hypothesize. However, while these possibilities are tantalizing, it's crucial to remember that tachyons are still entirely hypothetical. No experimental evidence has yet been discovered to confirm their existence. Their theoretical properties raise significant challenges, particularly in the realm of special relativity, where particles faster than light would require imaginary mass and complex energy states, concepts that complicate their plausibility within the framework of current physical laws. Despite these hurdles, the potential discovery of tachyons would set off a chain reaction in both experimental physics and theoretical research, prompting revisions of established laws and pushing the boundaries of our scientific knowledge. The confirmation of tachyons would not only be a revolution in physics, but would also signify a paradigm shift in how we view the universe. It would compel the development of entirely new theoretical models to explain and describe a reality where faster-than-light travel and communication are not only possible, but tangible. Such a discovery would elevate our understanding of space and time, forcing us to rethink the nature of existence itself and how we relate to the vast, mysterious cosmos around us. As we continue to unravel the complexities of space and time, the phenomenon of time dilation stands as a crucial aspect of our exploration. Time dilation, deeply rooted in Einstein's theory of relativity, explains how time slows down or speeds up, depending on an object's motion or proximity to a massive gravitational field. This concept becomes even more significant when applied to distant objects in the universe. When we observe galaxies or supernovae, we are essentially looking back in time, seeing light that has traveled across enormous distances, sometimes millions or even billions of years, before reaching us. This vast separation of time and space means that the effects of time dilation are particularly noticeable when objects move at significant fractions of the speed of light, as in the case of galaxies receding from us due to the expansion of the universe. As these galaxies move away, their light stretches into longer, redder wavelengths, an effect known as redshift. This shift not only helps astronomers measure the velocity and distance of distant objects, but also provides insight into the rate at which time is passing for those objects relative to our frame of reference. Distant supernovae, for instance, exhibit stretched light curves, appearing to brighten and fade more slowly than their counterparts closer to Earth. Gravitational time dilation adds another layer of complexity. Around massive objects like black holes, time slows down considerably. When material falls into a black hole, we observe it through the lens of time dilation. Photons emitted by this material experience a redshift due to gravitational effects, and to a distant observer, the object's motion seems to slow down as it approaches the event horizon. This creates a natural time lapse, allowing us to study the behavior of matter near these intense gravitational forces over extended periods, giving us unprecedented insight into the workings of one of the universe's most enigmatic phenomena. Furthermore, time dilation affects how we model the evolution of the universe itself. When fitting observational data to cosmological models, we must account for relativistic time effects to accurately trace the history of the cosmos. Time dilation helps us understand the age of distant celestial objects, such as galaxies and stars, and provides clarity on the timing of significant cosmic events, such as galaxy formation and the development of large-scale structures. By factoring in these relativistic effects, we can refine our models, providing a clearer understanding of the universe's past, present, and future. This deeper understanding of time dilation allows us to peel back the layers of the universe's grand narrative, offering us a clearer view of distant cosmic events and enabling more accurate predictions about the universe's evolution. By considering how time behaves in various cosmic contexts, we can continue to refine our understanding of the forces shaping the cosmos, inching ever closer to a more comprehensive picture of the universe's vast, interconnected nature. The nature of time itself is one of the most profound questions in modern cosmology, particularly when it comes to the period before the Big Bang. According to the standard model of cosmology, the Big Bang marks not just the birth of the observable universe, but also the origin of time as we understand it. In this framework, asking what existed before the Big Bang is analogous to asking what lies north of the North Pole, a question that seems nonsensical within the very context of space and time itself. Einstein's general theory of relativity describes how mass and energy warp space-time, creating the conditions under which time as we know it began. In this view, time is an intrinsic property that emerged alongside the expansion of the universe. As such, discussing time prior to the Big Bang is, from a relativistic standpoint, meaningless. Time, as we measure and perceive it, is bound to the expansion of the universe itself, making it an inseparable part of the cosmos's evolution from that monumental event. Understanding time before the Big Bang is not merely a question of physics, but also a question of the limits of human knowledge. As our understanding of cosmology continues to evolve, we may one day develop new theories that offer insights into this mysterious realm. However, for now, it remains one of the most profound and speculative questions in the field, an enigma that pushes the boundaries of our comprehension of the universe and its origins. The quest to understand what happened before the Big Bang has led to some fascinating, albeit speculative, theories. One idea is the concept of a cyclic universe, where the Big Bang is merely one phase in an eternal cycle of expansion and contraction. In this view, our universe could be just one of many, with each cycle effectively resetting the conditions for a new Big Bang after a big crunch or similar event from a previous cycle. This cyclical model proposes that the universe experiences an endless loop of creation and destruction, with no true beginning or end. Another intriguing theory arises from the realm of quantum cosmology, especially through models like loop quantum gravity. According to this theory, the Big Bang may not have been a singular event, but rather a quantum transition from a prior state. These models suggest that time itself could have existed in a fundamentally different way before the Big Bang, structured in ways we might struggle to fully comprehend. For example, loop quantum gravity posits that the universe could have undergone a bounce, a process where a previous contracting phase reversed into the expansion we see today. This alternative conception of time and space challenges our classical understanding and proposes a universe that may have operated under entirely different laws before the Big Bang. String theory, with its multidimensional framework, adds another layer of complexity. In this speculative realm, our universe could be a brain, a multidimensional object existing within a higher dimensional space. According to this view, interactions with other brains could have triggered the Big Bang, offering a scenario where time itself only becomes meaningful within the context of a larger, more complex multidimensional space. The idea is that the universe's origin might be tied to a collision or interaction between higher dimensional objects, making the idea of before the Big Bang both speculative and elusive. While these theories offer extraordinary possibilities, it's essential to note that they remain largely speculative and far from being empirically verified. Our current understanding of physics and technology limits our ability to test these ideas definitively. In many ways, exploring such hypotheses is about pushing the boundaries of theoretical physics rather than providing concrete answers. The very concept of time before the Big Bang, if it even exists, forces us to rethink the fabric of reality itself, urging us to reconsider how we understand the cosmos and the nature of existence. As we continue to develop both theoretical frameworks and observational technologies, we may inch closer to unraveling these mysteries, possibly opening new frontiers in the study of time, space, and the universe itself. Exploring the idea of a multiverse further expands these boundaries, offering a plethora of models, each with its own interpretation of time. One prominent concept is the bubble universe model, tied to the theory of eternal inflation. This theory suggests that our universe is just one of many bubbles in an ever-inflating cosmic space. Each bubble could have its own timeline, independent of the others, and time in our bubble might flow differently compared to the timelines in neighboring bubbles. This raises fascinating questions about the nature of time. If each bubble's timeline operates in isolation, what would it mean for the progression of time in a multiversal context? Similarly, the many worlds interpretation of quantum mechanics adds a layer of complexity to our understanding of time. This theory proposes that every possible outcome of a quantum event actually occurs, but in separate, branching universes. Imagine time as a sprawling tree with countless branches representing different histories and possible futures based on quantum decisions. In this model, time is not linear but fragmented, splitting into endless possibilities, each with its own unfolding reality. String theory's brain multiverse model introduces another captivating perspective. In this framework, our universe is a brain floating within a higher dimensional space, and there may be other brains with their own universes. Time within each brain could function according to its own physical laws and conditions. The interactions between these brains might lead to collisions that create new universes with distinct timelines. Thus, the multiverse, as envisioned by string theory, presents a patchwork of realities where time behaves differently across each universe, offering a new way to think about the very nature of time itself. These speculative models, whether time is branching, bubbling, or bound to brains, stretch our imagination and offer new ways to think about the cosmos. They expand our understanding of the universe beyond its observable limits, suggesting that what we consider reality may be only a small piece of an infinitely larger puzzle. One of the most fascinating phenomena that existed in the earliest moments of our universe is quark-gluon plasma. Right after the Big Bang, the universe was a seething cauldron of fundamental particles so energetic that protons and neutrons broke down into their constituent parts, quarks and gluons. This state of matter, known as quark-gluon plasma, existed at temperatures reaching several trillion degrees Celsius, where quarks, the particles that form protons and neutrons, and gluons, the particles that hold quarks together, were free to move independently. This liquid-like state allowed these fundamental particles to interact in ways that are impossible in the matter we observe today. Where does this exotic form of matter exist now? Quark-gluon plasma is believed to have existed only in the first few microseconds after the Big Bang, before the universe cooled and condensed into the matter that makes up the cosmos we observe. This brief but crucial phase offers scientists insight into the extreme conditions of the early universe and provides a glimpse of how matter and the laws of physics functioned under these extraordinary conditions. In the quest to understand the universe, scientists have found a way to recreate conditions similar to the earliest moments of creation. High-energy particle colliders, like the renowned Large Hadron Collider in Europe and the relativistic Heavy Ion Collider in the United States, provide the ideal environments for these experiments. By smashing heavy atomic nuclei together at nearly the speed of light, these colliders generate intense energy, recreating conditions that existed just moments after the Big Bang. This process momentarily produces what is known as quark-gluon plasma, an exotic state of matter. Quark-gluon plasma is an incredibly hot and dense substance that allows physicists to study the fundamental forces and particles that shape the universe. By observing these brief flashes of creation, researchers unlock clues about how matter came to be. It's a tantalizing glimpse into the very building blocks of the cosmos, providing insights into forces and particles that continue to shape everything around us today. But quark-gluon plasma is just the beginning. There's another theoretical form of matter that is even more bizarre: strange matter. Unlike ordinary matter, which consists of up and down quarks that form protons and neutrons, strange matter is composed of strange quarks. These quarks give strange matter a unique set of properties that make it potentially even more stable than what we encounter daily. This makes strange matter particularly fascinating to scientists, especially in relation to its potential existence within neutron stars. Neutron stars are already one of the universe's most mind-boggling objects. These collapsed remnants of supernovae are incredibly dense, packing a mass greater than that of the Sun into a sphere no larger than a city. In fact, they are among the densest known forms of matter. In the intense environment of a neutron star, the extreme pressure could cause neutrons to break down, allowing quark matter to form. If strange matter can emerge under these conditions, it could lead to the creation of what scientists call strange stars, or quark stars. Strange stars would be distinct from regular neutron stars in several key ways. While neutron stars are made up of a dense core of neutrons, a strange star would have a core made entirely of strange matter, surrounded by a thin crust of normal matter. This unique structure could make strange stars even denser and potentially smaller than their neutron star counterparts. The increased density could also alter the gravitational field of these stars, affecting how they interact with their surroundings. These subtle differences might also manifest in the star's rotational behavior or its thermal emissions, offering valuable clues about the nature of matter in extreme environments. As researchers continue to study these enigmatic objects, they hope to unlock more secrets about how such extreme forms of matter could shape the evolution of stars and galaxies. The mysteries surrounding strange stars could offer unprecedented insight into the fundamental forces that govern the universe, expanding our understanding of the cosmos in ways we can only begin to imagine. But even more fundamental questions lie ahead, like the nature of symmetry and asymmetry in the universe. For decades, physicists have struggled to explain why there is so much more matter than antimatter. According to the symmetry principles of physics, the Big Bang should have created equal amounts of matter and antimatter. If that had been the case, the two would have annihilated each other upon contact, leaving only energy behind. However, this is not what we observe. Instead, the universe is overwhelmingly made of matter, with only trace amounts of antimatter. This imbalance is one of the greatest puzzles in cosmology. Some theories suggest that in the early universe, both matter and antimatter were created in equal quantities. This symmetry could have been disrupted in ways we don't yet fully understand, but it's a question that continues to drive research in the field of particle physics and cosmology. If symmetric matter once existed in the universe, then finding traces of antimatter should be possible. Yet, this elusive material remains largely absent from the observable cosmos. As scientists probe deeper into the nature of the universe, questions about strange matter, quark gluon plasma, and the mysteries of matter and antimatter will continue to fuel discovery. The answers could reshape our understanding of everything, from the fundamental particles that make up our world to the grandest structures of the universe. However, what we observe in the universe is something far more tangible: matter. Matter that creates galaxies, stars, planets, and essentially everything we know to exist. This observation, however, comes with a major puzzle: the imbalance of matter versus antimatter. The discrepancy between the two suggests that some unknown mechanism must have tipped the scales ever so slightly in favor of matter over antimatter. This break in symmetry is crucial because it gives us the universe we see today, where stars shine and planets can support life. Without this imbalance, the annihilation of matter and antimatter would have resulted in a universe devoid of the very substance we are made of, leaving behind only a barren, lifeless sea of radiation. This brings us to a concept known as asymmetric matter. It refers to the actual state of the universe, which is not perfectly balanced between matter and antimatter. To unravel how this imbalance occurred, scientists point to the era of baryogenesis, a brief moment shortly after the Big Bang. This period, marked by extreme temperatures and dense conditions, could have created the perfect environment for processes that favored the creation of more matter particles over antimatter particles. One of the leading theories attempting to explain this imbalance is charge parity, CP violation. CP violation suggests that the fundamental laws of physics are not entirely symmetrical. Specifically, when particles are swapped with their antiparticles and reflected in a mirror, subtle changes could have occurred. These changes would have caused an excess of matter over antimatter, which is what ultimately led to the universe as we know it today. If CP violation did indeed occur, it would mean that the laws of physics behaved differently for matter and antimatter, resulting in the dominance of matter in our universe. Understanding asymmetric matter is vital for answering one of the most profound questions in physics: why does the universe exist at all? If the matter and antimatter had been perfectly balanced, they would have annihilated one another, leaving no trace of the universe we now see. Instead, this asymmetry allowed for the formation of the stars, galaxies, and planets that fill our universe. This exploration is not merely academic. By studying these forces and conditions, scientists hope to gain profound insights into the very rules that govern the birth and evolution of the cosmos. Now, on a completely different cosmic front, there exists an enigma that continues to baffle astronomers: ultra-diffuse galaxies. These mysterious structures intrigue researchers because of their immense size and remarkably faint nature. Unlike typical galaxies, which are dense with stars and bright in their appearance, ultra-diffuse galaxies are spread out over vast regions of space, making them appear ghostly and hard to detect. What makes these galaxies so unusual? For one, they challenge our understanding of galaxy formation and evolution. One explanation lies in their high content of dark matter, the invisible substance that influences the motion of stars and gas within galaxies. These ultra-diffuse galaxies are thought to have a significantly higher ratio of dark matter compared to visible matter. This abundance of dark matter could be the key to why these galaxies remain gravitationally bound despite their sparse populations of stars. It explains their large size and low surface brightness, as dark matter exerts a gravitational pull that holds the galaxy together. Additionally, the formation history of ultra-diffuse galaxies could provide further insight into their strange properties. Some of these galaxies may have started life similarly to regular galaxies, but were stripped of much of their gas due to cosmic events such as interactions with nearby galaxies or explosive supernovae. These events could have halted star formation, leaving behind a skeleton of what could have been a thriving regular galaxy. Now, only a small number of stars remain, spread sparsely across a vast region of space. Globular clusters, spherical collections of stars, offer another piece of the puzzle. Ultra-diffuse galaxies have varying amounts of these clusters, which provide valuable clues about their origins. Some ultra-diffuse galaxies, such as those in the Coma cluster, are found to have an unusually high number of globular clusters. This suggests that these galaxies may have experienced different evolutionary processes compared to more typical galaxies. The presence and distribution of these clusters help astronomers understand the history of the galaxy and its interaction with the surrounding cosmic environment. In recent years, observations with advanced telescopes have allowed astronomers to uncover more about ultra-diffuse galaxies. Continued research promises to reveal even more about their formation, evolution, and the role that dark matter plays in shaping the universe. Understanding these galaxies is not just about solving a single mystery, it is part of the larger narrative of cosmic development. Ultra-diffuse galaxies serve as a reminder of the diversity and complexity of the universe, offering a unique glimpse into how the unseen forces like dark matter influence the structure of the cosmos. By studying them, we are also unlocking more about how galaxies in general form and evolve over time, helping to shed light on the intricate web of cosmic forces that have shaped the universe from the beginning of time. Dark fluid is a captivating and theoretical concept that sits at the crossroads of two of the most mind-boggling enigmas in modern cosmology: dark matter and dark energy. These two mysterious forces together account for about 95% of the universe's total mass energy content, yet they behave in fundamentally different ways. Dark matter is thought to exert gravitational pull, binding galaxies and ensuring that stars and gas remain anchored in place. Meanwhile, dark energy appears to be responsible for the accelerated expansion of the universe, driving it outward at an ever-increasing rate. But what if these two phenomena were actually part of a single unified entity? This is where the idea of dark fluid comes into play. Imagine a substance that could behave both as dark matter in certain regions and as dark energy in others, providing an elegant solution to some of cosmology's most perplexing questions. In areas where the density is high, such as within galaxies, the dark fluid would take on the properties of dark matter, creating the necessary gravitational forces to hold stars, gas, and galaxies together. In contrast, in the vast expanses of intergalactic space, where the density is incredibly low, dark fluid would behave more like dark energy, contributing to the force responsible for pushing the universe apart. This dynamic duality of dark fluid is where things get really interesting. It's as if dark fluid is a cosmic chameleon, able to adapt its properties to fit the environment. In denser regions, it clumps and pulls things together. In emptier regions, it pushes things apart. Such a theory could provide a more unified approach to understanding the universe, potentially simplifying the complex forces that govern our cosmos. However, detecting dark fluid is no easy task. It would require state-of-the-art observational techniques and sophisticated theoretical modeling to uncover its true nature. As researchers continue to focus on studying large-scale cosmic structures, galaxy rotation curves, and the history of the universe's expansion, future missions might one day provide the breakthrough needed to confirm the existence of dark fluid. If it turns out to be real, this concept could radically alter our understanding of the universe's composition and the forces that shape it. By offering a unified framework for dark matter and dark energy, dark fluid could revolutionize the way we think about the cosmos, bringing us closer to an elegant, all-encompassing theory of the universe. Parallel to this concept is another mind-bending idea: mirror matter. Mirror matter is a theoretical construct that suggests there might exist a parallel set of particles, each corresponding to a known particle in our universe, but with different properties. These mirror particles would interact extremely weakly with ordinary matter, making them nearly impossible to detect. However, they might still have a profound impact on the universe's dynamics. The idea of mirror matter stems from efforts to understand parity symmetry, a principle that deals with how physical processes behave under spatial inversion, essentially flipping the universe as if seen in a mirror. The potential implications of mirror matter are fascinating. One possibility is that it could explain some of the strange properties of dark matter. Although dark matter does not interact electromagnetically, making it invisible to current detection methods, it still exerts gravitational influence on visible matter. Mirror matter, interacting primarily through gravity, could behave similarly to dark matter, clumping around galaxies and influencing their rotational dynamics without ever being directly observed. This would make mirror matter a perfect candidate to explain some of the unseen forces that shape the universe. Mirror matter could also offer new insights into cosmic phenomena that have long puzzled astronomers, such as galactic collisions. If galaxies contain mirror matter, their collision dynamics could be very different from those involving only ordinary matter. Understanding this could shed new light on the formation and evolution of large-scale cosmic structures. Despite its potential, detecting mirror matter is incredibly challenging because it interacts so weakly with ordinary matter. Nevertheless, some researchers believe that mirror matter could occasionally interact with normal matter in rare processes, potentially leaving behind unique signatures that advanced detectors could pick up. The search for mirror matter could open entirely new avenues of research in both particle physics and cosmology. If mirror matter exists, it would suggest that the universe contains hidden symmetries and invisible components that influence the observable cosmos. Detecting and understanding mirror matter would not only deepen our knowledge of the universe's composition, but also refine our understanding of the fundamental laws of physics. The ongoing pursuit of mirror matter represents the next frontier in the quest to understand the mysteries of the universe, revealing hidden dimensions of reality that could fundamentally reshape our worldview. Bose-Einstein condensates are among the most extraordinary phenomena in the realm of physics, shedding light on the strange and often counterintuitive behavior of matter at its most fundamental level. Discovered at temperatures just above absolute zero, these condensates are named after the physicists Satyendra Nath Bose and Albert Einstein, who paved the way for understanding the bizarre nature of quantum matter. When particles known as bosons are cooled to an unimaginably low temperature, they begin to coalesce into a single unified quantum state. At this point, the individual particles cease to behave as separate entities and instead act as a single quantum object, exhibiting strange properties that blur the lines between the classical and quantum worlds. This behavior is profoundly significant, not only because it allows scientists to explore quantum mechanics on a macroscopic scale, but also because it opens up a unique vantage point into the quantum nature of our universe. The study of these condensates has become a critical tool for uncovering deeper truths about quantum mechanics, offering insight into phenomena like superfluidity, quantum coherence, and phase transitions, concepts that were once confined to microscopic scales. These discoveries, made visible through Bose-Einstein condensates, have the potential to reveal uncharted territories in our understanding of the very fabric of reality. When we look at the formation of Bose-Einstein condensates in the vast expanse of space, the implications for physics and technology grow even more profound. In microgravity environments, such as those found aboard the International Space Station, researchers can observe these condensates in ways that are impossible on Earth. Gravity's interference is a significant barrier on our planet, where the precision needed to maintain these delicate quantum states is easily disrupted. However, in space, this challenge is overcome. Bose-Einstein condensates can be sustained for far longer periods, allowing scientists to conduct more comprehensive and in-depth experiments, pushing the boundaries of our knowledge of quantum mechanics. This type of research could hold the key to unlocking some of the most fundamental questions of physics. For example, the way these condensates behave in zero gravity could provide valuable insights into the nature of quantum coherence and superfluidity, and could even offer clues to quantum phase transitions, phenomena that have yet to be fully understood. By studying these condensates, scientists may uncover new pathways to unify quantum mechanics and general relativity, potentially leading to a theory that can explain both the behavior of the very small and the very large. The potential applications of these findings are nothing short of revolutionary. Advancements in quantum computing, precision measurements, and sensor technologies could radically transform everything from global communications to navigation systems, creating a new era of technological progress based on the principles of quantum mechanics. Exploring Bose-Einstein condensates in space is more than just a scientific endeavor. It is a voyage into the heart of the universe itself. This convergence of quantum physics and cosmology allows us to peer deeper into the laws that govern both the minuscule and the cosmic, offering profound revelations about the nature of reality itself. Cosmic strings, while theoretical, are another captivating concept in modern physics. These one-dimensional defects, believed to have formed during phase transitions in the early universe, are akin to the cracks that form in ice as water freezes. Though we have yet to observe them directly, the idea of cosmic strings offers a tantalizing glimpse into the complex forces that shaped the early universe. These theoretical structures are predicted to possess immense mass and tension, stretching across unimaginable distances in space. If they do exist, they could have played a pivotal role in the formation of galaxies, influencing the way matter and energy clump together in the cosmos. The impact of cosmic strings on galaxy formation is tied to their extraordinary energy density, which would warp spacetime itself. This warping could create strong gravitational forces, attracting matter toward the cosmic strings. As these strings move through space, they could act as gravitational attractors, pulling gas and other matter into their vicinity. This process could seed the formation of galaxies by creating the necessary density fluctuations, which would eventually lead to the clumping and condensing of matter into stars and galaxies. In a sense, cosmic strings could serve as the scaffolding upon which the galaxies are built, providing the structure around which matter gathers and accelerates the formation of cosmic bodies. Cosmic strings could also influence the distribution of primordial matter in the early universe, particularly dark matter. These strings might have disturbed the otherwise uniform spread of dark matter and gas, creating areas of higher density that accelerated the collapse of these regions. This process could have further facilitated the formation of galaxies in the infant universe, essentially giving rise to the cosmic structures we observe today. The presence of cosmic strings, though still hypothetical, could leave detectable traces in the cosmic microwave background, CMB, the afterglow of the Big Bang. These anomalies or fluctuations could offer indirect evidence of cosmic strings, providing vital clues about their role in shaping the universe. The study of cosmic strings offers an exciting avenue for understanding the early dynamics of the universe. By exploring their potential influence on galaxy formation and the large-scale structure of the cosmos, scientists may unlock deeper insights into the fundamental forces that govern cosmic evolution. If cosmic strings are real, they could profoundly alter our understanding of the universe's birth and evolution. Lastly, dark atoms and dark photons present an intriguing frontier in the study of dark matter, suggesting that it may not be as exotic as once thought. Rather than being composed of unknown particles, dark matter might consist of elements that resemble ordinary matter, yet are invisible and undetectable by traditional means. Dark atoms and dark photons could help bridge the gap between the known and unknown, offering new ways to study and understand the mysterious, invisible matter that makes up much of the universe. Their exploration could lead to groundbreaking discoveries in physics, revealing new layers of the universe's hidden structure. The concept of dark atoms is a fascinating extension of our understanding of the universe, suggesting that, much like ordinary atoms, dark atoms are composed of particles bound together by forces. In the case of dark atoms, these forces would be mediated by dark photons, hypothetical particles that carry the dark electromagnetic force. Just as protons and electrons are held together by electromagnetic forces in regular atoms, dark matter particles would interact with each other through this analogous dark force. However, these interactions would be incredibly weak or possibly non-existent when it comes to ordinary matter and photons. Dark photons, in this context, would play a similar role to ordinary photons, mediating the dark electromagnetic force among dark matter particles. This hypothesis opens up exciting possibilities, suggesting that dark matter might be more intricate and structured than previously imagined. It could have its own set of interactions and internal dynamics, adding a layer of complexity to the dark sector of the universe. One of the intriguing implications of dark atoms and dark photons is that they could offer new insights into the formation and distribution of dark matter throughout the cosmos. While dark matter has long been understood to play a crucial role in the formation of galaxies, the concept of dark atoms implies that these particles could form their own structures, clustering under their own dark electromagnetic interactions. This clustering could influence galaxy formation in subtle yet significant ways, possibly leading to alternative models of how dark matter behaves and is distributed across the universe. This new understanding could help refine our models of cosmic evolution, giving us a more detailed picture of the forces that shape galaxies and their behavior. Detecting dark atoms and dark photons remains a formidable challenge for scientists, as these particles do not interact significantly with ordinary matter. However, researchers continue to look for indirect evidence through astrophysical observations and experiments designed to detect faint interactions between dark and regular matter. For example, anomalies in cosmic background radiation or the dynamics of galaxy clusters could hint at the presence of dark interactions, providing key clues about the dark sector. The notion of primordial black holes offers another fascinating avenue of research in cosmology. These hypothetical black holes would have formed in the very early universe, shortly after the Big Bang, and they differ from the black holes we typically think of, which are created when massive stars collapse at the end of their life cycles. If primordial black holes exist, they could significantly alter our understanding of dark matter and cosmic evolution. Unlike other candidates for dark matter, such as weakly interacting massive particles, WIMPs, primordial black holes are composed of ordinary matter, but they are incredibly dense and collapsed into singularities. If these black holes were abundant in the early universe, they could account for a substantial portion of dark matter. The gravitational influence of these black holes would shape the formation and evolution of galaxies and galaxy clusters, adding a new layer of complexity to our models of cosmic development. Moreover, primordial black holes could play a crucial role in the growth of supermassive black holes, which reside at the centers of galaxies. These ancient black holes could have acted as gravitational seeds, attracting matter and accelerating the formation of larger black holes over time. Understanding this process could offer profound insights into the rapid formation of supermassive black holes in the early universe, a phenomenon that has long puzzled cosmologists. Additionally, primordial black holes could leave detectable imprints in the cosmic microwave background radiation, the afterglow of the Big Bang. As these black holes formed and interacted in the early universe, they could have generated gravitational waves or other detectable signals, which advanced observational tools might be able to capture. By studying these signals, scientists could gain a deeper understanding of the universe's earliest moments, pushing the boundaries of our knowledge of cosmic history. The potential existence of primordial black holes could also influence the way we understand high-energy cosmic events, such as gamma-ray bursts and supernovae. If these black holes are involved in such events, they could provide critical insights into the mechanisms behind these phenomena, enhancing our understanding of their origins and nature. In essence, confirming the existence of primordial black holes could revolutionize our understanding of the cosmos, from the formation of galaxies to the nature of dark matter and beyond. Investigating these ancient relics could provide invaluable data about the universe's formative moments, offering a richer, more nuanced understanding of the intricate tapestry that makes up our cosmic history. In addition to dark atoms and primordial black holes, the enormous magnetic fields observed in some galaxy clusters represent another captivating puzzle for astrophysicists. These magnetic fields, which span millions of light years, are far stronger than those found within individual galaxies. Their presence suggests complex dynamic processes occurring on a cosmic scale. The origin of these colossal fields can be traced back to the early universe, where weak seed magnetic fields were generated by fluctuations in density and temperature. As the universe evolved, these seed fields underwent significant amplification through a process known as the dynamo effect. The dynamo effect involves turbulent motions of gas within galaxy clusters, which interact with the seed magnetic fields, gradually strengthening them over time. The resulting magnetic fields can reach enormous scales, like those observed in the most massive galaxy clusters today. The movement and interaction of galaxies within these clusters also play a key role in amplifying these magnetic fields. As galaxies collide and merge, they generate additional turbulence, which further fuels the dynamo effect, leading to the growth of these immense magnetic fields. The strength and scale of these fields offer a glimpse into the complex processes shaping the structure and behavior of galaxy clusters. Understanding how these magnetic fields form and evolve could provide deeper insights into the dynamics of the universe at large scales, from the earliest moments after the Big Bang to the present day. This ongoing investigation into the origins of giant cosmic magnetic fields promises to unlock new avenues of research in astrophysics, potentially reshaping our understanding of the forces that govern the universe. Galaxy clusters, vast collections of galaxies, each carry their own magnetic fields. As these galaxies move through space and occasionally collide, their magnetic fields can merge, stretch, and reshape. This dynamic process affects the overall magnetic structure of the cluster, creating an ever-evolving web of cosmic magnetism. The intracluster medium, the hot, ionized gas that fills the spaces between galaxies, also plays a crucial role in this transformation. As this gas stirs, it causes the magnetic field lines to tangle and stretch, amplifying the magnetic activity on a cosmic scale. Cosmic phenomena like active galactic nuclei, AGN, add another layer of complexity. These AGN, which sit at the centers of some galaxies, emit powerful jets of plasma and charged particles that travel at nearly the speed of light. As these jets propagate through the galaxy cluster, they drag magnetic fields with them, injecting turbulent energy into the surrounding medium. This turbulence strengthens and stretches the magnetic fields, contributing to their vast scale and strength. It's this process, helped along by the energetic jets, that provides the foundation for much of the cluster's magnetization. Scientists study these enormous magnetic fields to better understand the physical conditions and processes within galaxy clusters. Radio telescopes are crucial in this endeavor. They detect synchrotron radiation, a type of electromagnetic radiation emitted by charged particles spiraling along magnetic field lines. By mapping this radiation, astronomers can map the magnetic fields across clusters, offering crucial insights into the complex and dynamic interactions shaping our universe. These observations allow us to glimpse the role cosmic magnetism plays across the largest scales, influencing everything from the formation of stars and galaxies to the behavior of cosmic rays. Understanding the origins and evolution of these colossal magnetic fields helps us see not only the inner workings of galaxy clusters, but also the broader cosmic picture. Magnetic fields are not only involved in star and galaxy formation, but also in the behavior of high-energy particles, such as cosmic rays. These cosmic rays, charged particles traveling through space, are profoundly affected by magnetic fields, which act as guides, deflecting and altering their trajectories. The influence of these invisible magnetic structures is multifaceted. They not only change the paths that cosmic rays take, but also the energy these particles carry. The movement of charged particles like protons and electrons through magnetic fields causes them to spiral along field lines instead of traveling in straight lines. This spiraling is the result of the Lorentz force, the force acting on charged particles within a magnetic field. Depending on the strength and orientation of the field, this force can significantly alter the particle's speed and direction. As a result, cosmic rays can travel through space following complex twisting paths, loops, spirals, or even long detours across interstellar and intergalactic space. In galaxies and clusters, magnetic fields trap high-energy particles, confining them to intricate looping paths. In the Milky Way, the galaxy's magnetic field ensnares cosmic rays, sending them on a convoluted journey through the spiral arms and the interstellar medium. This scattering effect prolongs the time it takes for cosmic rays to travel across the galaxy, influencing the distribution and intensity of the cosmic radiation that ultimately reaches Earth. The study of these magnetic fields, from the smallest galaxies to the vastest clusters, allows us to unlock the mysteries of the cosmos. By understanding how these fields interact with cosmic rays, we gain insights into the broader processes that govern the universe, from the birth of stars to the acceleration of particles in the farthest reaches of space. In essence, cosmic magnetic fields are not merely background noise. They are central to the story of the universe, guiding particles, shaping galaxies, and revealing the underlying forces that govern the cosmos. Cosmic magnetic fields wield incredible influence over the behavior of high-energy particles, particularly cosmic rays, as they travel through the vast expanse of space. As these particles pass through regions with varying magnetic field strengths, they undergo dramatic transformations, subject to processes such as magnetic reconnection and shocks from supernova remnants or other energetic astrophysical events. These interactions have a dual nature. They can either accelerate particles to unprecedented energies or slow them down, resulting in a broad spectrum of cosmic ray energies that we observe today. However, the role of cosmic magnetic fields extends far beyond shaping energy. One of the most intriguing challenges they present is the deflection of cosmic rays from their direct paths. Due to this, tracing these high-energy particles back to their origins becomes an almost impossible task. Cosmic rays rarely travel in straight lines, making it difficult to pinpoint their sources, whether they are emitted by supernova, active galactic nuclei, or other cosmic accelerators. In the quest to understand these particles and their sources, unraveling the impact of cosmic magnetic fields is crucial. To study these interactions, scientists rely on a blend of advanced observational tools and direct detection instruments, many of which are deployed in space. Instruments like radio telescopes placed on Earth and space probes equipped with detectors provide invaluable data that help researchers map out magnetic field structures across the cosmos. These tools also measure cosmic ray properties, offering deeper insights into the dynamic relationship between magnetic phenomena and high-energy particles. With these data, astronomers can begin to decipher the cosmic dance of matter, energy, and magnetic forces, allowing them to better understand the forces shaping our universe. In addition to influencing the paths of cosmic rays, magnetic fields also reveal something profound about the universe's behavior on a grand scale. The magnetized filaments observed near the galactic center present another striking example of how magnetic forces shape the cosmos. These vast, elongated strands of magnetic fields, filled with cosmic plasma, stretch across tens of light years. Their origins remain a captivating mystery, drawing the attention of astrophysicists and astronomers alike, who have put forth several intriguing theories to explain their formation. One leading hypothesis centers on the supermassive black hole located at the heart of our galaxy, known as Sagittarius A Star. Although this black hole is largely dormant, it periodically erupts, releasing enormous amounts of energy in the form of powerful jets and outflows. These explosive events may distort and stretch the magnetic field lines in the surrounding region, forming the filaments we observe today. This dynamic interplay between the black hole's activity and the magnetic field can create the massive filament-like structures that puzzle scientists. Another possibility proposes that these filaments are the result of interactions between cosmic rays and magnetic fields in the galactic center. This region, brimming with high-energy particles from supernova explosions and stellar winds, provides a fertile ground for cosmic rays to interact with the turbulent magnetic environment. As cosmic rays traverse through this charged atmosphere, they can induce currents and amplify the magnetic fields, leading to the formation of these intriguing filaments. The relationship between cosmic rays and magnetic fields could thus be a key factor in shaping these structures. Ultimately, these cosmic magnetic fields not only influence the trajectories and energies of cosmic rays, but they also serve as a window into the deeper workings of our universe. By studying these fields and their interactions with high-energy particles, scientists are uncovering new layers of cosmic history, revealing the profound and complex interplay of forces that govern the vast expanses of space. The formation of magnetized filaments could be closely linked to magnetic reconnection, a process where opposing magnetic field lines break apart and reconnect, releasing vast amounts of energy. This fascinating phenomenon is observed regularly in the Sun's atmosphere and in other extreme astrophysical environments. At the heart of the chaotic, highly magnetized conditions in the galactic center, these magnetic reconnection events could play a pivotal role in stretching and aligning magnetic field lines, ultimately giving rise to the striking filamentary structures we observe. To unlock the mysteries of these filaments, detailed observations and studies are essential as they help us understand their origins and properties. Instruments like radio telescopes are invaluable for mapping the complex magnetic fields and detecting synchrotron radiation emitted by high-energy electrons spiraling around these magnetic lines. Such observations provide vital insights into the strength, orientation, and energetic processes occurring near the galactic center. Through continuous research and observation, studying these magnetized filaments not only sheds light on a specific cosmic phenomenon, but also enhances our broader understanding of magnetic fields, black hole activity, and high-energy astrophysical processes. By studying the extreme conditions in the heart of our galaxy, we begin to grasp the immense role that magnetic fields play in the formation and evolution of stars, influencing everything from the collapse of gas clouds to the later stages of a star's life. Magnetic fields are especially crucial during the early stages of star formation. As molecular clouds, dense regions of gas and dust, collapse under gravity to form stars, the magnetic field lines threaded through these clouds can either hinder or support the collapse process. Magnetic fields provide vital support against gravitational collapse by introducing magnetic pressure and tension, which can slow down the rate at which a cloud contracts. This regulation allows for a more gradual and controlled star formation, preventing a rapid collapse that could otherwise lead to excessive fragmentation of the cloud. As a protostar forms and evolves, magnetic fields continue to shape its development. A key role they play is in angular momentum transfer. As a protostar contracts, it spins faster. Without a mechanism to shed angular momentum, it could spin so rapidly that it would lose stability. Magnetic fields intervene by interacting with the surrounding accretion disk, channeling the excess angular momentum away from the star. This process ensures that the protostar can efficiently accumulate material from the disk while maintaining its stability. In addition, magnetic fields are responsible for the phenomenon of stellar winds and magnetic braking. Young stars often display intense magnetic activity, producing powerful stellar winds that expel material from their outer layers. These winds interact with the star's magnetic field, carrying away angular momentum and gradually slowing the star's rotation. This process helps explain why stars, including our Sun, rotate at relatively slow speeds despite initially spinning rapidly during their formation. In the later stages of a star's life, magnetic fields continue to influence stellar evolution. For massive stars, they can affect the behavior of the star's core and the distribution of elements within the star, impacting critical processes like nuclear fusion and the eventual supernova explosion. In smaller stars, magnetic activity often gives rise to phenomena like star spots, flares, and the production of X-rays, all of which significantly influence the star's magnetic environment and its interactions with the surrounding interstellar medium. The study of magnetic fields in the context of stellar formation and evolution involves a variety of observational techniques, including radio, optical, and X-ray astronomy. These methods allow scientists to map the magnetic field lines, measure their strengths, and observe how magnetic fields interact with stellar material. Magnetic fields are not only a fundamental and dynamic force in the universe, but they are intricately linked to the birth, life, and death of stars. From regulating star formation in molecular clouds to shaping the final stages of stellar evolution, these fields highlight the interconnected nature of cosmic forces and stellar processes. But the story doesn't end there. The magnetic anomalies observed on exoplanets provide an intriguing puzzle for scientists. These unusual magnetic fields are typically a result of the internal dynamics and composition of the planets themselves. To understand these anomalies, we must explore what happens inside these distant worlds. At the core of many planets, both within our solar system and beyond, lies a molten core composed of conductive materials like iron or nickel. When this molten core is in constant motion, it generates a magnetic field through a process known as the dynamo effect. The movement of molten metals creates electric currents, which in turn produce a magnetic field. This field can fluctuate and vary depending on the specific conditions inside the planet. Understanding the dynamo effect and the dynamics of planetary cores is essential for unlocking the mysteries of exoplanetary magnetic fields and their role in shaping the conditions on these distant worlds. Magnetic fields, particularly planetary ones, can be influenced by the dynamic interactions between their host planets and their parent stars. Exoplanets, in particular, which orbit in close proximity to their stars, often find themselves bombarded by intense stellar radiation and magnetic activity. This constant exposure can induce fluctuations or irregularities in their magnetic fields, creating a layer of complexity in the planet's magnetic behavior. These interactions between the planet's magnetic field and stellar forces can sometimes result in mysterious anomalies that add to the complexity of understanding exoplanetary systems. Moreover, it's important to consider that some exoplanets may harbor vast oceans of liquid water beneath icy surfaces or thick protective atmospheres. If these oceans are saline, they might create unusual magnetic signatures when subjected to tidal forces or other geophysical activities. These interactions could lead to magnetic anomalies that further complicate our understanding of planetary systems. The ongoing study of these anomalies and how they relate to the magnetic fields of exoplanets provides us with invaluable insights, not only into the nature of distant worlds, but also into the fundamental mechanics of magnetic fields themselves. As we move beyond planetary boundaries, we come to intergalactic magnetic fields, which, though subtle, play a significant role in shaping the large-scale structure of the universe. These vast fields stretch across the spaces between galaxies, permeating the cosmos and affecting the movement of charged particles. They also influence the formation and evolution of cosmic structures, guiding the behavior of energetic particles such as cosmic rays. As these high-energy particles move through magnetic fields, they spiral around the field lines, redistributing energy and matter in ways that would not occur if the fields weren't present. This redistribution can impact the growth of galactic clusters and the formation of even larger structures within the universe. Magnetic fields also have a profound impact on intergalactic gas, which is essential for star formation. The gas, as it moves through these magnetic fields, experiences resistance, which can either slow down or accelerate the process of star formation. Depending on the strength and orientation of the fields, they can cause the gas to clump together, eventually forming new stars or, in some cases, galaxies. This influence on star formation can significantly alter the evolution of galaxies over billions of years. In addition, intergalactic magnetic fields are crucial in the formation and behavior of cosmic phenomena, including the jets emitted by supermassive black holes. These jets, composed of ionized matter, are created and guided by magnetic fields, which shape their paths as they travel through vast stretches of intergalactic space. These powerful jets can carry energy and matter across enormous distances, playing an essential role in the distribution of energy throughout the universe's cosmic web. Though invisible to the naked eye, intergalactic magnetic fields act as an intricate cosmic tapestry, subtly guiding the formation of some of the most significant structures in the universe. These fields ensure that the architecture of the cosmos is not only shaped by gravity, but also by these enigmatic magnetic forces. Magnetic reconnection events in cosmic plasmas represent one of the most dynamic and significant phenomena in astrophysical studies. These events occur when oppositely directed magnetic field lines suddenly snap and realign, releasing vast amounts of energy. One of the most prominent examples of magnetic reconnection can be seen in solar flares and coronal mass ejections on our own sun. During these explosive events, the sun's magnetic field lines in the corona rapidly reorganize, unleashing bursts of energy that accelerate particles to nearly the speed of light. This process triggers powerful radiation bursts and creates dazzling light displays, such as the northern and southern lights when particles interact with Earth's magnetic field. Beyond the solar system, magnetic reconnection plays a pivotal role in the magnetosphere dynamics of planets like Earth. When Earth's magnetosphere, dominated by its own magnetic field, interacts with the solar wind, magnetic reconnection can occur at the boundary, transferring energy from the solar wind into Earth's magnetosphere. This process can lead to geomagnetic storms, disturbing satellite communications, power grids, and, in a more positive light, creating the beautiful auroras that light up polar skies. On an even larger scale, magnetic reconnection events affect cosmic plasmas found in environments such as accretion disks around black holes, the interstellar medium, and even in the formation of stars. These events can significantly alter the distribution of thermal and kinetic energy within these plasmas, influencing how they evolve over time. In essence, magnetic reconnection in cosmic contexts plays a key role in the dynamic processes that govern the development and behavior of the universe itself. In the vast reaches of space, magnetic fields wield an extraordinary influence on the dynamic behavior of cosmic plasmas. From the dazzling auroras that light up our night skies to the violent events surrounding supermassive black holes, magnetic reconnection is a fundamental process that shapes the energetic interactions of the universe. For astrophysicists, understanding this process is crucial for unraveling the mysteries of energy transfer across the cosmos. Magnetic fields aren't just abstract concepts. They are key forces that drive the behavior of interstellar dust and gas, fundamentally shaping the structure and evolution of the interstellar medium. These fields determine the way matter behaves and interacts within galaxies, influencing a variety of remarkable phenomena. One of the most significant impacts of magnetic fields is seen in star formation. In the dense clouds of gas where stars are born, these magnetic fields can exert a stabilizing influence against the immense gravitational forces attempting to collapse the gas. As the gas clouds try to condense and form stars, the magnetic fields slow down this collapse, moderating the rate of star formation and ensuring a more controlled, gradual process rather than an explosive one. Moreover, magnetic fields affect the alignment and polarization of interstellar dust grains, which play a key role in our understanding of cosmic structures. These dust grains, often elongated, can align themselves with the magnetic field lines of the surrounding space. As light passes through these dust clouds, it becomes polarized, a phenomenon that astronomers can measure to map out the strength and structure of these magnetic fields. This alignment not only allows scientists to study the magnetic architecture of the universe, but it also impacts the way light travels, affecting the radiation we observe from distant stars and galaxies. Magnetic fields also guide the movement of ionized gas within the interstellar medium. Charged particles, such as protons and electrons, trace the magnetic field lines, creating intricate and sometimes turbulent patterns. These motions give rise to complex filamentary structures within nebulae and other gas clouds. Additionally, strong magnetic fields can suppress certain instabilities in the gas, providing much-needed stability to these vast cosmic structures. In essence, magnetic fields serve as invisible architects, orchestrating the behavior of interstellar dust and gas, underlining many of the stunning and complex phenomena we observe across the universe. Whether it's controlling the rate of star formation, influencing light polarization, or shaping gas cloud patterns, these fields are essential in driving the evolution of the cosmos. Even deeper within the universe's history lies the concept of primordial magnetic fields. These ancient fields are thought to have emerged just moments after the Big Bang, during the universe's infancy. If these fields existed, they would have played a key role in shaping the earliest stages of cosmic evolution, influencing the formation of the large-scale structures we observe today. The origins of primordial magnetic fields are theorized to have occurred during the inflationary epoch, a brief but rapid period of expansion shortly after the Big Bang. During this time, quantum fluctuations could have expanded to macroscopic scales, imprinting magnetic fields that would permeate the early universe. Although these fields would have been faint by today's standards, they could have provided the foundational structures on which larger magnetic fields later grew. Another possible source of primordial magnetic fields arises from the phase transitions that occurred in the early universe. During these chaotic events, such as the electroweak or quantum chromodynamics phase transitions, the fundamental forces and particles of the universe began to take shape. As these transitions unfolded, turbulence and currents may have generated weak magnetic fields that spread throughout the universe. These nascent fields could have evolved over time, guiding the motion of charged particles and intergalactic gas, ultimately influencing the formation of galaxies and galaxy clusters. Though these primordial magnetic fields are believed to be incredibly weak compared to those generated by stars or galaxies, their impact was no less profound. These early fields may have set the stage for the larger, more powerful magnetic structures that would later form as the universe continued to evolve. Today, astrophysicists continue to study the role of these ancient fields, seeking to understand how they shape the universe as we know it, and how their legacy persists in the magnetic fields we observe in galaxies and intergalactic space. In the vast expanse of the universe, even the faintest magnetic fields can have profound, lasting effects. These subtle forces might have played a critical role in the formation of cosmic structures. As matter clumped together under the influence of gravity, forming the first stars and galaxies, primordial magnetic fields could have compressed and amplified, leaving an imprint on the magnetization of these structures. Alternatively, these fields might have served as a subtle, yet persistent, influence, shaping the dynamics of cosmic plasma over billions of years. Detecting these ancient magnetic fields is one of the most challenging frontiers in astrophysics. To uncover the faint traces of these primordial forces, scientists employ a range of observational techniques. One of the most promising methods involves studying the polarization of light from the cosmic microwave background, the faint afterglow of the Big Bang. Another technique, known as Faraday rotation, examines how light from distant galaxies is altered as it passes through magnetic fields, revealing subtle fingerprints of these ancient forces. Whether or not we can detect them, the very concept of primordial magnetic fields offers us a valuable window into the earliest moments of the universe's evolution. They help us understand the unseen forces that have shaped the cosmos into what we observe today, influencing everything from the formation of galaxies to the behavior of cosmic plasma. Magnetic fields play an essential role in the formation of jets emitted by active galactic nuclei. These incredibly energetic streams of particles that travel across vast distances of space. The jets, which can stretch for thousands or even millions of light years, are powered by supermassive black holes at the heart of active galaxies. These black holes, with their immense gravitational pull, drive the formation of these jets in a highly complex process. When matter falls into a black hole, it forms an accretion disk, a dense, spiraling region of material that heats up as it spirals inward. In this chaotic environment, magnetic fields emerge as one of the key players in the formation of the jets. The intense magnetic fields in the accretion disk are twisted and wound up due to the differential rotation of the disk, channeling particles away from the black hole's plane and along its poles. This process, known as the Blandford-Znajek mechanism, relies on the presence of strong magnetic fields to extract rotational energy from the black hole and convert it into kinetic energy, propelling the jets outward. Once the jets are launched, the magnetic fields continue to play a pivotal role. They provide a kind of scaffolding, helping to maintain the jets' structure and prevent them from dispersing too quickly. This is crucial for the jets to remain focused and narrow, enabling them to travel vast distances through space without losing their integrity. In addition, these magnetic fields help stabilize the jets against various instabilities, ensuring they don't fragment or lose their coherence over time. Moreover, magnetic fields within the jets can accelerate particles to relativistic speeds through a phenomenon known as magnetic reconnection. During this process, oppositely directed magnetic field lines break and reconnect, releasing a tremendous amount of energy. This energy release accelerates particles to speeds approaching the speed of light, leading to the emission of high-energy radiation, including radio waves, X-rays, and gamma rays. These energetic emissions make the jets observable across the electromagnetic spectrum, providing astronomers with a unique tool to study their properties and behavior in unprecedented detail. From their birth near the black hole to their journey across intergalactic space, magnetic fields are indispensable to the formation, acceleration, and stability of these powerful jets. Without them, the jets would dissipate before they could travel the incredible distances they do, robbing us of one of the most dramatic phenomena in the universe. In this way, magnetic fields illuminate the cosmos in awe-inspiring and powerful ways, offering us a glimpse into the very forces that shape the universe's most enigmatic and majestic features. In the early universe, dramatic cosmic phase transitions set the stage for the structure and dynamics we observe today. These transitions, triggered by shifts in temperature and density as the universe expanded and cooled, were pivotal in shaping the fundamental forces and properties of matter. As the universe evolved, these phase changes occurred during specific epochs, each marking a key moment in cosmic history. Understanding these transitions is essential for deciphering the origins of the universe, as they could hold the key to the very forces that govern our reality. One of the most significant phase transitions is thought to have occurred shortly after the Big Bang during what is known as the Grand Unified Theory, GUT-T epoch. In those early moments, the universe was incredibly hot and dense, with temperatures and energies far beyond anything we can imagine. During this time, it's hypothesized that the strong nuclear force, the weak nuclear force, and the electromagnetic force were unified into a single fundamental force. As the universe expanded and cooled, this single force is believed to have split through a phase transition, giving rise to the distinct forces we observe today. The energy released in this monumental event could have played a crucial role in the creation of magnetic fields and other cosmic phenomena, potentially setting the stage for the formation of the complex structures that would eventually emerge. A critical subsequent transition took place during the electroweak epoch, when the universe was only about 1,000th of a second old. During this brief yet crucial period, the unified electroweak force began to split into the electromagnetic force and the weak nuclear force. This process was marked by a dramatic shift in the Higgs field, which gained a non-zero value, giving elementary particles their mass. The energy released in this phase transition may have caused fluctuations in the primordial plasma, stirring turbulence that would go on to shape the formation of magnetic fields and influence the overall structure of the universe. Not long after, another significant phase transition occurred during the quantum chromodynamics QCD epoch, roughly 1 microsecond after the Big Bang. At this moment, the universe had cooled enough for quarks and gluons to combine, forming protons and neutrons, the very building blocks of atomic nuclei. This transition, often compared to the freezing of water into ice, represented a profound change in the state of matter. The effects of this transition extended beyond the immediate formation of protons and neutrons. It altered the thermal history of the universe, impacting the formation of matter and potentially laying the groundwork for the intricate cosmic structures that would later emerge. Each of these early phase transitions brought about profound changes in the very fabric of the universe. They were not merely fleeting events in cosmic history, but rather fundamental shifts that influenced the behavior of particles and the dynamics of the cosmos. As scientists continue to study these early cosmic moments, they are uncovering the forces and mechanisms that gave rise to the universe's vast and diverse structure. These transitions help us understand not just the past of our universe, but also its present form and future potential. One of the most intriguing aspects of the universe is the apparent fine-tuning of its fundamental constants, values like the speed of light, the gravitational constant, and the strength of the electromagnetic force. These constants are set with such precision that even the slightest deviation would make the formation of complex structures, such as stars, planets, and life itself, impossible. The question arises, why is the universe set up this way? One explanation lies in the anthropic principle, which suggests that we observe the universe as it is because, if it were any different, we would not be here to observe it. In other words, the only reason we can ask about the fine-tuning of the universe is because our universe supports life. If it didn't, no one would be here to wonder about its properties. Another explanation draws from the concept of the multiverse. According to this hypothesis, our universe may just be one of many, perhaps an infinite number, each with its own set of physical laws and constants. In such a diverse multiverse, it becomes statistically likely that at least one universe would have the right conditions for life. In this context, our universe is just one of the rare few where the constants happen to fall within the narrow range needed to support the emergence of complex structures and life. A third perspective considers the possibility that there are deeper, as yet unknown, laws of physics that dictate the values of these constants. Physicists are still searching for a theory of everything, a unified framework that explains not just the forces of nature, but why the constants of the universe are set as they are. If such a theory exists, it could reveal that the fine-tuning we observe is not a coincidence, but rather a natural outcome of underlying physical principles that govern the universe. In this view, the apparent precision of the constants could be the result of deeper, more fundamental laws that have shaped the very nature of reality. These hypotheses and explanations are more than just theoretical musings. They are essential pieces in the puzzle of understanding our universe. Each phase transition, each cosmic event, holds vital clues to the forces that shape the universe and continue to govern its evolution. By delving into these early moments of cosmic history, scientists aim not only to understand how the universe began, but also how it might evolve in the distant future. Some researchers propose a fascinating idea. What we perceive as fine-tuning in the universe might not be the result of some divine or unnatural force, but instead a consequence of our limited understanding. As we advance in fields like quantum mechanics, cosmology, and particle physics, new discoveries may shed light on how the constants and initial conditions of the universe are not just randomly aligned, but are part of inevitable processes that occurred during the early stages of the universe's development. While these theories differ in their approaches, they all grapple with one of the most profound and intriguing questions in cosmology. Are the conditions we observe a fluke of nature? Or is there a deeper, more systematic explanation behind it? Whether it's anthropic reasoning, the vastness of the multiverse, deeper physical principles, or potential truths waiting to be discovered, the question of fine-tuning continues to provoke thought and research, pushing us toward a more profound understanding of the cosmos. One theory that provides a fascinating perspective on the formation of the universe is cosmic inflation. This theory suggests that immediately following the Big Bang, the universe underwent a period of incredibly rapid expansion, expanding at an almost unimaginable rate in a fraction of a second. This rapid growth not only stretched space-time itself, but also smoothed out any initial irregularities, setting the stage for the universe as we know it. At the heart of this idea is the concept of a high-energy scalar field, often referred to as the inflaton field, which permeated the early universe. This hypothetical field drove the accelerated expansion, pushing space to expand exponentially. The field is described by a potential energy curve that governs its evolution over time. During the inflationary period, the inflaton field was in a state of extremely high potential energy, which caused space itself to expand rapidly, creating the vast universe we see today. But what triggered this explosive expansion? It likely began when regions of the inflaton field were displaced from equilibrium due to quantum fluctuations in the early universe. These fluctuations resulted in areas with excess energy, which, instead of collapsing inward due to gravity, caused space to expand outward. This rapid expansion continued until the field settled into a lower energy state. As it did so, the energy stored in the field was released, converting into particles and radiation, and reheating the universe. This process filled the universe with hot plasma, which eventually cooled down and formed the galaxies and cosmic structures we observe today. The theory of cosmic inflation provides elegant solutions to several long-standing problems in cosmology. It explains the uniformity and flatness of the observable universe and accounts for the slight density fluctuations that led to the formation of galaxies and other cosmic structures. These fluctuations, seeded by quantum effects during inflation, were stretched to macroscopic scales, laying the groundwork for the cosmic microwave background radiation and the large-scale structure of the universe. Although cosmic inflation remains a compelling theory, it is still an area of active research and debate. Physicists are looking for direct evidence to support it, such as the study of the cosmic microwave background or the search for primordial gravitational waves, which could provide further insights into this transformative phase in the universe's early history. Another intriguing scenario in cosmology is the Big Bounce theory, which presents a radically different view of the universe's history compared to the traditional Big Bang model. Instead of the universe beginning from a singularity, an infinitely dense point, The Big Bounce proposes that the universe undergoes a cycle of contraction and expansion. According to this model, the universe has experienced multiple phases of collapse and rebirth, oscillating between periods of contraction and expansion. Before the current phase of expansion, the universe would have been contracting, with galaxies and cosmic structures gradually moving closer together. As the universe contracted, its density and temperature would have increased dramatically. But instead of collapsing into a singularity, the contraction would reach a critical point where quantum gravitational effects or other speculative physical phenomena intervene. These effects would prevent the formation of a singularity, triggering a bounce, a transition from contraction to expansion. This bounce marks the beginning of a new cycle of expansion, and the physics behind it may involve new theories of gravity, such as loop quantum gravity, or modifications to general relativity that allow for a finite smallest scale in space and time. These theories offer a framework where the universe's density can approach a maximum without becoming infinite, thus avoiding the singularity predicted by traditional models. The Big Bounce theory, like cosmic inflation, offers a unique and captivating perspective on the universe's evolution, one that challenges our understanding of time, space, and the nature of the cosmos itself. In the quest to unlock the mysteries of the universe, both the inflationary model and the Big Bounce theory represent bold attempts to understand the forces and phenomena that shape the cosmos. As our knowledge expands, we may one day uncover the true nature of these processes, revealing deeper truths about the origins of the universe and the fundamental laws that govern its existence. In the intricate dance of the universe, the stored energy from the contraction phase of its previous cycle is transformed into expansive energy. This transformation propels the universe into its next cycle of growth, initiating an expansion phase that mirrors what we observe today. As the universe rebounds from its bounce, it enters a period of rapid expansion, very similar to the early stages of the Big Bang model. The remnants of the previous cycle, including thermal distributions and quantum fluctuations, continue to shape the early moments of this new phase. These remnants act much like the inflationary period of the Big Bang, seeding the universe with essential patterns and structures. As time passes, galaxies, stars, and cosmic structures begin to form, and the universe evolves in a way that closely resembles our current understanding, but always within the framework of an eternal cycle. One of the most intriguing aspects of the Big Bounce scenario lies in its philosophical implications. Unlike the Big Bang, which suggests a singular beginning, the Big Bounce proposes an infinite and cyclical cosmology. This model implies that the universe has no ultimate beginning or end. Each cycle is an opportunity for different physical properties and evolutionary paths for matter and energy. Such a perspective challenges our traditional view of the cosmos and introduces an entirely new way of thinking about time, existence, and the fate of the universe. To seek observational evidence for the Big Bounce, scientists might look to the cosmic microwave background, CMB, for patterns or imprints left by previous cycles. For example, unusual gravitational wave signatures could hold clues to the existence of past universes. While the Big Bounce remains speculative, it offers a fascinating alternative to the Big Bang model. If confirmed, it could provide profound insights into the true nature and destiny of the cosmos, reshaping our understanding of existence itself. Within the cosmos, one of the most valuable tools in understanding the universe's expansion is the study of baryon acoustic oscillations, BAOs. These oscillations, or sound waves, traveled through the hot, dense plasma of the early universe, leaving an imprint on the cosmic microwave background. These waves, created by gravitational forces, formed periodic density fluctuations in the primordial plasma. About 400,000 years after the Big Bang, conditions allowed photons and baryons, such as protons and neutrons, to decouple, and the sound waves essentially froze in place. The resulting temperature variations observable in the CMB act as imprints of these primordial sound waves. The significance of BAOs cannot be overstated. They serve as a cosmic ruler by providing a standard scale to measure the expansion of the universe. By comparing the observed scale of these oscillations in the distribution of galaxies, scientists can infer the rate of cosmic expansion. This measurement is essential for understanding dark energy, the mysterious force driving the accelerated expansion of the universe. BAOs also offer a unique method of cross-checking other cosmological measurements, improving our accuracy in determining the universe's geometry and the parameters that govern its evolution. In this way, BAOs provide a critical tool in the quest to unlock the secrets of the cosmos, including the nature of dark energy, the distribution of matter, and the very fabric of space-time itself. Turning to the birth and evolution of galaxies, the cyclic nature of star formation within galaxies forms another fascinating aspect of cosmic evolution. This cycle is driven by the interplay between the interstellar medium, the birth and death of stars, and the dynamic processes that occur within galaxies. Star formation begins in cold, dense molecular clouds made up primarily of hydrogen gas. These clouds, when they become gravitationally unstable, collapse under their own weight. External forces like shock waves from supernovae or gravitational interactions with neighboring galaxies often trigger this instability. As the clouds collapse, they fragment into smaller clumps, eventually forming protostars. These protostars evolve, heating up and igniting nuclear fusion in their cores, thus becoming main sequence stars. Stars, depending on their mass, can live anywhere from millions to billions of years, playing an essential role in shaping the galactic ecosystem. Massive stars, which have relatively short but intense lifespans, end their lives in supernova explosions. These dramatic events not only distribute heavy elements and byproducts of nuclear fusion into the surrounding interstellar medium, but they also generate shock waves that trigger new rounds of star formation. In this way, the cycle of stellar birth, death, and rebirth continues, perpetuating the evolution of galaxies over the course of billions of years. Ultimately, this cyclical process is not just a tale of stars, it's a story of the universe itself. Each new cycle builds upon the remnants of the last, ensuring that the cosmos remains ever-changing, ever-expanding, and perpetually in motion. Whether it is through the imprints left by the Big Bounce or the echoes of ancient sound waves, the universe is constantly unfolding, revealing more of its mysteries with every passing moment. The dynamic, cyclical nature of the universe suggests that perhaps the journey of cosmic evolution is never truly over, only ever unfolding, again and again, through infinite cycles of creation and rebirth. In the vast expanse of space, the cycle of star formation is an intricate and dynamic process, constantly fueled by a variety of cosmic forces. At its core, it begins with the material ejected by a supernova, which, combined with the radiation pressure and stellar winds from massive stars, injects enormous amounts of energy into the surrounding gas. This powerful energy compresses nearby molecular clouds, sparking new rounds of star formation. In a fascinating feedback loop, each generation of stars creates the necessary conditions for the next, ensuring that the cycle continues uninterrupted. Moreover, galactic dynamics play a pivotal role in shaping this cyclical process. The rotation of spiral arms in galaxies, for example, can compress interstellar gas as it flows into these regions, resulting in enhanced star formation rates. Additionally, the interaction between galaxies, whether through mergers or close passes, can disturb the gas within them. This disturbance often leads to bursts of star formation as compressed gas clouds collapse, fueling the birth of new stars. This cycle is far from simple. It is a delicate balance of gravitational collapse, stellar evolution, feedback mechanisms, and the forces at play within the galaxy itself. Together, these elements create a self-sustaining process where the birth and death of stars are in constant harmony. Not only does this process propel the growth and evolution of galaxies, but it also plays a crucial role in enriching the interstellar medium with elements necessary for the formation of planets, and potentially, life itself. Then, there's the fascinating event of reionization, a pivotal phase in the history of the early universe. This marked the period when the very first stars and galaxies began to form, transforming the dark, opaque cosmos into the transparent, luminous universe we observe today. Roughly 1 billion years after the Big Bang, the universe transitioned from the cosmic dark ages, when the universe was hot and dense, to a more organized state. During this time, protons, neutrons, and electrons combined to form neutral hydrogen atoms in a process known as recombination. This led to the decoupling of photons from matter, allowing light to travel freely and giving birth to the cosmic microwave background radiation. This event was nothing short of a transformation, changing the entire structure of the universe and setting the stage for everything that followed. Thus, the cycles of star formation, fueled by cosmic dynamics and interactions, not only create the building blocks for new stars and galaxies, but also the very foundation of life itself. However, the universe, after reaching a period of vibrant expansion and formation, entered what is known as the Dark Ages. This was an era when light-emitting objects such as stars and galaxies had yet to form. During this time, clouds of neutral hydrogen filled the vast expanses of space, shrouding the universe in darkness. It wasn't until reionization began that the universe started to emerge from this cosmic shadow. The first stars, galaxies, and quasars began to form through the gravitational collapse of these primordial gas clouds. The energy emitted by these early luminous objects, ultraviolet and X-ray radiation, was so intense that it was capable of ionizing the surrounding hydrogen, splitting it into protons and electrons once again. As more stars and galaxies continued to form, their radiation slowly permeated the intergalactic medium, progressively ionizing the hydrogen. This process not only made the universe transparent to light, but also marked a turning point in cosmic evolution. Reionization wasn't a uniform event. It occurred in patches across the universe. Ionized bubbles began to form around the first light sources. Over time, these bubbles expanded and merged, eventually enveloping the entire universe. The combined radiation from countless stars and galaxies ensured that neutral hydrogen remained ionized, allowing light to travel freely through the cosmos. The significance of reionization cannot be overstated. This epoch was not just a critical transformation in the transparency of the universe, but also laid the very foundation for the cosmic web we observe today, the vast network of galaxies, clusters, and superclusters. By studying the signatures of reionization, such as the absorption features in the spectra of distant quasars and the polarization of the cosmic microwave background radiation, astronomers gain invaluable insights into the timing and nature of this transformative period. Understanding reionization helps us unravel the history of the universe, from its dark, unlit beginnings to the structured, light-filled cosmos we experience now. As we dive deeper into the cosmic mysteries, one of the most profound and enigmatic questions remains: what is the evolution of dark energy? This elusive force drives the accelerated expansion of the universe and holds the key to determining its ultimate fate. Dark energy is still a mystery, and its nature could lead to dramatically different outcomes for the cosmos. One scenario, known as the lambda cold dark matter model, lambda CDM, suggests that dark energy remains constant over time, filling space uniformly with a constant energy density. If this is the case, the universe will continue to expand at an accelerating rate indefinitely. Galaxies will drift apart at ever-increasing speeds, eventually becoming so distant from one another that they will exist in isolation in a dark, cold universe. This scenario, called the Big Freeze, marks the eventual end of the universe as a cold, lifeless expanse. However, there are other possibilities. Dark energy might not be constant at all. In models involving dynamic dark energy, often represented by a hypothetical field known as quintessence, the energy density of dark energy changes as the universe evolves. If the strength of dark energy increases over time, the acceleration of the universe's expansion could intensify, leading to a scenario known as the Big Rip. In this catastrophic outcome, the force behind cosmic acceleration would become strong enough to tear apart galaxies, stars, planets, and even atomic structures. The very fabric of the universe could unravel, resulting in a violent end to all matter and energy. On the other hand, if dark energy weakens or decays over time, the expansion of the universe might slow down or even reverse. This could lead to the Big Crunch, a dramatic scenario where the universe, instead of expanding forever, starts to contract. Over billions of years, all matter and energy could collapse into an incredibly dense and hot state, possibly setting the stage for a new Big Bang, creating a cyclical model of cosmic rebirth. There is also the intriguing hypothesis of phantom energy, where dark energy's equation of state causes it to grow stronger with time. This would lead to even more violent expansions, driving the universe toward the inevitable Big Rip scenario. Under this model, everything in the cosmos would be torn apart as the universe expands exponentially. To determine which of these outcomes is most likely, scientists use observational data from supernovae, the cosmic microwave background radiation, and large-scale structure surveys. Future missions and telescopes are expected to refine our understanding of dark energy, providing crucial insights into the fate of the universe. As we delve deeper into these cosmic mysteries, we also find ourselves confronted with another fascinating puzzle: the apparent periodicity of mass extinction events on Earth. For decades, scientists have been intrigued by the possibility that these catastrophic events might be driven by regular, possibly cyclical, cosmic or terrestrial forces. Understanding these drivers is not just essential for piecing together the history of life on Earth, but also for grasping the complex interplay between our planet's biosphere and its broader cosmic environment. Each discovery sheds light on the delicate balance that sustains life on Earth, revealing the profound connection between our world and the vast universe beyond. In exploring the potential drivers of mass extinctions on Earth, one intriguing hypothesis connects the planet's movement through the vast Milky Way galaxy to these catastrophic events. Our solar system orbits the center of the Milky Way in a complex, roughly 200 million year cycle. As we travel through this cosmic expanse, the solar system occasionally passes through denser regions of the galactic disk, areas filled with interstellar dust and gas. This motion can potentially cause gravitational disturbances that may redirect comets from the Oort cloud, a distant zone of icy bodies surrounding our solar system, toward Earth. The increased impact from these comets and asteroids could trigger devastating climate shifts and widespread environmental disruptions, possibly setting the stage for mass extinction events. Another cosmic factor under consideration involves the powerful influence of nearby supernovae. These exploding stars emit intense radiation and energetic particles that could severely impact Earth's atmosphere. In extreme cases, the radiation could strip away portions of the atmosphere, leaving the planet vulnerable to hostile conditions. Although direct evidence linking supernovae to specific mass extinction events remains scarce, this remains an area of active and compelling scientific research. Supernovae may periodically expose Earth to lethal conditions, contributing to shifts in the planet's climate and environment, and possibly catalyzing the mass extinctions that punctuate our planet's deep history. Turning to Earth's own geological processes, it's clear that volcanic activity also plays a significant role in shaping the planet's extinction dynamics. Large volcanic provinces, triggered by the movements of plate tectonics, can release vast quantities of gases like sulfur dioxide and carbon dioxide into the atmosphere. These gases have the potential to rapidly alter the climate, causing cooling or heating effects, ocean acidification, and widespread ecological disruption. Additionally, the resurfacing of Earth's crust, driven by mantle plumes or other deep Earth processes, might contribute to these volcanic events. Some researchers suggest that the periodicity of extinction events could be influenced by a combination of factors, rather than a single dominant cause. The complex interplay between cosmic impacts, volcanic activity, climate oscillations, and biological factors could set the rhythm for these mass extinctions. While scientists debate whether a strict periodicity exists, the study of these forces highlights the interconnectedness of Earth's biological systems with its geological and cosmic environments. Understanding these dynamics not only sheds light on the historical patterns of life and death on Earth, but also reveals potential threats in our planet's future, providing insight into the resilience of life in the face of catastrophe. As our understanding of mass extinctions evolves, it becomes clear that cosmic phenomena like galactic magnetic field reversals could play a pivotal role in shaping these cycles. The galaxy's magnetic field isn't uniform, but instead exhibits complex structures, including areas where the magnetic field reverses direction. These reversals are caused by the dynamic processes of plasma movement and the rotation of the galaxy. When cosmic rays, high-energy particles from supernovae, active galactic nuclei, and other astrophysical events encounter these reversed magnetic fields, their paths are altered. Instead of traveling in a straight line, the cosmic rays spiral or twist along corkscrew trajectories. This bending of cosmic rays leads to a phenomenon known as cosmic ray diffusion, which scatters the particles and significantly slows their progress. As a result, cosmic rays take longer to traverse the galaxy and experience a random walk-like motion, making it nearly impossible to trace them back to their original sources. The study of mass extinction periodicity is an ongoing, multidisciplinary pursuit combining data from paleontology, geology, and astronomy. Each new discovery builds upon the last, helping scientists understand not just the past cycles of life and death, but also the possible threats we might face in the future. Through this research, we gain insight into the forces that have shaped and will continue to shape the history of life on Earth. Cosmic rays, the high-energy particles that traverse the vast expanse of space, are profoundly influenced by the magnetic field reversals that occur within our galaxy. These reversals play a crucial role in shaping the energy spectrum of cosmic rays, particularly in how they interact with the magnetic fields encountered during their journey. High-energy cosmic rays, those with greater momentum, possess the ability to navigate through magnetic field reversals with greater ease. Their paths remain more direct, as they are less susceptible to the deflection caused by the ever-changing magnetic forces. In contrast, lower-energy cosmic rays with less momentum are more prone to being deviated by these field reversals, which results in more complex and erratic paths through space. This phenomenon creates a fascinating energy-dependent propagation of cosmic rays, with the high-energy particles traveling more directly, potentially reaching Earth more quickly than their lower-energy counterparts. In addition to the directional shifts caused by magnetic field reversals, these disturbances can also lead to the trapping and confinement of cosmic rays within certain regions of the galaxy. As these cosmic rays become confined, they are subjected to a variety of interactions with their surroundings. One of the most notable of these is their collision with interstellar gas, which can result in the production of secondary particles and gamma-ray emissions. This process adds another layer of complexity to the cosmic ray spectrum that we observe here on Earth. The combined effects of magnetic field reversals, cosmic ray diffusion, and the resultant particle production contribute to the intricate and ever-changing nature of the cosmic ray environment, making it a fascinating subject of study for scientists striving to understand the processes occurring both within our galaxy and beyond. Understanding the behavior of cosmic rays in the presence of galactic magnetic field reversals is therefore essential to uncovering the larger picture of high-energy processes in space. These magnetic events cause significant deviations in the trajectories of cosmic rays, impacting their diffusion, energy distribution, and overall detectability. By studying these magnetic fields, scientists are slowly piecing together the complex journey of cosmic rays, shedding light on the high-energy phenomena that occur both within our galaxy and in the far reaches of the universe. Shifting our focus to the far-off reaches of Titan, one of Saturn's moons, we encounter a radically different environment that challenges our conventional understanding of life. Titan's surface is covered with vast lakes and seas of liquid methane and ethane, creating a strikingly unique environment for potential life forms. The extreme cold of Titan, with temperatures dropping below -290 degrees Fahrenheit, presents a series of obstacles to life as we know it. However, it also opens the door to fascinating possibilities for life that could thrive in these methane-rich, frigid conditions. In such an environment, life would need to rely on a chemistry vastly different from the water-based life forms we are familiar with on Earth. One of the most intriguing hypotheses posits that life on Titan-like worlds could utilize liquid methane as a solvent, replacing water in the biochemistry of life. This shift would require a fundamentally different approach to the molecular interactions that drive life processes, as the properties of liquid methane are unlike those of water. Methane, being a non-polar solvent, would facilitate entirely different types of molecules to dissolve and interact within it, compared to the water-based reactions that occur in Earth's biosphere. Furthermore, the membrane structures that are so essential for cellular function on Earth would need to be radically reimagined in a methane-based environment. On Earth, cell membranes are composed of phospholipid bilayers that function effectively in water. In the methane-rich seas of Titan, however, life forms would need to develop membrane structures composed of entirely different compounds. One possibility is the use of small, nitrogen-containing molecules called aotose, which would be stable and flexible in liquid methane. These novel structures would allow for the integrity of the cell membrane and enable the compartmentalization of biochemical processes, ensuring that life could function in this extreme environment. Metabolism, the process by which life forms harness energy, would also undergo a dramatic transformation in such a setting. On Earth, life forms rely on redox reactions involving oxygen and organic molecules to generate energy. On Titan, however, this process would likely be replaced by chemical reactions involving hydrogen, acetylene, and ethane. One particularly fascinating possibility is the existence of methanogenic life, which could combine hydrogen with acetylene to produce energy and methane. This process, though similar to some anaerobic reactions found on Earth, would be adapted to the unique chemical conditions of Titan, creating a stable biosphere in a world so unlike our own. In both the cosmos and the extreme environments of distant moons like Titan, the mysteries of life and energy are continually unfolding. By understanding the complex interplay between magnetic fields and cosmic rays, as well as the potential for life in radically different biochemistries, scientists are expanding the boundaries of what we know about the universe. As our knowledge grows, so too does our appreciation for the incredible diversity of conditions that can sustain life, whether in the vast stretches of intergalactic space or in the frozen methane seas of distant worlds. Exploring the potential of methane-based life and the biochemistry and ecology of such life forms significantly broadens our understanding of life's adaptability in the universe. Instruments on missions like the proposed Dragonfly drone, which aims to explore the surface of Titan, could be key to unlocking crucial data about these exotic environments. Studying these alien worlds could not only tell us whether such life forms exist, but also how they thrive, offering us a deeper understanding of life's broader potential in the cosmos. The possibility of life on Titan-like worlds would expand our definition of habitability beyond traditional Earth-based criteria, showing that life can evolve and adapt to conditions vastly different from those we know. The icy moons of our solar system, such as Europa, Enceladus, and Titan, present particularly exciting possibilities. These moons harbor subsurface oceans beneath thick ice crusts, creating environments that may be perfect for life. The key ingredients are all present: liquid water, energy sources, and the necessary chemical building blocks. The moons maintain their subsurface oceans in liquid form due to tidal flexing, which generates internal heat from gravitational interactions with their parent planets. Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn, experience this constant internal kneading, which prevents their oceans from freezing solid. This geological activity may also mean that these moons harbor hydrothermal vents on their ocean floors, similar to those found in Earth's deep sea environments. On Earth, hydrothermal vents are teeming with life, despite the extreme conditions, relying on chemosynthesis rather than photosynthesis. Microorganisms in these vents use chemical reactions involving compounds like hydrogen sulfide and methane to produce energy. If similar vents exist on the icy moons, they could provide a stable energy source and a rich chemical environment, potentially supporting microbial life. These deep-sea environments allow organic molecules to undergo complex chemical reactions, which could lead to the development of life. The thick ice crusts on these moons act as protective shields, guarding the subsurface oceans from harmful cosmic radiation and meteoric impacts. Within this safe cocoon, life could have the stability needed for lengthy evolutionary processes. The recent discovery of water plumes erupting from Enceladus and suspected plumes on Europa offers tantalizing evidence of dynamic processes beneath the ice, providing a way to sample these hidden oceans without needing to drill through kilometers of ice. On Titan, Saturn's largest moon, the possibility of life exists in a liquid water-ammonia mixture beneath its icy surface. The presence of ammonia lowers the freezing point of water, preventing the subsurface oceans from freezing despite the moon's frigid temperatures. This environment is chemically different from Europa's or Enceladus's water-based subsurface oceans, and it could support entirely unique forms of life that use ammonia in their biochemistry. The investigation into these subsurface oceans is now a primary focus for space missions like NASA's Europa Clipper, which is set to explore Europa's habitability. Future missions to Enceladus are also in the works. These missions aim to analyze the chemical composition of plumes, the ice surface, and other geophysical characteristics, searching for biosignatures or even direct evidence of life. The discovery of life in these distant subsurface oceans would profoundly impact our understanding of life's resilience. It would show that life could arise and persist in environments vastly different from Earth's surface, expanding the boundaries of what we consider habitable. Similarly, adapting to the extreme radiation environments around red dwarf stars presents unique challenges, but also opens up remarkable possibilities for life forms to adapt in ways we may not yet understand. Red dwarf stars, the most common type of star in our galaxy, are known for their volatile nature, frequently emitting powerful solar flares and bursts of radiation. Despite these challenges, planets within the habitable zones of red dwarf stars could theoretically sustain life, but that life would need to be extraordinarily resilient. On Earth, organisms like tardigrades and certain bacteria exhibit an incredible tolerance to radiation through mechanisms like efficient DNA repair systems and protective proteins that stabilize their cellular structures. Life on planets orbiting red dwarf stars might evolve similar or even more advanced biological repair mechanisms to cope with heightened radiation exposure. Additionally, these life forms might produce pigments or compounds that act as biological sunscreens, protecting them from ultraviolet radiation. Alternatively, life might find refuge underground or beneath thick layers of ice or water, using natural barriers as shields against harmful radiation. In this scenario, subsurface habitats on planets orbiting red dwarf stars could offer a stable, protected environment for life. Just as life on Earth thrives in extreme environments, like hydrothermal vents deep in the ocean or microbial colonies deep within the Earth's crust, similar niches might exist on planets orbiting red dwarf stars. Furthermore, life could adapt by becoming nocturnal or seeking shelter during periods of intense radiation. If a planet is tidally locked to its red dwarf star, meaning one side always faces the star while the other remains in perpetual darkness, life might thrive in the twilight zone or on the night side, where radiation levels are lower. These life forms could even develop circadian rhythms, adapting to the quieter periods of the star's activity, staying dormant or minimally active during peak radiation times. The potential for life to adapt and survive in such extreme and diverse environments highlights the incredible resilience of life in the universe and the boundless possibilities for discovering life beyond Earth. The more we learn about these distant worlds, the more we realize that life may be far more adaptable and widespread than we once thought. The search for life beyond Earth is not just about finding something alien. It's about understanding the full potential of life itself and how it might thrive in the most unexpected of places. In the mysterious realms of red dwarf stars, life may find ways to survive, evolving under conditions that challenge everything we know about habitability. Red dwarf planets, with their weak but persistent stellar radiation, might still foster life, especially if these planets have thick atmospheres filled with gases such as carbon dioxide or methane. These atmospheric layers could act as powerful shields, absorbing or deflecting harmful radiation from the star, making the planet's surface or the layers just beneath the atmosphere more hospitable for life. Such atmospheres would provide a critical protective barrier, allowing organisms to survive in the otherwise inhospitable conditions. However, it doesn't stop there. If the planet possesses a strong magnetic field, it could offer an additional layer of defense. Magnetic fields can divert cosmic and stellar radiation, providing further protection to any potential life forms. These complex planetary systems could potentially harbor life not only in the depths of their atmosphere, but even on the surface, in niches protected by both atmospheric and magnetic shields. Life, even in these extreme environments, would likely adapt in multifaceted ways, finding biological, ecological, or even geophysical strategies to cope with the challenges posed by the hostile radiation environment. Such resilience would highlight the remarkable adaptability of life, revealing just how resourceful life could be in the face of cosmic dangers. Understanding how life could adapt to these extreme environments is crucial for the search for extraterrestrial life. By studying the potential biological strategies that might evolve under red dwarf stars, we can refine our expectations of the forms life could take in diverse stellar environments. One possibility is the emergence of silicon-based life forms. These life forms would be fundamentally different from the carbon-based organisms we are familiar with on Earth, exploiting the unique chemical properties of silicon. While silicon chemistry is less versatile than carbon, it still offers fascinating possibilities for life in environments that would be inhospitable for carbon-based organisms. In high-temperature environments, such as the scorching surfaces of exoplanets or around geothermal vents, silicon-based life could thrive due to silicon's greater stability at elevated temperatures. These organisms might use silanes, which are analogous to alkanes in carbon chemistry, or silicon-oxygen compounds like silicates as the backbone of their biochemistry. Silicate-based biopolymers could form the structural and functional molecules of these life forms, potentially creating heat-resistant shells or exoskeletons similar to mineral-like structures that can withstand extreme conditions. Silicon-based life might also flourish in environments where traditional carbon-based life forms cannot survive. Places with scarce liquid water but abundant silicon compounds like the crusts of rocky planets or the icy moons rich in silicon. In these environments, life could thrive by using silicon to build complex molecules in the absence of water. Rather than relying on water as a solvent, these hypothetical organisms could use alternatives like liquid ammonia or even liquid methane to facilitate their biochemical processes, creating a unique metabolic system. The metabolic processes of silicon-based life forms would likely differ sharply from those of carbon-based organisms, possibly relying on energy derived from inorganic reactions involving silanes and oxygen. This energy-driven approach would be reminiscent of chemosynthesis seen in Earth's deep-sea ecosystems, but would be uniquely adapted to exploit the chemistry of silicon compounds. Ultimately, the very possibility of silicon-based life forces us to rethink our assumptions about the nature of life itself. While the challenges posed by the hostile environments around red dwarf stars seem insurmountable, these conditions may give rise to life forms that are strikingly different from anything we have ever encountered. The resilience and ingenuity required for survival in such environments would challenge our understanding of biology, pushing the boundaries of what is conceivable for life in the cosmos. Understanding these potential adaptations could guide future space exploration and open up new avenues in the search for extraterrestrial life. In environments with extreme radiation, such as planets orbiting red dwarf stars, or within high radiation zones of galaxy cores, life could take on forms vastly different from what we know on Earth. In these harsh conditions, organisms may evolve based on silicon rather than carbon as their foundational element. This shift could allow them to develop robust radiation-resistant mechanisms. Silicon's stronger bonds with oxygen, for instance, might offer enhanced stability under high radiation, reducing the likelihood of structural breakdowns that would be catastrophic for carbon-based life forms. These silicon-based life forms could employ additional protective strategies, such as radiation-absorbing outer layers or efficient repair systems, mirroring those found in Earth's extremophiles, which thrive in harsh environments. From a structural perspective, silicon-based life could exhibit diverse forms, from crystalline structures that grow and reproduce through the action of silicate materials to more fluid-based entities using silane or siloxane chemistry. This flexibility in chemistry could enable these organisms to move and adapt in ways that carbon-based life cannot. Their methods of communication and environmental interaction could also differ drastically. Rather than using the complex biochemical systems found in Earth's carbon-based life, these organisms might utilize mineral-based sensors or electrochemical gradients, facilitating communication and environmental sensing that is entirely alien to us. While the notion of silicon-based life remains speculative and has yet to be empirically verified, imagining these organisms challenges our understanding of life and opens up new possibilities for how life could exist across the universe. It urges us to consider how different forms of chemistry, far removed from Earth's carbon-centric model, could support life in extreme conditions, expanding our view of what constitutes life itself. Now, consider the idea of life surviving in the upper atmospheres of gas giants like Jupiter or Saturn. These environments present an entirely new set of challenges: extreme pressures, freezing temperatures, and intense radiation. Despite the severity of these conditions, the possibility of life in such realms is tantalizing, driven by the discovery of complex organic molecules and chemical compounds within these celestial bodies. How could life adapt to these challenges and thrive in the thick, dynamic clouds of gas giants? Let's explore. One of the most significant challenges for life in gas giants is the turbulent and ever-changing nature of their atmospheres. Organisms would need to possess extraordinary resilience, able to withstand rapid fluctuations in environmental conditions. To stay afloat in these shifting atmospheric layers, they might develop buoyant structures or gas-filled sacs. These adaptations would allow them to maintain a stable position at altitudes where conditions are more suitable for biological processes, akin to the buoyancy mechanisms employed by certain microorganisms in Earth's oceans. In such an environment, staying afloat could be key to survival. Energy acquisition in gas giants would also differ dramatically from solar-powered life forms on Earth. Without the luxury of sunlight, these organisms could turn to chemosynthesis, a process that involves harnessing energy from chemical reactions. Gas giants are rich in hydrogen, methane, ammonia, and other volatile compounds. Life could metabolize these chemicals much like the extremophiles on Earth that thrive around deep-sea hydrothermal vents, relying on the oxidation of substances like hydrogen sulfide or ammonia to fuel their biological processes. This form of life would be able to exist in the complete absence of sunlight, using the chemical wealth of their environment to power their survival. To endure the intense radiation and fluctuating environmental conditions, these life forms would likely need highly sophisticated protective mechanisms. Thick outer shells or complex molecular layers could protect them from harmful radiation. Similar to how some Earth microorganisms produce pigments to shield themselves from ultraviolet radiation, gas giant life might employ similar strategies to shield themselves from the planet's intense radiation belts. Their biochemical pathways could also be vastly different from life on Earth. While carbon serves as the backbone of life on Earth, gas giant organisms might rely on sulfur, nitrogen, or other elements abundant in their environments. These flexible and adaptive biochemical pathways could enable them to utilize the specific resources available, facilitating life in a way we have yet to fully comprehend. This speculation on silicon-based life and life within the gas giants challenges not just our understanding of biology, but also our place in the universe. As we continue to explore the cosmos, we are constantly confronted with the question, how can life exist under such extreme conditions? Through these fascinating possibilities, we inch closer to understanding the myriad ways life could manifest across the universe, whether in distant stars, within gas giants, or in environments we've yet to even imagine. The presence of organic molecules and the possibility of liquid water within the deeper layers of planetary atmospheres raise exciting prospects for life, especially in the vast gaseous expanses of gas giants. Even trace amounts of water, condensed into droplets or existing in its vapor form, could act as a vital solvent for biochemical reactions that might support life on a microscopic scale. Such possibilities are far from science fiction. Missions like NASA's Juno are actively probing Jupiter's atmosphere to gather data that could reveal signs of habitability, or more intriguingly, direct evidence of life. These efforts highlight an important aspect of astrobiology: the exploration of how life could adapt to the harsh and seemingly inhospitable conditions of gas giants, expanding our understanding of life's potential resilience and diversity across the cosmos. In binary star systems, where two stars orbit one another, the dynamics offer a complex yet stable environment for the possibility of life. These systems are particularly intriguing due to their intricate yet balanced habitable zones, regions where planets can orbit both stars, experiencing both stable energy sources and varying radiation patterns. This unique combination may create diverse environmental conditions, offering life the opportunity to adapt and thrive. One scenario in these systems involves planets in circumbinary orbits, where they revolve around both stars in wide, stable paths. Such planets, known as Tatooine planets, after the fictional world from Star Wars, would experience day-night cycles influenced by the dual suns. If the stars are sufficiently close, their combined energy could create a broad, stable habitable zone where liquid water and potentially life could exist. In such systems, the dual star setup could provide more consistent energy and light, fostering ecosystems capable of adapting to fluctuating luminosity. Meanwhile, another scenario presents planets in S-type orbits, where they orbit one star while experiencing periodic gravitational and radiation influences from the companion star. These planets would have highly complex seasonal and daily cycles, with fluctuating conditions that could challenge any life forms that might develop. Life here would need to be extraordinarily adaptable, possibly evolving organisms with flexible metabolisms capable of switching energy sources to meet the changing environmental conditions. Some life forms might even develop protective mechanisms to counteract the increased radiation during specific orbital phases. Binary star systems also harbor stable regions known as Lagrange points, where the gravitational forces of both stars balance the motion of a planet or moon. Objects within these Lagrange points could experience relatively stable conditions, providing potential niches for life. The combined energy from both stars might create environments that support hybrid photosynthetic processes or unique methods of energy utilization suited to the mixed spectrum of light and radiation. In more complex systems, binary stars of differing types, such as a main sequence star paired with a red dwarf, or a white dwarf and a sun-like star, could create environments rich with multiple energy wavelengths. Life could evolve to exploit these differing types of radiation, with organisms adapted to harness energy from the ultraviolet-rich light of a hotter star, or the infrared light from a cooler companion. In these systems, habitability would also depend on climate stability over geological timescales. With potentially longer periods of stability, these binary systems could support the complex evolutionary processes required for life to develop and thrive. The gravitational interactions within the system could also stimulate geological and atmospheric activity, replenishing planetary surfaces with essential minerals and gases that are crucial for biological processes. As research continues, aided by powerful telescopes and space missions, our understanding of these binary systems expands. The search for potentially habitable planets in binary star systems is opening up new avenues of discovery, illustrating the diverse ways in which light adapt to the complex and dynamic environments of the universe. Equally fascinating are rogue planets, also known as nomad or free-floating planets, that drift aimlessly through interstellar space without a star to orbit. The idea of life evolving on such isolated, starless worlds presents both a captivating and challenging concept. These planets, far removed from the comforting warmth of a star, would face extreme conditions. Chief among these is the absence of sunlight, a resource that is fundamental to life as we know it. Yet, in the most unlikely of environments, nature has a history of surprising us. Could life on a rogue planet find ways to survive in the dark? How might organisms adapt to a world where the heat of a star is but a distant memory? These questions remain central to the search for life beyond the traditional habitable zone and challenge our very understanding of the conditions necessary for life to thrive. Ultimately, these explorations, whether in the atmospheres of gas giants, the dynamic zones of binary star systems, or the cold emptiness of rogue planets, underscore one powerful truth. Life may not just exist within the comfortable confines of the familiar, but in the most unexpected and extreme environments of the universe. And as we continue to search, the possibilities grow ever more fascinating, revealing that the resilience and adaptability of life could be far broader and more varied than we ever imagined. However, life on rogue planets is far from a far-fetched idea. In fact, it's an intriguing possibility that sparks curiosity about how life might adapt and thrive in such unusual conditions. Rogue planets, which are planets that have been ejected from their parent star systems, offer some unexpected chances for life to take root. While they don't have the warmth and light from a nearby star, there are still several ways these planets could support life, even under extreme circumstances. One of the most critical factors is a substantial internal heat source. These rogue planets, much like Earth, can retain heat generated by the decay of radioactive elements within their cores. Even without the comforting warmth of a parent star, this process could keep a rogue planet warm enough to support liquid water beneath an icy crust. The planet's interior heat may also be augmented by gravitational interactions with other celestial bodies before the planet was ejected from its original orbit. This residual geothermal energy could keep subsurface oceans in a liquid state, potentially providing an environment where life might thrive in the dark, beneath thick layers of ice. In such a scenario, life would have to rely on chemosynthesis rather than photosynthesis. Similar to extremophiles on Earth, which thrive near hydrothermal vents, life forms in these sub-ice oceans might exploit geothermal vents, utilizing chemical reactions involving sulfur and other minerals to survive. In fact, these geothermal vents could become the center of microbial life, where organisms tap into the planet's internal heat and mineral-rich environment. Just as deep-sea ecosystems on Earth rely on the chemical energy found in underwater vents, rogue planets could host ecosystems that function without sunlight, focusing entirely on chemical energy from the planet's core. These life forms would exhibit extraordinary biochemical adaptations, enabling them to survive in harsh, starless conditions, harnessing energy in ways we might not yet fully understand. Another fascinating aspect of rogue planets is the potential for thick, insulating atmospheres. A dense atmosphere, rich in greenhouse gases such as carbon dioxide and methane, could trap heat generated from the planet's core, creating a stable, warm environment on the surface or just beneath a thick layer of ice. This atmospheric insulation would mimic Earth's greenhouse effect, but without the need for sunlight. Instead of relying on solar radiation, these planets could maintain conditions that allow for liquid water and, consequently, life. Moreover, these thick atmospheres could shield any potential life forms from harmful cosmic radiation, providing a stable environment that could foster biological processes similar to those found in more hospitable environments in our own solar system. In another possibility, rogue planets might carry biospheres with life that originated while the planets were still part of a star system. These planets could have been ejected with existing ecosystems, and over time, life forms might evolve specialized mechanisms to cope with their new starless existence. Life might rely on stored chemical energy, bioluminescence, or other metabolic pathways that don't require sunlight. Organisms might even evolve the ability to generate their own light through biochemical processes, a fascinating adaptation that would enable them to survive in the cold, dark world of a rogue planet. Lastly, life on rogue planets could be influenced by the concept of panspermia, the idea that life or its building blocks could travel between planetary bodies. Microbial life could hitch a ride on comets, asteroids, or even cosmic dust, seeding rogue planets with the necessary components for life. If a rogue planet passed through a region rich in organic molecules, it could capture these building blocks and foster the development of complex chemical processes essential for life. In this way, rogue planets could act as unexpected cradles for life, even if it wasn't initially native to the planet itself. Despite the incredibly harsh conditions on rogue planets, life could potentially adapt in extraordinary ways. Whether through exploiting internal heat sources, relying on chemosynthesis, taking advantage of thick atmospheres, or being seeded through panspermia, life might find ways to survive and thrive. This resilience demonstrates the remarkable adaptability of life, offering new perspectives on the vast potential for life in diverse cosmic environments. By studying rogue planets, we push the boundaries of our understanding of life's capacity to survive under the most unlikely conditions, broadening our search for extraterrestrial life and revealing the incredible possibilities that exist beyond the stars. Super-Earth exoplanets, planets larger and more massive than Earth but smaller than ice giants like Neptune, present an entirely different set of intriguing conditions that could also foster life. These massive planets, with their intense gravitational forces, create environments where life forms would have to adapt in ways we can scarcely imagine. The extreme pressures on super-Earths could give rise to unique forms of life, requiring extraordinary biochemical and physiological traits. One potential environment on super-Earths is deep, high-pressure oceans. These oceans could extend hundreds of kilometers beneath the surface, vastly deeper than Earth's oceans, which are only about 11 kilometers deep at their most extreme point. Within these pressurized environments, life forms would need to develop structural and biochemical adaptations to survive. Just as extremophiles on Earth thrive in the crushing depths of our oceans, life on super-Earths could evolve cellular structures reinforced with pressure-resistant proteins and membranes to ensure biological processes remain stable. These organisms might rely on chemosynthesis, using chemical reactions from hydrothermal vents to power their metabolic processes and form the base of complex food webs, just like life at Earth's deepest oceanic trenches. Surface life on super-Earths would also face the challenge of the planet's immense gravity, which could be several times stronger than Earth's. To support their own weight and avoid collapsing under this pressure, life forms would likely evolve shorter, sturdier bodies. Their cellular structures would need to be reinforced, perhaps incorporating denser biomaterials or novel molecular frameworks that can withstand the stress of the planet's gravity. Life forms on super-Earths might possess compact, reinforced skeletal or exoskeletal systems, allowing them to thrive in these high-pressure, high-gravity environments. The adaptability and resilience of life in these extreme conditions would push the boundaries of what we know about biological survival, offering new perspectives on life's potential across the universe. In the vast expanse of space, the possibility of life evolving on exoplanets with environments vastly different from Earth challenges our understanding of biology. When we look at super-planets, worlds with thick, dense atmospheres, a truly fascinating picture of survival begins to form. Life on these planets would have to contend with atmospheric conditions far more extreme than anything we experience. However, the adaptability of life is boundless. The atmosphere of a super-R could be enriched with various gases, creating conditions where life forms may evolve specialized mechanisms for breathing or metabolizing under intense pressure. Respiratory systems, for instance, might be adapted to efficiently extract oxygen or other critical gases, even under immense atmospheric pressure. In such a dense atmosphere, the presence of greenhouse gases, such as carbon dioxide or ammonia, could reshape metabolic pathways in unexpected ways. Life might exploit these compounds chemically in ways we can only begin to imagine. In regions where solid surfaces and deep oceans interact, places where water meets rock, life could evolve along the edges of these extremes, utilizing mineral-rich vents for energy. These niches could give rise to entirely new forms of biofilm or microbial mats, capable of withstanding the dual pressures of rock and ocean. These ecosystems, although similar to Earth's deep-sea vent communities, would have to adapt to even more extreme conditions. The complex interactions at these interfaces could provide fertile ground for life to thrive, developing unique forms of metabolic activity. The life on super-R exoplanets would not only need to survive in high-pressure environments, but also withstand immense gravitational forces. This would require adaptations that go far beyond our understanding of cellular structures on Earth. Life forms might develop pressure-resistant cellular structures or completely novel metabolic processes. Such adaptations would be crucial in these high-pressure worlds where even basic survival would demand extraordinary resilience. Investigating these possibilities is not just a scientific endeavor, it's essential for broadening our understanding of the vast potential diversity of life forms and their remarkable ability to adapt. Similarly, the prospect of life on planets orbiting neutron stars, remnants of supernova explosions, opens a door to even more extreme survival strategies. Neutron stars, with their staggering density and powerful gravitational fields, represent some of the most hostile environments in the universe. These stars emit intense radiation, including X-rays and gamma rays, creating an environment unlike anything life on Earth could endure. Life in such an environment would have to be radically different, built to withstand forces and conditions that seem almost beyond the realms of possibility. The immense gravity of a neutron star would impose enormous pressure on potential life forms. To avoid being crushed, organisms might evolve highly compact, robust body structures. Their size could be drastically reduced, and their cellular structures might be reinforced by incredibly strong molecular bonds, far stronger than anything seen in earthly organisms. But the challenges don't stop at gravity. The intense radiation emitted by neutron stars would require life forms to develop unprecedented mechanisms for survival. On Earth, certain microbes, like Deinococcus radiodurans, can repair DNA damage caused by radiation at remarkable speeds. Life on a neutron star planet could push this ability to an extreme, perhaps even evolving entirely new molecular processes for radiation protection and DNA repair. To survive this level of radiation, life might develop thick radiation-absorbing exteriors, possibly composed of materials similar to those used in radiation shielding. This would serve as a protective barrier against the constant barrage of harmful radiation. Some life forms might even turn the radiation to their advantage, evolving to use it as an energy source. This hypothetical process, known as radiotrophic biology, could involve organisms harnessing the radiation itself, converting it directly into usable biochemical energy. This would be akin to how some Earth organisms, like certain fungi, use chemical energy from decaying matter in the process of chemosynthesis. In this case, life would have evolved to exploit the very forces that would otherwise destroy it, creating a radically different form of energy production that challenges our ideas of how life can function in extreme environments. Exploring the potential for life on these types of exoplanets opens up a new frontier in astrobiology. As we push the boundaries of what we know about life's resilience, we gain insight into how life could thrive in the most unexpected and extreme conditions, reshaping our search for biosignatures and deepening our understanding of life's vast potential across the universe. Neutron stars, with their extreme gravitational forces and intense magnetic fields, present a tantalizing yet hostile environment for life. These magnetic fields, often strong enough to influence surrounding space, might offer unique challenges and opportunities for hypothetical organisms. Life on planets orbiting such stars could evolve to shield itself from these intense fields, or conversely, harness their power. Imagine organisms developing magnetically aligned structures that allow them to navigate these magnetic forces, or even finding ways to convert magnetic energy into biochemical energy. On Earth, certain bacteria known as magnetotactic organisms already align with Earth's magnetic field, hinting that such mechanisms could exist elsewhere in the universe. But it's not just about the magnetic fields. The surface of a neutron star's planet would likely be inhospitable, bathed in radiation, and subjected to unpredictable gravitational shifts. However, life could take refuge beneath the surface, where extreme conditions are more manageable. Just as some extremophiles on Earth thrive deep within the planet's crust, organisms on these distant planets might live in subterranean shelters. They could find sanctuary in underground pockets, insulated from the hostile environment above, and survive by using heat from within the planet itself. These organisms could rely on chemosynthesis, converting minerals from the planetary crust into energy, much like life forms that thrive near Earth's deep-sea hydrothermal vents. Considering these extreme environments, one can't help but marvel at the adaptability and resilience of life. While these possibilities remain speculative, they urge us to expand our understanding of what life might look like in the universe. They challenge us to imagine life in places where survival seems nearly impossible, pushing the boundaries of what we once thought was biologically feasible. Such scenarios not only enrich our knowledge of life's potential, but also fuel our quest to explore and understand the farthest reaches of the cosmos. In a similar vein, the idea of life existing in the subsurface oceans of Pluto-like objects in the Kuiper Belt offers an equally fascinating possibility. Though the surface of these objects is incredibly cold, with temperatures plummeting to near absolute zero, the oceans beneath a thick, icy crust could offer a relatively stable environment for life. Geological evidence suggests that heat generated from radioactive decay or tidal forces, if the objects have moons or experience gravitational interactions with nearby bodies, could maintain liquid water beneath the ice. This water could serve as a sanctuary for life, providing a habitat where conditions, although dark and cold, are stable enough for life to thrive. Within these subsurface oceans, life forms could resemble Earth's deep-sea extremophiles, particularly those found around hydrothermal vents. These organisms rely on chemosynthesis, using the energy from chemical reactions such as those involving hydrogen sulfide or methane rather than sunlight to fuel their growth. Similarly, life in these icy ocean worlds might thrive by tapping into the minerals from hydrothermal venting or other geothermal processes. These deep, dark oceans could host rich ecosystems despite the lack of sunlight. The chemistry of the water in these subsurface oceans is another crucial factor. If compounds like ammonia are present, they could act as antifreeze, lowering the freezing point of water and preventing it from turning to ice. This would allow liquid water to persist even in an extreme cold. Such conditions could give rise to life forms with entirely different biochemistries, organisms that could use ammonia in their metabolic processes where traditional biological molecules would freeze and fail. These unique adaptations could enable life to flourish in ways we can't yet fully imagine. Energy sources in these alien oceans could come from more than just chemical reactions. Hydrothermal activity might provide both heat and nutrients, fueling life in a way that mirrors the ecosystems found around Earth's deep-sea hydrothermal vents. Furthermore, organisms in these dark, isolated worlds might evolve bioluminescent capabilities, using their own light for communication, navigation, or even to attract prey. Life on these icy worlds could be unimaginably different from anything we have on Earth, but its existence would push the limits of what we consider possible for life in extreme environments. As we continue to explore the potential for life on other planets, these speculative scenarios not only expand our understanding of the universe, but also deepen our appreciation for the astonishing versatility and resilience of life itself. Whether it's surviving in the magnetic fields of neutron stars or thriving in the cold, dark oceans of distant Pluto-like objects, life is capable of more than we can yet comprehend. Exploring these possibilities challenges us to rethink the boundaries of life and to look for signs of it in places we might have once thought too extreme to sustain it. The journey to understand life's potential is just beginning, and the possibilities are boundless. In recent years, intriguing studies have suggested that some Pluto-like objects may experience episodic cryovolcanism, a phenomenon where liquid water or icy slurries are periodically ejected to the surface. These dramatic events could expose subsurface materials to the harsh outer environment, creating temporary windows for potentially fascinating biochemical interactions. The key to this lies in the possibility that life forms could evolve mechanisms to survive these cycles, enduring harsh surface exposure before retreating back to the safety of subsurface habitats during more stable periods. Such discoveries raise questions about the potential for life to adapt and thrive in environments previously thought too extreme. Missions to explore the outer reaches of our solar system, including the moons Europa and Enceladus, or even Pluto itself, could provide invaluable insights into these distant and isolated environments. Instruments designed to detect biosignatures, such as specific organic molecules, isotopic ratios, or geological formations shaped by biological processes, could help determine whether the subsurface oceans of Pluto-like bodies might harbor life. The idea that life could flourish beneath thick ice layers in cold, dark, and chemically rich waters challenges our very understanding of habitability. It also pushes the boundaries of where we might find life, not only within our solar system but beyond it in the vast expanses of space. These subsurface oceans offer a tantalizing possibility that life could adapt to the most extreme and isolated conditions imaginable. The life forms that might exist in these frozen oceans would likely be strikingly different from those found on Earth, exhibiting remarkable biochemical and physiological adaptations. They could survive in the cold, under layers of ice, relying on chemical-rich environments to sustain them. The study of these potential habitats broadens our definition of what makes a place habitable, offering a fresh perspective on life's resilience and its potential to thrive in the darkest, most challenging environments. Meanwhile, the ultimate fate of black holes in an expanding universe presents a different kind of mystery, one that brings together general relativity, quantum mechanics, and cosmology in an intriguing dance. While black holes are famous for their immense gravitational pull, they are not exempt from the passage of time or the universe's endless expansion. One of the most widely accepted theories about their eventual end is linked to Hawking radiation, a quantum mechanical phenomenon proposed by physicist Stephen Hawking. This theory suggests that black holes emit radiation due to quantum fluctuations at their event horizons, where particle-antiparticle pairs spontaneously form. One particle falls into the black hole while the other escapes, causing the black hole to gradually lose mass over time. Though the process is incredibly slow for massive black holes, it ultimately leads to their gradual evaporation. As the black hole shrinks, it loses mass at an accelerating rate, culminating in a rapid and intense burst of radiation before it disappears entirely. This theoretical process, known as black hole evaporation, would mark the final stage in the life of these cosmic giants. However, this theory remains a subject of intense study and debate, and whether it holds true for all black holes is yet to be determined. What is certain, however, is that the fate of black holes is intricately tied to the fundamental forces of the universe, and understanding this process could open new doors in our quest to grasp the true nature of time, space, and the cosmos itself. In an ever-expanding universe, the future of black holes presents an intriguing and complex picture, especially as cosmic acceleration, driven by dark energy, continues to increase. The timescale for this process stretches far beyond the current age of the universe, perhaps even surpassing its lifespan. In this future, black holes will find themselves in a progressively isolated environment as galaxies drift farther apart. As this isolation deepens, the density of the surroundings decreases, reducing the available material for black holes to accrete. Their fate will no longer be influenced by external forces, but instead by internal mechanisms such as Hawking radiation, a quantum process that will guide their ultimate demise. As we look even further into the distant future, a time beyond the evaporation of black holes, the universe may enter a phase known as the heat death, or the Big Freeze. In this scenario, the universe would continue expanding indefinitely, and galaxies, stars, and other celestial bodies would drift apart. The remnants left behind would be cold and dark, the product of countless eons of entropy, where the energy within the universe has been dispersed. Following the evaporation of all black holes, the universe will become an immense, sparse expanse, devoid of significant sources of energy. The universe will be filled with low-energy particles and radiation, reaching a state of maximum entropy. Here, the cosmos will enter a final, still phase, with no discernible movement or interaction left to witness. However, alternative cosmological models offer different potential fates for both black holes and the universe. One possibility is the Big Rip, where the accelerated expansion of the universe eventually tears apart all cosmic structures. In this scenario, everything from galaxies to atoms could be shredded as dark energy pushes the universe apart with ever-increasing force. Another possibility is the Big Bounce, a cyclical model in which the universe contracts in a big crunch, only to rebound and initiate a new cycle of expansion. Under such scenarios, the role of black holes and their fate would change, depending on the dynamics and properties unique to these models. While much about the distant future remains speculative, the prevailing understanding suggests that black holes will ultimately meet their end through Hawking radiation, contributing to the final stages of an increasingly cold and isolated universe. This process reflects the profound intersection of quantum mechanics and cosmology, offering a glimpse into the long-term evolution of some of the most enigmatic objects in the cosmos. As dark energy continues to accelerate the expansion of the universe, its implications for galaxy formation and the broader structure of the cosmos will become increasingly significant. In the far future, as the universe expands at an ever-accelerating pace, galaxies will become increasingly isolated from one another. The immense distances between them will grow so vast that interactions and mergers between galaxies will become exceedingly rare. In the current era, gravity plays a dominant role in the formation of galaxies and galaxy clusters. However, as dark energy becomes the prevailing force, this gravitational pull will give way to the repulsive force of dark energy, leading to a dramatic transformation in the nature of the cosmos. One immediate consequence of this accelerating expansion is the cessation of new galaxy formation outside of gravitationally bound clusters. As galaxies drift further apart, The gas necessary for new stars to form will become too diffuse to collapse under its own gravity. Existing galaxies, meanwhile, will exhaust their remaining gas reserves. Once the material needed for star formation is depleted, new stars will cease to be born, and the process of star formation will come to an end. This expanding universe will also have profound effects on the observable universe. In the present day, we can observe galaxies that are billions of light years away, the light from which has had time to reach us since the Big Bang. However, as the universe continues to accelerate, the distance between us and these galaxies will increase at an ever-growing rate. In the far future, galaxies will drift beyond the observable horizon, making it impossible for future observers to see them, as their light will no longer have time to reach us. Ultimately, the interplay of dark energy, cosmic acceleration, and the inevitable isolation of galaxies will reshape the very nature of the universe. While much of this remains speculative, these models offer a glimpse into the breathtakingly distant future of the cosmos, one where the universe, as we know it, may eventually fade into cold and quiet isolation, leaving behind only the faint echoes of a once vibrant cosmic dance. However, as the expansion of the universe accelerates, more and more galaxies will recede beyond the cosmic event horizon. This is the point beyond which light emitted today will never reach us. The result will be a diminishing observable universe, with galaxies becoming increasingly isolated within their own local clusters or superclusters. These regions, though, will not be completely immune to cosmic changes. Local clusters, which remain gravitationally bound despite the repulsive force of dark energy, will continue to experience some degree of galactic evolution. Even in these isolated clusters, interactions and mergers between galaxies will persist for a long period, giving birth to new star formations and potentially new galactic structures over immensely long timescales. However, as the expansion of space continues, even these clusters will eventually drift further apart. This cosmic expansion will increasingly isolate galaxies, leading to the formation of a vast cosmic desert. As this happens, the night skies of these distant future galaxies will appear more and more empty. Stars within these galaxies will age and eventually die, leaving behind stellar remnants such as white dwarfs, neutron stars, and black holes. Over even longer periods, these remnants will cool and fade, heading toward what is known as the heat death of the universe, a state dominated by dark entropy. While these predictions paint a somewhat bleak vision of the universe's future, they serve as a reminder of the transient nature of our current vibrant, star-filled cosmos. The accelerating expansion of the universe will fundamentally reshape the fabric of the cosmos, turning once clustered and interactive galaxies into isolated islands of aging stars, surrounded by an ever-expanding ocean of dark energy. This shift will create a stark contrast to the dynamic, interconnected universe we observe today. As the universe continues to age, the stars will gradually burn out, and the prospects for life as we know it will change drastically. The dwindling of stellar energy sources, along with broader cosmic factors, will reshape the very nature of existence. This phase, often referred to as the degenerate era, will be dominated by stellar remnants and faint, long-lasting celestial objects. Despite the challenges, life could continue to exist for billions of years in the more immediate future, particularly around stable stars like our Sun or the long-lived red dwarfs. Red dwarfs, in particular, possess lifetimes that extend into the trillions of years, offering prolonged stability for any planets that may harbor life within their habitable zones. Yet, even these stars will eventually exhaust their nuclear fuel, pushing the universe into a phase where star formation ceases and existing stars gradually burn out. As the most massive stars die, they will leave behind remnants, white dwarfs, neutron stars, and black holes. It is possible that planets orbiting white dwarfs could host life, provided they remain within the habitable zone. However, these habitable zones would be much closer to the remnant star, and the conditions for life would differ dramatically from those around a main sequence star, due to the much lower energy output of white dwarfs. In the distant future, as stars continue to fade, the universe will continue its inexorable march toward an era dominated by silence, darkness, and the slow decay of once vibrant galaxies. As the universe ages, it will face an inevitable and gradual decline that spans billions to trillions of years. During this time, potential biospheres, if any remain, will become increasingly frigid and starved of energy. In the remnants of collapsed stars like neutron stars and black holes, life would find the most hostile of environments. To survive around these objects, life forms would need to adapt to extreme gravitational forces and intense radiation fields, making it almost impossible for life to thrive. The habitable zones around such stellar remnants, if they even exist, would be incredibly narrow, plagued by constant dynamical instability and high levels of radiation. Over time, the remaining stellar remnants will slowly cool and fade away, marking the beginning of an era where only the faintest glow of white dwarfs and brown dwarfs will remain. Brown dwarfs, often called failed stars, might offer some minimal heat, but low luminosity would make them poor hosts for complex life. Eventually, even these objects will exhaust their meager supplies of fusion fuel, and the universe will be left populated mostly by dark, cold remnants drifting aimlessly in space. In this distant future, any form of life would face severe energy scarcity, relying on non-stellar energy sources, if such sources even exist. Theoretically, advanced civilizations might adapt by tapping into alternative energy sources. They could harness the faint residual heat from black holes through processes like Hawking radiation or exploit geothermal energy from the cores of large planets. These civilizations might also develop technologies capable of artificially sustaining biospheres, possibly through fusion reactors or other technologies that we have yet to even imagine. However, as the universe continues its relentless march toward higher entropy and approaches the so-called heat death, the availability of usable energy will dwindle to nearly zero. In this state of near-complete thermodynamic equilibrium, life would find it almost impossible to survive. The cosmos would become an expanse of near-uniform temperature, its only light coming from the faint glow of background radiation and the remnants of stars that once burned brightly. The gradual extinction of stars charts a course towards an increasingly inhospitable universe, pushing the very boundaries of life's resilience. While the distant future is purely speculative, it serves as a profound reminder of the transitory nature of cosmic epochs and the extraordinary adaptability of life in the face of such challenges. As the universe moves toward an era of extreme darkness and cold, the nature of dark energy, the mysterious force responsible for the accelerated expansion of the universe, becomes increasingly important. Dark energy will play a critical role in determining the ultimate fate of the cosmos. Depending on the properties and behavior of dark energy, the universe's long-term evolution could take several dramatically different paths. One of the most widely discussed models of dark energy is the cosmological constant, often denoted by the Greek letter lambda. In this model, dark energy is a constant, unchanging force, akin to a vacuum energy, that permeates all of space. If this model holds true, the universe will continue expanding at an ever-accelerating rate, and galaxies will recede from one another faster and faster. Eventually, these galaxies will move beyond each other's observable horizons, causing the universe to enter a state known as the Big Freeze or heat death, where it becomes cold, dark, and empty. Stars will burn out and galaxies will drift into isolation. Alternatively, there are models that involve quintessence, in which dark energy is dynamic, with its energy density changing over time. If dark energy weakens, the expansion of the universe could slow down, potentially stabilizing the cosmos or even reversing the process, leading to a contraction of the universe. This scenario is known as the Big Crunch. In this model, the universe could collapse back into a highly dense and hot state, possibly setting the stage for a new Big Bang in a cyclic model of cosmic evolution. On the other hand, if dark energy continues to strengthen over time, the universe could face an even more catastrophic fate known as the Big Rip. In this scenario, the repulsive force of dark energy becomes so strong that it eventually overpowers all other forces. It would first tear apart galaxy clusters, then disintegrate individual galaxies, and ultimately it would overcome the gravitational forces holding star systems together. The fabric of the universe itself could unravel, leading to an end where all structures are obliterated, leaving behind only the void. These potential futures, whether they lead to the Big Freeze, Big Crunch, or Big Rip, reveal the cosmos as a place of constant change and unpredictable fate. The fate of the universe, shaped by dark energy and the eventual fate of all stars, will profoundly influence not just the structure of the universe, but the very possibility of life itself in the distant future. As we look toward this far-off future, we are reminded of the delicate balance that governs the cosmos and the fragile nature of existence itself. And finally, imagine a cosmic fate so devastating that it rips apart the very stars, planets, and even the atomic and subatomic structures that make up all matter. This catastrophic end, known as the Big Rip, would unfold in an ever-accelerating expansion, gradually disintegrating everything in its path. The universe, propelled by an unstoppable force, would stretch beyond any known limits. The disintegration would be swift, profound, and unstoppable. Some cosmological theories suggest that dark energy, the mysterious force accelerating the universe's expansion, could undergo phase transitions. Much like certain materials change state under varying conditions, dark energy's behavior might evolve, bringing new dynamics into the cosmic picture. Such transitions could alter the delicate balance between expansion and contraction, potentially steering the universe toward an unexpected fate. This possibility could lead to shifts in how the cosmos evolves, deepening the mystery of its final destiny. Adding another layer of intrigue, there's the speculative idea of phantom energy, a form of dark energy where the equation of state parameter, a ratio of pressure to energy density, falls below -1. If phantom energy governs the cosmos, the expansion rate would accelerate at such an extreme pace that the universe would experience the Big Rip far more dramatically than current models predict. This would push cosmic evolution to its absolute limits, making the universe's end seem like an inevitable, unstoppable force. Current and future cosmological missions are dedicated to understanding the true nature of dark energy. For instance, the European Space Agency's Euclid mission and NASA's Wide Field Infrared Survey Telescope, WIRST, are designed to precisely measure the universe's expansion rate. These missions aim to gather crucial data on the large-scale structure of the universe, shedding light on the behavior of dark energy and its role in cosmic evolution. Yet, even with all these technological advances, the ultimate fate of the universe remains an enigma. Will dark energy lead to a cold, desolate universe, a dramatic disintegration of all matter, or perhaps even a cyclical regeneration of cosmic life? These questions speak to a profound curiosity about our universe's long-term evolution. From the smallest particles to the largest galaxies, dark energy is at the heart of understanding the ultimate destiny of all that exists, including the possibility of life itself. The Big Rip scenario, although hypothetical, is one of the most dramatic and mind-bending theories in cosmology. It imagines a time when dark energy grows so powerful that it literally tears apart the fabric of space-time. In this theory, the universe's expansion accelerates to an unimaginable extent, overcoming every other force in existence. The consequences would be progressively catastrophic. At the earliest stages, galaxy clusters begin to drift apart as gravitational forces no longer hold them together. Galaxies themselves become isolated as the accelerating expansion pulls them away from each other. As the expansion continues, individual galaxies, which have their own gravitational forces keeping them intact, would begin to unravel. Stars within galaxies would drift alone, disconnected from their once dominant forces. Solar systems would experience their own breakdown. Planets, moons, and all other celestial bodies would be torn away from their stars, powerless against the relentless pull of dark energy. Eventually, the forces at work would overcome the gravitational forces binding stars, ripping them apart. In the final moments, the expansion would become so extreme that even atoms would fail to hold together. Electrons would be stripped away from their atomic nuclei, while nuclei themselves would disintegrate. The fundamental particles that make up all matter would be torn apart. The force of expansion would grow so powerful that it could even disrupt the very fabric of space-time. The concept of distance, once a foundational aspect of physics, would cease to have any meaning, as distances between points in space would stretch to infinity. While the Big Rip is a captivating vision of the universe's end, its likelihood hinges on the precise properties of dark energy, properties that are still not fully understood. Ongoing and future observations aim to measure the equation of state parameter for dark energy with greater accuracy. If this parameter is found to be less than -1, it could provide support for the Big Rip hypothesis. However, current evidence suggests that this parameter is close to -1, in line with the cosmological constant model, keeping the final fate of the universe uncertain and open to exploration. The fate of the universe is a topic that has fascinated scientists for centuries. Among the many theories that attempt to predict its end, one of the most unsettling is the idea of a Big Rip. However, this is not the only potential outcome. Alternative theories, like those involving dark energy's quintessence or evolving scalar fields, offer different possibilities. These models suggest that dark energy may not remain constant, but rather change over time, potentially leading to scenarios like the Big Freeze or a cosmic rebound. While the Big Rip remains one of several speculative futures, it underscores the immense uncertainties surrounding the nature of dark energy. The question of whether the universe will end in a catastrophic tear, a slow freeze, or even a cyclical rebirth continues to challenge our understanding of cosmology and the fundamental forces that shape the cosmos. One intriguing concept that further complicates our understanding of the universe's fate is the potential decay of protons. Although no direct evidence has been observed, several grand unified theories, GUTS, predict that protons, long considered to be stable, might have a finite lifespan, potentially decaying into lighter particles such as positrons and neutrinos. If proton decay does occur, it would be an extraordinarily slow process, predicted to take anywhere from 10 to the power of 31 years to 10 to the power of 33 years. If this process happens, the gradual disappearance of all baryonic matter, which includes the atoms that form everything we see, would unfold over an unimaginable timescale. As protons decay, the structure of the universe would begin to disintegrate. All ordinary matter, stars, planets, and even celestial bodies, would break down into their constituent parts. Stellar remnants such as white dwarfs, neutron stars, and black holes would eventually decay as well. White dwarfs, composed mostly of protons and neutrons, would slowly break apart, leaving behind a trail of subatomic particles. Neutron stars, similarly, would disintegrate. Black holes, though they may persist for a much longer period, would eventually succumb to Hawking radiation, which causes them to evaporate. Over time, the universe would lose all of its matter, and life as we know it would cease to exist. The decay of protons would have a devastating effect on any remaining biological structures. Proteins, DNA, and other biomolecules, all of which rely on stable atomic structures, would disintegrate. Even if advanced civilizations existed, their attempts to sustain themselves would be futile against the gradual decay of fundamental particles. As the last of the matter disappears, the universe would be dominated by radiation, photons, neutrinos, and other nearly massless particles. This transition would lead to a state of maximum entropy, where energy is evenly distributed, and structures that once defined the cosmos would become unrecognizable. Over trillions of years, the universe would cool to a state approaching absolute zero, with energy spread thinly across a featureless expanse. As entropy increases, the universe would effectively become dead. No energy gradients would remain to fuel processes like stellar fusion or biological activity. The very fabric of the universe would unravel into an uninhabitable void. The scenario of the heat death of the universe, also known as the Big Freeze, aligns with this vision of an ever-expanding cold and dark cosmos. In this future, star formation would cease as the available gas and dust needed to form new stars would be exhausted. Existing stars would eventually burn out, and their remnants, white dwarfs, neutron stars, and black holes, would cool and fade over billions of years. Without any source of energy, the universe would become a bleak, lifeless place. Atomic and molecular bonds would break down, and the universe would transition to a state where no significant astrophysical processes could occur. Experiments aimed at detecting proton decay, such as those conducted in particle detectors like Super Kamiokande in Japan, have been ongoing for decades. However, no definitive signs of proton decay have yet been observed, suggesting that if it occurs, it is at a timescale far beyond the reach of current technology. The confirmation or rejection of proton decay remains a critical piece of the puzzle in understanding the ultimate fate of matter and the universe itself. In conclusion, the potential decay of protons and the ultimate heat death of the universe underscore the transient nature of matter and energy in the cosmos. The universe is on a slow, inevitable journey toward a state of maximum entropy, where all matter and energy will be evenly distributed and all processes will cease. While the mysteries of dark energy and proton decay continue to challenge our understanding, they also remind us of the fragile, ever-changing nature of the universe we inhabit. The universe, as we know it, is steadily marching toward an inevitable fate, one shaped by the mysterious force known as dark energy. This accelerating expansion is slowly but surely pushing all remaining matter farther and farther apart. Over time, galaxies and galaxy clusters will become isolated islands separated by vast expanses of empty space. As this expansion continues, the observable universe for any remaining observers will shrink, confined only to their local region. Eventually, this isolation will reach a point where no new matter or information can traverse the ever-expanding void. This bleak future leads us to the concept of heat death, a state of maximum entropy where the universe has reached a point of complete disorder. In this scenario, all energy sources and structures capable of doing work will have dissipated. No longer will there be pockets of energy or activity to power processes. Everything will be uniformly spread across the cosmos, and all localized energy sources will have vanished. Without energy differences, there will be no spontaneous processes, no change, no events. The universe will settle into a still, lifeless equilibrium. In this frozen state, the concept of time itself would become irrelevant. Without any processes marking its passage, time would lose its conventional meaning. The universe would essentially become a static, unchanging void, with no events or interactions to create any sense of movement. From an experiential perspective, everything would cease. Life, intelligence, and consciousness, everything that requires energy and order, would vanish. The conditions for life, whether in the form of basic microbes or advanced civilizations, would no longer exist. This state of total entropy marks the end not just of physical processes, but also of the very possibility of awareness. It would be the complete cessation of consciousness and intelligence. The idea of heat death might seem like a distant and inevitable end, dictated by the second law of thermodynamics. This law forces the universe to slowly move from states of order and energy toward states of disorder and cold. It is a reminder of the universe's inherent dynamism, the continuous march toward eventual decline. But there's more to this tale of cosmic fate. The universe, while on the slow path toward entropy, could face an even more sudden and dramatic transformation. This possibility is rooted in quantum field theory, which introduces the concept of a false vacuum, an energy state that appears stable but might not be the true lowest energy state of the universe. The true vacuum, in contrast, represents the ultimate, most stable energy configuration. Currently, our universe could be sitting in this false vacuum, and while it seems stable, it could be precariously poised to transition to the true vacuum. This transition, if it were to occur, might happen through a quantum process called tunneling. In quantum tunneling, particles and fields can, through a probabilistic process, tunnel through energy barriers that would be impossible to overcome in classical physics. In the case of the false vacuum, this could mean that a small bubble of true vacuum could form spontaneously, expanding outward at the speed of light. As this bubble spreads, it would convert the surrounding false vacuum into true vacuum, fundamentally changing the very laws of physics in the process. Constants could shift, particle masses could change, and the nature of matter itself could be altered. Inside this bubble, all matter, atoms, molecules, and even fundamental particles might disintegrate or be restructured according to the new laws of physics. The potential consequences of this vacuum decay would be catastrophic. Not only would it rewrite the laws of physics, but it would obliterate everything in its path. The fabric of space itself would be torn apart as the true vacuum bubble expanded, devouring everything in its wake. The question remains, could this quantum transition happen? Current theories suggest that such an event would likely occur on a timescale far beyond the current age of the universe. The probability of a vacuum decay through quantum tunneling is extremely low, but because quantum events are probabilistic, it could theoretically happen at any time. Certain high-energy events, such as particle collisions far beyond the energies we can currently achieve, could potentially catalyze this process. If these conditions are met, the barrier between the false and true vacuum could be overcome, triggering a catastrophic shift in the very nature of reality itself. In this cosmic drama, the universe moves inexorably toward a state where energy and life are impossible. Whether through the slow creep of entropy or a sudden shift via quantum tunneling, the universe's fate seems sealed. The end of all things, it seems, might come in many forms, some gradual, others abrupt. But the eventual outcome is the same, a cold, lifeless void where nothing remains but the echoes of a once vibrant cosmos. However, such conditions are expected to be exceedingly rare, even among the high-energy phenomena of the universe. If vacuum decay were to occur, it would radically redefine the concept of cosmological fate in ways that would challenge our understanding of the universe's eventual end. Rather than the gradual approach of a heat death, where the universe drifts into a cold and thermodynamically inert state, or the dramatic rupture of the Big Rip, vacuum decay would instigate an immediate and profound transformation. This change would not be a slow evolution, but rather a sudden, all-encompassing shift in the fabric of reality. The idea of a false vacuum and the potential for quantum tunneling to trigger vacuum decay remains speculative, entrenched deeply in the realms of theoretical physics. It represents one of the most exotic and consequential scenarios in modern cosmology. These ideas are rooted in our understanding, or rather the limitations of our understanding of quantum field theory and the true nature of vacuum energy. For this theory to transition from the speculative to the concrete, we would need significant advancements in both theory and empirical evidence. Still, even as it stands, this speculation reveals the astounding complexity and profound mysteries that govern the ultimate fate of our universe. Another layer to these cosmic enigmas lies in the long-term fate of information in a universe that is dominated by black holes. The concept of information here refers to the fundamental details of particles and fields, their properties, configurations, and interactions. The fate of this information is an essential and hotly debated topic in the field of theoretical physics, touching on profound questions regarding the nature of black holes, quantum mechanics, and the conservation of information. At the heart of this debate is the so-called information paradox, first formulated by the legendary physicist Stephen Hawking. According to classical general relativity, any matter that falls into a black hole is effectively lost to the observer outside the event horizon, leading to the possibility that all information about the infalling particles or fields is irretrievably destroyed. This suggests a universe where, at some point, information simply vanishes, which contradicts fundamental principles of quantum mechanics. Quantum mechanics, particularly the principle of unitarity, tells us that information cannot be destroyed. It must persist in some form throughout the evolution of the universe. To reconcile this, Hawking proposed that black holes emit radiation as a result of quantum effects near their event horizons, a process now known as Hawking radiation. This radiation leads to the gradual evaporation of black holes, a process that, while theoretically sound, creates a new dilemma. The radiation itself is thermal in nature and appears to carry no information about the specific objects that fell into the black hole. This leaves us with a troubling question. If a black hole evaporates entirely, does the information it contained vanish as well? To resolve this paradox, various theories have been put forward, each suggesting different outcomes for the fate of information. One prominent theory is black hole complementarity, which proposes that information is both reflected at the event horizon and passes into the black hole. This would mean that two different observers, one falling into the black hole and one remaining outside, would witness complementary perspectives, thereby preserving the information without violating the principles of general relativity. Another fascinating idea is the holographic principle, which proposes that the information falling into a black hole is encoded on its event horizon. This concept suggests that all information within a certain volume of space can be represented as a hologram, a theory deeply connected to string theory and explored in the context of the ADS-CFT correspondence. The holographic principle offers a tantalizing solution, wherein the universe itself may function as a vast cosmic hologram. Finally, the firewall hypothesis emerges as a more controversial and radical solution. It posits the existence of a kind of information firewall at the event horizon of black holes, where infalling information is rapidly transformed into radiation. This would effectively break the laws of general relativity, but it would preserve unitarity, offering a potential resolution to the paradox. Each of these theories provides a unique lens through which to view the ultimate fate of information and, by extension, the fate of the universe itself. While we have yet to uncover definitive answers, these debates push the boundaries of our understanding, exploring the very nature of reality as we know it. The mysteries of black holes and quantum mechanics continue to challenge our deepest assumptions, offering insights into the future of cosmology that may one day reshape our view of the universe and its ultimate destiny. However, this hypothesis remains highly contentious, with no consensus among scientists. Some theories suggest that black hole evaporation could leave behind stable remnants that preserve all the information that has ever fallen into the black hole. These remnants would be extremely dense and small, maintaining the lost information but presenting new theoretical challenges. If, in the distant future, the universe were to be dominated by black holes, the long-term fate of information would depend on how the information paradox is ultimately resolved. As black holes slowly evaporate over timescales so long they defy human comprehension, the way they manage information will decide whether that information is lost or preserved in some form. In a scenario where information is preserved through mechanisms such as the holographic principle, even after black holes have evaporated, the encoded information might survive. On the other hand, if information is handled by a mechanism yet to be understood, the nature of information conservation could be fundamentally different from current models. Many physicists believe that resolving this paradox demands a more complete theory of quantum gravity, one that unifies quantum mechanics with general relativity. This theory could offer new perspectives on the nature of space-time and how information is preserved, potentially uncovering groundbreaking mechanisms that ensure information remains conserved, even in a universe dominated by black holes. The fate of information in the far future remains intertwined with some of the most profound questions in fundamental physics. As our understanding of black holes, quantum mechanics, and the very fabric of information evolves, new insights may not only answer the information paradox, but also reshape our understanding of the universe itself. In this compelling exploration, we venture into the speculative and thought-provoking future of the universe shaped by the potential influence of intelligent life. The idea of how advanced civilizations might impact the cosmos is both fascinating and boundless, offering us glimpses into a future where technology, science, and life itself evolve in ways we can scarcely imagine. If intelligent life continues to advance, the possibilities for their influence on the universe are profound. One of the most compelling concepts involves the creation of massive structures, such as Dyson spheres, enormous swarms of satellites designed to capture us energy output. This act alone could drastically alter the star's life cycle, influencing not only the local stellar environment, but the very fabric of the universe. These civilizations could tap into the immense power of stars, extending their lifespans and potentially engineering the cosmos on a scale beyond our comprehension. As technological capabilities develop, it's conceivable that future civilizations might be able to manipulate stars directly. Imagine harnessing the power of fusion, regulating stellar processes, or replenishing a star's fuel to stabilize habitable zones. Such capabilities could ensure long-term sustainability for biospheres, creating environments where life can thrive for millennia. In addition to this, civilizations could undertake massive galactic engineering projects, possibly rearranging stars, optimizing the distribution of matter, or even preventing the collision of galaxies. Such endeavors would require an unprecedented understanding of astrophysics, gravitational forces, and the very nature of space-time itself. But what of life beyond our own solar system? The spread of intelligent life across the galaxy could alter the very shape of the cosmos. Consider the deployment of self-replicating probes, devices designed to explore, gather data, and potentially terraform planets across the Milky Way. These probes could seed life in previously sterile regions, spreading life or its precursors to parts of the galaxy where no life previously existed. The possibilities extend even further with the potential harnessing of energy from phenomena like rotating black holes, tapping into cosmic power sources that could sustain civilizations for eons. Equally captivating are the speculative possibilities involving the stability of the universe itself. Should models of a metastable vacuum state hold true, an advanced civilization might possess the ability to prevent catastrophic vacuum decay, ensuring the universe's fundamental stability over vast timescales. With the delicate balance of the universe in mind, intelligent life might also devise ways to prevent mass extinction events, such as asteroid impacts or nearby supernova explosions, potentially protecting ecosystems and preserving biological life. The concept of spreading intelligent life beyond their home star systems could fundamentally reshape the future of the universe. From generation ships to faster-than-light travel, the possibilities for seeding distant regions of the cosmos with life are boundless. Such efforts could influence evolutionary pathways, shaping the future of matter and life throughout the galaxy and beyond. Furthermore, the establishment of communication networks spanning vast distances could bring about the formation of a galactic society where civilizations share knowledge and collaborate on large-scale projects, working together to solve problems and enhance their understanding of the universe. Perhaps most profound of all is the potential for advanced civilizations to influence the very expansion of the universe. With a deep understanding of dark energy, these civilizations could manipulate the universe's rate of expansion, slowing or accelerating it according to their desires. This ability could be pivotal in averting catastrophic events like the Big Rip or fine-tuning conditions for a cyclic universe in which the cosmos is reborn in an endless cycle. As the universe faces the eventual march toward entropy, the preservation of information could become a key focus. Advanced civilizations may discover ways to encode information in black hole event horizons, or even develop complex computational structures to safeguard knowledge beyond the physical limitations of the cosmos itself. This approach could ensure the survival of not only civilizations, but also the very essence of life as we know it, far into the distant future. The Kardashev scale provides an intriguing framework for understanding the potential of future civilizations, classifying them by their energy consumption and technological capabilities. From planetary-level civilizations, Type 1, to star-manipulating societies, Type 2, and ultimately to those capable of controlling entire galaxies or even universes, Type 3, the scale offers a roadmap for how life could evolve on an unimaginable scale. While these speculations may seem distant, they serve as a valuable lens through which we can examine our technological aspirations and our place in the universe. As we continue to explore the cosmos, it's clear that intelligence holds the key to transformative power, both locally within our own solar system and universally across the vast expanse of space.